I'm Patrick Michel, and my co-chairs or chairs are Megan Shalbrook and Angela Stickel, who made a wonderful work to organize this session, which will be very interesting. It's about deflection testing with a lot of numerical models, and we can see how these models advance, and hopefully that will allow us to validate them. So let's start with our first speaker. I think we had also an announcement that we'll have a poster session tonight at 9 p.m. open for interacting with people who have posters. So maybe the link will be shown later. But we can start with the first speaker, because we have 5 talks actually. So the first one is Sabina Raducan from University of Bern, and she will tell us about the cratering processes on rubble pile asteroids, insight from laboratory experiments and numerical models. You can come to the
next hello slide. Everyone. Can you hear me?
Yeah.
Can you show the slides? Great. And yeah, next slide, please. So we are here at the Planetary Defense Conference, and one of the main focus is the upcoming DART mission, which will impact Dimorphos and change its period of rotation around Didymos and deflect it. Next slide, please. But we know from past research that the amount by which we can deflect an asteroid is heavily influenced by the target properties and the impact conditions. And while we do know some impact conditions, so we know the impact velocity and we know the impactor mass and shape, so how the spacecraft will look like, we don't know much about the target properties. So we don't know the cohesive strength, the bulk density, porosity, or the internal structure. Next slide. And previous numerical models focused on quantifying the effects of target properties and simple structures on the consequences of the DART impact. And one of the main findings was that impacting targets with very different material properties and different simple structures can result in the same deflection. However, we also saw that these impacts create craters that have very different crater sizes or crater morphologies. And here are some examples for impacts into homogeneous targets, into layered targets, and into targets with a porosity gradient, which have similar deflection, which produce a similar deflection, but different craters. So to be able to characterize the target, we'll need a measure of both the deflection, so the deflection efficiency, and of the impact craters. But the problem is that this past research, they only looked at very strong targets, stronger than about 100 pascals. Next slide. And if we are looking at the recently visited asteroids Ryugu and Bennu, they both seem to be rubber pile asteroids with little to no surface cohesion. So can the Dimorphos also be a rubber pile? What happens if we impact such an asteroid? And next slide. And there are several works that are looking at DART-like impacts into rubber piles. But to increase our confidence in our numerical models, we need to validate them against laboratory experiments. And we need laboratory experiments that are purposely designed to mimic asteroid surfaces. Next slide. And one such experiment was recently conducted at the Experimental Projectile Impact Chamber in Spain. So we conducted vertical impacts in quarter space into heterogeneous targets at about 400 meters a second. And the target consisted of 4 layers of porous ceramic boulders embedded in a matrix of dry beach sand. And we can see the configuration here in the image. And the boulders were chosen in such a way that they resemble the mechanical properties of the boulders on Bennu, and that is in terms of strength and of porosity. Next slide. And here are a series of snapshots from this EPIC experiment. And then we used the Bern SPH code to try to model this experiment, which is shown on the right. But in the simulation, we model the entire geometry. So we model it in half space rather than quarter space. Next slide. And then due to resolution constraints, we only model the slow ejecta. So the fast ejecta that is seen in the experiment is not going to be seen in the simulation. And next slide. And here's the crater at 10 milliseconds after the impact. Next slide. and at 20 milliseconds after the impact. Next slide. And at 35, and next slide. If we're looking at the final crater morphology from this impact experiment, we see that we created a crater that was about 20 centimeters in diameter and about 30 centimeters deep. Then we compare our numerical SPH simulation, which is here shown in this yellowish orangey color. We can see that the crater size matches very well with the experiment. And then if we compare this crater with the crater profile from a similar impact into a homogeneous target, which is shown in white here, we can see that the crater into the homogeneous profile seems to be twice as large as the impact into the heterogeneous target. And this is still work in progress, but it's possible that the cratering efficiency was affected by impact armoring, similar to the craters on Bennu, as we saw in the OSIRIS-REx session on Monday. And then next slide. Then when we look at the boulder distribution from this experiment, this can be categorized in three groups. So the boulder that was placed at the impact point got completely crushed and is this whitish material at the bottom of the crater. Then the boulders that were placed in a close proximity to the impact point got ejected far away, which can be seen in these red circles. And then the boulders that were placed more than about 2 impactor diameters away from the impact point got redistributed around the crater rim. And we can see that our SPH simulations was able to closely reproduce this boulder distribution. Next slide. And now that we have a well-validated code, we can use it to model dart-like impact on heterogeneous targets. And here is shown as an example, a dart-like impact into a spherical homogeneous target with no cohesion. And this is the target morphology 2 hours after the impact. And next slide. So we modeled dart-like impacts into spherical rubble pile asteroids, for which we used different distributions of boulders. So the first one was the grid-like distribution of 2.5 meter boulders, then a random distribution of 2.5 meter boulders, and then a random distribution of boulders between 2 and 10 meters. And next slide. And this is how the target morphology looks about 2 hours after the dart-like impact. And we see that the morphology of the target is quite strange. And then there were boulders that got ejected far away. There were boulders that got redistributed on the surface. Next slide. And here's a comparison to a similar impact into a homogeneous target. And then next slide. And then if we're looking at the deflection efficiency from this impact, we can see that the presence of the boulders reduced this deflection of efficiency, which we usually call it beta, by quite a large amount. And then we can also see that the size and the distribution of the boulders also affect beta. And then next slide. So the DART mission is likely to impact the rubber pile asteroid. But we need well-validated models to be able to model more realistic impact scenarios. And then our SPH simulations show that dart-like impacts on spherical, weak, cohesionless asteroids may not create an impact crater, but rather change the morphology of the target asteroid. And that we also see that the distributions of the boulders in the asteroid will affect not only this morphology, but also the momentum transfer efficiency. And next slide. And thank you.
Perfect, right on time. Thank you, Sabina. So we can go to the next talk. We'll have the session of questions afterwards. Thank you very much. So the next talks will be given by Robert Luther from the Museum for Natural Kind of Berlin. And his talk will be about the kinetic impactor techniques, benchmark, and validation studies with ICEL and SPH.
Yeah, hello to everyone. So next slide, please. Yeah, so I present you our benchmark and validation study focusing on the kinetic impactor technique in the context of the DART and the HERA missions. Next slide, please. So as you have heard from the presentation from Sabina before, the effect of kinetic impactors on the asteroid and its orbital change depend on the material properties of the asteroid. In this study, we used two shock physics codes, namely ICEL and SPH, to simulate the outcome of a kinetic impactor event for different target material properties. Both codes include complex material models that account for a range of rheologies, material damage, or porosity compaction. ICEL is a grid-based code, while SPH is a particle code. So you see a small representation there in the slide for this. To prove that both codes produce accurate results, we validate them against laboratory experiments with low-strength granular targets and benchmark them against each other. We especially validate against experimentally derived values of the momentum enhancement factor beta, which describes the imparted momentum to the asteroid. Next slide, please. For the validation of our models, we chose a series of impact events published by Chewy et al. 2020, who impacted quartz-sand, glass beads, and regular simulant targets with cylindrical PVC projectiles at velocities between 1 to 3 kilometers per second. On the left on the slide, you see the experimental setup with on top a vertically mounted accelerator and the high-speed camera to the side. Besides the initial cratering evolution within the first milliseconds, Chewy et al. Observed the crater size, measured the ejector curtain angle, and, which is important for this study, determined the transferred momentum based on the movement of the target pole, you see to the left, which is attached to a spring system. Next. In the center, you see two high-speed images from half millisecond after the impact, at the top for regolith and at the bottom for glass beads. So modeled ejector curtains are overlain over the high-speed images, and the curtain angles fit the ones from the experiment. The glass beads show a much steeper curtain angle than the regular simulant, which mainly comes from the smaller coefficient of friction. In the following, I will focus on the regular simulant. Next slide, please. On this slide, I discuss the crater diameter, but before, I would like to give you some short impression of the cratering event in regular simulant. If you click the next two slides back and forth, you see some kind of short animation for cratering down there. And so this is an impact in regular simulant at 2.2 kilometers per second. And you can nicely see this shallow crater curtain as also on the snapshot from the slide before. On the figure on the left, we compare the results for crater diameters for different impact velocities. The violet circles show results derived with ICEL, while the green triangles show results using SPH. We have used similar material models and parameters for both codes. And you can find them in the table there. And we find a reasonable agreement between the two codes and also the experimental results, especially when we consider the scatter in the experimental data itself. Towards faster velocities, the results between the two codes differ more than for the slower impact velocity. Next slide, please. This deviation for the models in greater diameters for the faster impacts is not seen for the beta values, which are shown here for the same models and experiments. So the x-axis shows again the velocity and the y-axis the momentum enhancement. The agreement between models and experiments is remarkably good. Next slide, please. We extended the benchmark, the study to impacts with 500 kilogram dart-like projectile impacting at 6 kilometers per second into a large range of materials similar to the regular simulant. For these, we vary the porosity between 20 and 50%, so which is shown on the x-axis, and the target cohesion between 1, 10, and 100 kilopascal, which is represented by the three colors. The y-axis shows again the determined beta. The solid lines show the ICEL results, and the dashed lines the one for SPH. So we can find in general a good agreement between ICEL and SPH for a range of combinations of porosity and cohesion. Next, please. Yeah. To the lower end, at 20% porosity, we can find an increase of the beta prediction from ICEL by about 20% with respect to the SPH values at 1 kilopascal and 100 kilopascal cohesion. For 50% porosity and 10 kilopascal cohesion, SPH predictions exceeds the ones from ICEL by about 20%. However, also this deviation is still a good result. Next, for the case of 20% porosity and 10 kilopascal cohesion, we also compared the effect of the impact angle. Next slide, please. So the impact angle is shown here on the x-axis with the vertical impact on the right side, and the y-axis shows the impact angle scaled momentum. So we normalize to the vertical momentum of the projectile. With decreasing impact angle, so shallower impacting projectile, the impact angle scaled momentum decreases by about 25% for impacts at 30 degrees with respect to the vertical plates. Next, please. Yeah, it's shown here. And yeah, exactly. And the results between the, no, one back, please. Yeah, and the results, however, between the two codes differ only by about 9% at the largest scatter there at 30 degree impact angle. Okay, next, please. So summarizing, we have shown that both ICEL and SPH can reproduce laboratory results in the HERA-relevant low-strength regime, HERA and DART, of course, for regular simulant in terms of diameter and ejection behavior. We have validated our codes against experimentally determined momentum enhancement factors, which is important, I think. And the benchmark between the codes for different porosities and cohesions shows good agreement between the two codes. As shown in a previous study by Stigler et al. 2020, the predictions of beta can deviate by about 20%, so we're in the same range. The deviation is smaller when we compare the effect of the impact angle, but also here we of course want to do further studies to test for different materials here. Yeah, we want to analyze the source for the deviations between certain material parameters between the codes. And yeah, so we will also plan to do further validations. And with this, I thank you for your attention.
Okay, thank you, Robert. Thank you for this very good talk. So just for the participants, I'm checking the chat, and I plan at the end of the 5 talks to open a question from the chat. So if you have questions, put them in the chat. Of course, the speakers can also respond as Sabina just did for one question, but don't hesitate to put in the chat, and we'll come back at the end with all the speakers to respond to some of these questions. Thank you, Robert, again. And we move to the next talk. So the next talk will be given by Ryota Nakano from Auburn University. And the talk will be about the NASA double asteroid radiation test, orbital perturbation by the ejecta collision-driven reshaping of Didymos after the impact event. Thank you.
Can you hear me?
Yes.
Okay. Thank you for the introduction. My name is Ryota Nakano. I'm a PhD student working with Toshi Hirabayashi at Auburn University. As introduced, my presentation is entitled NASA Double Asteroid Redirection Test, Orbital Perturbation by the Ejecta Collision-Driven Reshaping of Didymos after the Impact Event. Next slide, please. So let me introduce motivation first, why we are interested in this analysis. So the main reason is that Didymos is spinning at close to its spin limit. As you know, Didymos is a top-shaped asteroid spinning at 2.26 hours. Given this fast spin, we considered Didymos may be structurally sensitive to reshaping. So even small perturbations, such as ejecta cloud hitting on Didymos, which can deliver kinetic energy, and also seismic shaking attenuation due to the dart impact, may trigger reshaping. And this analysis is particularly important in order to determine, accurately determine the momentum transfer coefficient, which is beta parameter, and to assess overall the dart deflection capability. Next slide, please. So the question we want to answer is how Didymos reshaping affects the orbital period after the dart impact. We took a statistical approach to investigate this. While the reshaping magnitude is unknown, we have some knowledge from previous studies, like how top-shaped asteroids would reform. Also, ejecta will distribute heterogeneously on Didymos, which will lead to asymmetric reshaping. So using under these two assumptions, we developed a shape model generator to create reshaped shape models of Didymos. Next slide, please. So we modeled the reshaping by using 4 parameters: alpha positive x, negative x, positive y, and negative y. Each alpha values represents the ratio of each axis for the reshaped body to that of the original body. And the magnitude of reshaping is controlled by alpha max value. So let me explain the process by using the example shown on the right. So I first defined alpha max as 1.1 as an example, which corresponds to about 40 meters of reshaping. Given this alpha max value, or I can say threshold of each alpha values, 4 parameters are randomly selected from 1 to 1.1. So if you look at 4 values, none of these exceeds 1.1. Using 4 parameters, 4 values, we modified the original shape model of Didymos as shown in the right. And please note that alpha for z-axis is uniquely determined by considering the volume to be constant regardless of the shape. Next, So we considered 12, So we considered 12 different alpha max cases. And for each alpha max, we considered 500 cases. So in total, we have 6,000 simulations to be propagated in a dynamical simulation. Next slide, please. So this is the result of 180 days of propagation. I show Dimorphos orbital period change after 180 days from the impact as a histogram. So here I only picked 2 alpha max values, 1.05 and 1.001, which corresponds to less than 20 meters of reshaping and less than 1 meters of reshaping. If you look at the histogram on the left, we can see orbital period change is in a range from about 100 seconds to 700 seconds, with the mean at around 420 seconds. On the other hand, when we have much smaller reshaping, the orbital period change was in a range from 2 seconds to 16 seconds, where the mean is located at around 8 seconds. Next slide, please. So here, one important consideration is that determining the alpha max value for each axis, determining the alpha values for each axis by using ground-based observation may be difficult. However, we can constrain reshaping magnitude by detecting spin period change. By that, Didymos angular momentum should be conserved at any time. So if the reshaping event occurs, the momentum inertia of the shape should change, and accordingly, the spin period should also change. Using this consideration, I obtained this table. So if alpha max is about 1.1, then the spin period, the mean spin period would be around 840 seconds Whereas if we have alpha max as 1.001, we have mean spin period change of around 8 seconds. The reason why I say mean is because for each alpha max value, I have 500 data sets, and I'm simply taking the mean of the spin period change. And using these spin period change values and using the orbital period change mean orbital period change values I showed in the previous slide, we can obtain this linear relationship. The blue stars are the data set we have, and the black solid line is the linear fit, and dotted shaded region showing the 1 sigma error region. Next slide, please. So in conclusion, from the statistical investigation we took, we found that for a shape change of less than 40 meters, the reshaping-driven orbital period change is characterized to be linear, and we predict the relationship as change in orbital period is equal to negative 0.98 times change in spin period minus 3.905. Here, this minus 3.905 should ideally be 0, but because of the statistical nature we took, and also because we are just using simple linear fit, we have this y-intercept value. The orbital period should always become shorter than the original period for the head-on data impact scenario. And like I mentioned earlier, detailed observation of DDMOS spin period change can constrain the magnitude of reshaping, and from which we can determine, we can decouple the reshaping driven orbital period change and can accurately determine the momentum transfer efficiency. And one thing to add as an important fact is that according to Dr. Peter Plavik's presentation at DDMOS observation workshop in 2018, we may obtain observation accuracy with 1 sigma error of 0.036 seconds. This means that less than 1 centimeter of reshaping could potentially be detected. And with that, I end my presentation, and thank you very much for your attention.
Thank you very much. Thank you for this great presentation. So we move to the next talk by Patrick King from APL, and he will tell us about the late time nuclear disruption in the PBC 2021 scenario.
Thank you. Can you hear me?
Yes.
Very good. Okay, there we go. Thank you for the introduction. I will be presenting some of the work myself and some of my colleagues at Livermore have done on modeling nuclear disruptions for planetary defense, specifically in the context of late-time interventions. I hope you agree that, given the details of this year's exercise, that our results are particularly timely and relevant. Next slide, please. As a quick summary of our work, we present the numerical simulation of one example of a nuclear disruption event, conducted using the hydrocode Spheral. I'll present both the general methodology of the simulation and the main results we obtained. This simulation is then used as a guideline to inform our gravitational simulations of the trajectories of the fragments in the solar system. After presenting the methodology of the gravitational simulations, I will conclude with a simple summary of the implications of our study tailored for the PDC 2021 scenario. Next slide, please. We focused this particular study on understanding the far-field behavior of the fragments resulting from a robust nuclear disruption. The Spheral simulation consisted of a 100-meter asteroid target whose shape was chosen to be a scaled-down model of Bennu. Shown in the top left is a 3D perspective view of the object's initial zoning. The shaded region indicates the ablation zone, where the simulation resolution was tailored to capture the energy deposition curve. Examples of this deposition curve are shown in the bottom left. A 1 megaton device was situated 15 meters above the equator, or 65 meters from the center. The disruption was then calculated as the subsequent hydrodynamic evolution of the body. The plot on the right contains a slice through the middle, showing the pressure and internal energy of the material as the strong first shock is traversing it. The body was chosen to be uniform density with 25% microporosity. We used standard geological models for the material strength and equation of state. This methodology is consistent with the Livermore team's approach as described in recent publications. Other talks and posters by my colleagues from Livermore can provide more details on the physics of this process. Next slide, please. To characterize the disruption, we computed statistical properties of the bulk particles of the target after half a second of physical simulation time. Since we do not opt for a complete fragmentation model, the statistics of these bulk particles serve as an estimator of the post-disruption fragment field. Of the initial 1 megaton of device energy, about 60 kilotons was delivered to the target, and 4 kilotons of that was converted to kinetic energy of the bulk particles, an efficiency of about 0.35%. This energy divided by the bulk mass provides an estimate of the robustness of the disruption. This should be compared against Q star D, our disruption threshold. In this case, an object of this size and composition has a Q star D of about 1 joule per kilogram. Our disruption is roughly 17,000 times greater than this, demonstrating that this is a very robust disruption. We will characterize the disruption by considering both the deflection and disruption components. Any disruption transfers enough momentum that it will provide an overall deflection of the fragments in addition to dispersing them. This corresponds to the center of mass frame velocity of the fragments. Inside the center of mass frame, the relative velocity of the fragments provides the disruption velocity. The center of mass frame, position and velocity of the fragments, is provided in the top left plot. We find that the fragments are deflected with a velocity of about 47 meters per second and disrupted with about 49 meters per second. As a final check, we calculate how uniform and radial the disruption is in the center of mass frame. To determine how radial it is, we compare the position and velocity vector alignment in the center of mass frame. The distribution of this angle is plotted in the top right. Perfectly radial expansion should show a distribution close to 0 degrees. We find a generally small angular distribution centered around 20 degrees, indicating a mostly radial expansion with some higher structure. Similarly, we can determine in the distribution of fragment velocities on the sphere, which indicates how uniform it is. This is plotted in the ATOP projection provided in the bottom right. We can compare a power spectrum decomposition of this compared to some strongly directional distributions. We find that it is mostly flat, dominated by the lowest order mode, where the directional distributions are strongly peaked at higher order modes. Taken all together, we will model our disruption as a collection of fragments deflected from an original orbit and dispersed according to an approximate spherical expansion proportional to the disruption velocity. Next slide, please. To properly assess the consequences and effectiveness of a disruption, we need to follow the orbits of the fragments as they evolve under the solar system conditions they experience and the impulse we provide them. We adopted an N-body approach with the solar system instantiated as large particles and generate a suitable impacting orbit according to the desired scenario parameters. The impactor is replaced with the approximate fragment field and integrated forward. The impacting fragments are then tallied. Each scenario was tested to ensure that our system results in an impact trajectory if no action is taken. An example, using the PDC 2019 scenario, is shown in the top plot, along with some diagnostic plots from the perspective of the impactor. We employ softened gravity to ensure system stability, but this approach does soften out the early time fragment-fragment interactions. We ensure the accuracy of certain effects, especially gravitational focusing by the Earth, by controlling this softening length. A snapshot of the fragment field is shown in the bottom right plot. The blue point indicates the position of the Earth. In this case, the fragment field was very well dispersed. Next slide, please. Because there is a fair degree of uncertainty in the size of the impactor, we should consider how we will handle scaling our disruption results to other conditions. We will employ a naive velocity scaling informed by simple energy balance, noting that this approach is overly simplistic and needs to be studied in greater detail. In particular, the numbers we employ here should be revised using the best available target data and repeated over a variety of yields and heights of burst to verify the scaling of velocity with yield and size. The plot on the right encapsulates how this naive scaling functions. In this plot, we have a device yield on the x-axis and the target size on the y-axis. On the one hand, the device yield is a controllable mission parameter that may be subject to restrictions. On the other, we are unsure as to the mass of the object, which can be treated as an effective size. The plotted color scale is the velocity scaling relative to the nominal values provided earlier, which we would use to obtain the scaled velocities. The color lines indicate contours for the scaling, at 100% in blue, 10% in cyan, and 5% in red. As you can see, at nominal yield, we achieve about a 5% efficiency if the object is at the upper end of the uncertainty region. Similarly, if the object is at the lower end of the size uncertainty region, the same disruption can be achieved at lower yield. We will study these three scalings to bound our uncertainty and provide answers that can be interpreted in the context of the PDC 2021 scenario. Lastly, I will comment that our principal figure of merit is the impact fraction, which is defined as the ratio of impacting mass to the original mass of the impactor. Next slide, please. To provide an assessment for the PDC 2021 scenario, we computed impact fractions as a function of the time before impact the object is disrupted, using the date of impact and impactor orbit provided in the exercise index. In this study, we consider three velocity scalings and three different disruption velocities, three different disruption directions, to bound the range of possibilities as broadly as possible, resulting in 9 variants. These are presented in the two plots shown here, in linear scale on top and a log scale on bottom, to showcase different regions of the plots. The time to impact is shown on the x-axis. Longer times to impact indicate that the object was disrupted with more time before the actual impact. You may recall that in the context of deflection missions, it is desirable to direct the deflection in the direction of the object's orbit, as that leads to secular increases in deflection over many periods. Since we are sub-period here, this effect may not be present, but we want to understand the role that different directions can play in these types of emergency situations. The three relevant directions are the in-orbit direction, shown in blue lines, the radial direction directed outward relative to the sun, shown in cyan lines, and the ecliptic out-of-plane direction, shown in red lines. As I mentioned before, we are also conducting three different velocity scalings. The solid lines are the nominal 100% scaling, seen as the bottom group of three plots, 10% scaling in dashed lines, seen as the middle group of three, and 5% scaling in dashed dot, shown in the top as the top group of three. To summarize, the three directions are generally similar to each other, consistent with expectations, and the curves are generally grouped with velocity scaling. The radial direction may have some advantage relative to the others in this scenario, but this needs to be confirmed with further study. At the nominal scaling, the impacting mass can be reduced to 1% by as little as 2 weeks before impact. However, for the more marginal scalings, this is far more modest. By 2 months, the nominal case has likely achieved 0.1% impact fraction, but we need to run more expensive simulations with more fragments to resolve that region. The scenario has passed into the noise at this point. The 10% efficiency case, corresponding to roughly a 500-meter object at nominal yield scaling, can achieve 10% impact fraction by 2 months. For 5% efficiency, this is extended to 3.5 months. This underscores the challenge of this scenario. It is crucial to act as soon as possible to maximize the reduction in impacting mass to eliminate as much risk or damage as possible. I will conclude by restating the general conclusion for the nominal case. For a 100-meter object and 1 megaton device, the nominal velocity scaling appears to provide a 1% impact fraction if the object is disrupted by at least 2 weeks before impact. Thank you for your time, and I can answer any questions at the end of the session.
Thank you very much. Thank you for this fascinating talk. So we move to the last one of the session, which was extremely interesting so far. So we have Nicolas Gentil from Lawrence Livermore National Laboratory, and he will present his work on an overview of numerical radiation transport techniques in asteroid deflection modeling. Thank you.
Hi, I'm Nick Gentili from Lawrence Livermore National Lab. Next slide, please. I'm going to give a short overview of radiation transport methods in relation to asteroid deflection simulations. The simulations are being done with radiation hydrodynamics codes designed for inertial confinement fusion simulations. Radiation transport methods dominate the runtime, so we face trade-offs between speed and accuracy. Next slide, please. This is the photon transport equation, which we are solving in the code. It has terms which model material motion, corrections, and Compton scattering. For asteroid simulations, we need to take both of these effects into account to accurately calculate the energy and momentum coupling. Next slide, please. There are two common numerical radiation transport algorithms. The Monte Carlo method uses computational particles that act like photons. Random numbers are used to simulate emission, scattering, and absorption positions for these computational particles. A good feature, it can handle all of the physics. A bad feature, it has statistical noise, which declines slowly as a function of the number of particles, so it's computationally expensive. The SN, or discrete ordinates method, simulates the intensity at fixed angles. It's analogous to finite elements in angle space. A good feature, it's much faster than Monte Carlo. A bad feature, it can have simulation artifacts, especially in vacuum or low opacity materials. Next slide, please. These plots show simulation artifacts of the two methods. The top plot shows statistical noise in the radiation flux calculated with Monte Carlo. That's the gray line. The electron and ion flux, although they were calculated with diffusion, also show statistical noise. That's because of the statistical noise in the temperature that was caused by the Monte Carlo. The lower plot shows the radiation energy density from a point source in a medium with absorption but no scattering. So the top part of the plot shows the result from Monte Carlo, which has statistical noise in it. The bottom part shows the results from SN, which show ray effects because of the finite discrete number of angles. So we know how to fix the top plot by throwing more particles at it. We don't know how to fix the bottom plot without doing a lot of new theoretical development. So next slide, please. Diffusion is a very fast but approximate radiation transport option. It averages over the angle, so all the angular information is lost. Diffusion also approximates the flux. Both of these approximations are less accurate in less opaque material. Next slide, please. So we model frequency-dependent data like opacities with the multi-group approximation. This approximation represents opacities as a histogram in a set of fixed frequency ranges called groups. We use about 200 groups so we can attempt to resolve opacity features like absorption lines. Next slide, please. So we're using Monte Carlo in asteroid simulations because it has better accuracy in vacuum than SN in diffusion, and it models Compton scattering angular behavior more accurately. We mitigate the statistical noise by using many particles, and we mitigate the slow computational speed by using many processors. So next slide, please. So one-dimensional simulations model a small part of the asteroid surface with very fine zones, and we can vary the angle of incidence of the radiation by changing the angle that the computational particles are created at. So these simulations let us look at the ingoing shock, the amount of ejected material, the amount of energy escaping the asteroid surface, the spectrum of the radiation escaping, etc., in great detail. Next slide, please. Two-dimensional simulations let us simulate the energy deposition and momentum coupling as a function of angle more realistically. So these simulations take much longer than one-dimensional simulations because they have many more zones and many more particles. So we do fewer of them. So these results model half of a 35-meter asteroid. The source is 1 kiloton, 85 meters from the surface. And in the plot on the left, you can see the matter temperature and the radiation temperature that results from this simulation. And in the plot on the right, you can see the photons coming from the source near the top of the simulation and re-radiated photons coming out of the asteroid near the bottom. Next slide, please. So full radiation hydrodynamics simulations are useful for characterizing the impact of different physics on asteroid deflections. Because of their computational expense, these calculations are being used to attempt to parameterize the energy deposition for use in hydrodynamics only simulations, which are much more rapid. And for more information on that, you can see the talk by Mary Berkey and the poster by Kirsten Howley later today. Thank you very much.
Okay, thank you very much. So we have now the floor open for questions. So we had 5 fantastic talks. So I already have a few questions that were asked on the chat, but they were also answered apparently, but I will still take some of them because I think for all the participants, maybe they don't look at the chat. So there was one that was not answered is maybe for Sabina and Luther, what could be the principle for the selection of target materials for experiments? So you showed some confrontation with experiments, but of course the parameter space is very wide. So do you have any suggestions for experiments to define some new material properties that we could test with the simulations?
I can start answering that. So ideally, we would have some material from Ryugu or Bennu that we can impact, but probably no one else would be very happy about that.
Yeah, and plus there may be small size, but
yeah. So far we mostly used sand and regolith simulant as analog materials. Whether these are the best analogs for an asteroid surface, that is probably not that well known, and especially that we don't really know what the material on Dimorphos is going to be like. But the idea is to have a material that is weak. If it's cohesionless, then we have to take care because experiments on Earth will happen in the gravity regime rather than in a strain regime. Yeah, and then if it's in terms of boulders, then we just read every single paper that comes out on the boulders on Ryugu and Bennu and see what is more similar to that.
Mm-hmm. There are also some meteorites that are used. Somebody like George Flynn made also some experiments on meteorites. So, I mean, basically, maybe everything is possible, but I think what maybe we should say that it's also important to characterize well the material properties before the impact, so that for the numerical code, we don't have too many free parameters to assume initial properties.
Exactly. I would have added this, and I think maybe one interesting point is also how is the porosity compaction behaving. So what I mean, porosity is one parameter, but in our models we have more parameters to represent compaction.
Yeah. So there was another question about the porosity at which ICEL and ICEL and SPH made comparison with various porosities. And then for the beta factor, there was a switch in the trend, like ICEL and SPH switched for which code would predict higher values. So can you comment that? Do you have an explanation for that? And are they the same porosity model that were used?
So ICEL and SPH have 2 different porosity models. ICEL has the epsilon alpha model, strain-based, and SPH uses the P alpha model, so based on the pressure. And I should add that in the first plots that I've shown, we tried to very much align the parameters between ICEL and SPH, while for the benchmarking, where you have all the different porosities, it was a bit more free still that was just more focusing on the DART scenario, and we chose also the materials in a way based on porosity, but not, as I said, we have more parameters behind, not exactly on all the porosity model parameters. So I think we can do some more alignment here, and probably we get a better fit here.
Mm-hmm. Yeah, if I can add a bit to that. Sure. So in ICEL, we used, when we modeled the porosity, we used basically the compaction curve was also changed with the strength and with the porosity. And while this was also done in SPH, it might have not been done exactly the same. way. So that might also lead in some differences. And in the future, we'll try to align the parameters more to see if we can take these differences down if very similar parameters would be used.
And regarding the material property, there is a comment that it would be interesting to see impacts on power law distributed grains, like talc plus sand, etc., and see the effect of the power law. So that's also effectively an interesting study to see on a regolith with a power law size, see how it works. Then I have another question, but I think it was answered in the chat, but I can still say it because that will probably prepare to a future talk about the nuclear deflection. So the question was for Nicholas, can we infer how much of the target asteroid mass escapes as gas or fine dust or as chunks, and how much stays bound as slow ejecta or very slowly escaping coma or is redistributed? And also about the scaling laws regarding asteroid size and nuclear deflection yield. You have a comment on that?
Only that I think that Mary Berkey's talk's going to give more information on that.
Okay. So
yeah, basically, we do know the velocity of every zone in the thing, and we also have some estimate of whether that material's melted or not, and can eventually escape. So, so we can do it.
Okay, so please stay for the next session about deflection and disruption, where Mary Berkey will present that. That's good. I have a question for, I think it was Patrick, who was talking about the n-body method for following the fragments. So what was the fragment size you considered? Did you consider very small ones or large ones? And if you consider small one, do you count for solar radiation pressure, etc.?
So the fragment sizes that we employed, we actually split the mass of the impactor that we adopted into a set of equally sized fragments. We have run studies where we've done power law distributions of masses, and those, as far as the orbital dynamics are concerned, don't particularly change the impact fraction curve, although they do add what might be perceived as noise to those curves, as the different sizes of the fragments kind of make them a little bit more jagged. But the general behavior is pretty similar. We don't use a tremendous number of them. Part of that is because we're a little handicapped, not too badly, by the n-squared scaling of the n-body code. So for speed and to get a general understanding of the impact fraction down to sort of like a part in 1,000, we use 1,000 fragments. We can run an unlimited number. That's a parameter we set in the code. So to resolve that a little bit further down, we can use a larger number. In terms of the other effects like solar radiation or other non-gravitational or even tidal forces, we don't include that. We don't include any of the radiation terms, but including that in future versions of our code of our version of Spheral might not be too difficult. So hopefully we can account for those effects as well.
Okay, yeah, it's work in progress. Okay, thank you. I have also a question for Ryota about the shape change due to fast rotation. You answered in the chat, but it will be good to discuss that because that's also very interesting. So you may get basically a size increase at the equator due to the shape change, and therefore that may trigger mass escape if the speed rate remain the same. So what do you think about that idea? Because I think you did not consider that.
Yeah, so basically what we consider is have the shape, fix the shape, and then modify the shape. And that is almost equivalent to have increased the size of the equator region. And we did not take into account the mass loss event, but maybe it may be interesting to take into account that. Yeah.
Yeah, that could be effectively very interesting because it could be very unstable.
Yeah,
okay.
But at the same time, it's going to be a little bit tricky to model all of the particles trajectory inside Peabody system. Yeah.
Okay, very good. Any other question? Maybe some. I saw a hand raised by Alain Eric. I don't know if it's a mistake or not. Oh, you removed the hand, so it was a mistake. That happens. So is there any other question for our speakers? Maybe I see one. Yeah, that's for Nicolas. So were there any special considerations of radiation relevant parameters in the Lagrangian mesh motion aspect of your hydrodynamic simulations?
What do you mean by radiation relevant parameters?
That's, since it's not my question, I cannot tell you what it means.
Okay, well, I guess I'll say the radiation couples energy and momentum into the hydro equations. That you know, and that affects the well, that affects the motion of the material. The mesh, there's no imposed mesh motion other than the material velocity in a Lagrangian code, like there is in a in an Ale code. So so I think the answer to your question is, you know, there are terms in the hydro equation that come from energy and momentum deposition for the radiation, and we believe we are correctly simulating those. I hope that answers it.
Apparently it does, and I'm happy to know you think you simulate correctly. Okay, and the final question, because then we'll have to move on, is did anyone look at different zones of compaction as was seen during the small Caroni impactor experiment on Hayabusa 2? So I think that's more for the impact modelers, I mean the classical impact modelers. Sabina or Robert?
So we are working on modeling also heterogeneities. I'm not sure what is meant with different zones of compaction here. Is it?
I'm not sure either.
Same material, but
do you see some region where the material is compacted, basically?
Okay, and in a different amount, let's say. So in one part it's more compacted than the other.
Yeah.
I mean, of course, we see changes in density in our models, but I mean the SCI impact, of course, is a complex one. Yeah, it's not so symmetric, so you need the 3D models to really fully simulate it. I think Martin Yutzi was also doing a lot of modeling on that.
Yeah, there is work in progress on that, we could say.
Yeah, so far we looked at porosity gradients that they only change in the as a gradient in 2D rather than in 3D. But yeah.
Okay. Well, there is work in progress about that, so we can report in a future meeting.
We're going to begin now session 8, the first part, part A. The second part is going to be later this evening. It's going to be moderated by my colleague George Varadakis of the Aerospace Corporation, and then me, Marco Tantardini. We have 5 great talks. Since we are in the third day, we all know now quite well the rules. So we have 8 minutes. At the 7th minute, we will call the time. At the end, there's going to be Q&A. So we start now with the first speaker, Dr. Yuri Wang of the Chinese Academy of Sciences. The floor is yours.
Thanks for your introduction. And where is, oh, okay. Thank you. Can you hear me?
Yes, we do.
Can you hear me? Okay.
Yeah.
Okay, thank you. Hello, everyone. My name is Yuri Wang. I'm a PhD student from Chinese Academy of Sciences, National Space Science Center. And today I would like to introduce a new concept of asteroid meditation strategy. And today my speech topic is assembled kinetic impactor for deflecting asteroid via combining spacecraft with launch vehicle upper stage. And the next slide, please. Here is the outline of my presentation. And first, I will introduce the research background, explain the reasons of why we propose the concept of assembled kinetic impactor, and then the corresponding simulation method and simulation results are given. The technical feasibility of AKI is preliminarily discussed. At last, there is a brief conclusion. Next slide, please. Oh, okay. Asteroid impacts poses a major threat to all life on the Earth. Several serious impact events, like the KT events and Tunguska events and Charlia events, have aroused the people's attention to the planetary defense. Next slide, please. Planetary defense is to use active method to destroy the structure of the asteroid or to deflect the orbits of the asteroid. Among these, the kinetic impactor is the most feasible method, but actually not efficient for large asteroid in short running time. Next slide, please. Although the kinetic impactor strategy is currently the most feasible method to deflect asteroid, the constraints of the launch capability have resulted in a limited deflection efficiency. The previous simulation results show that in order to deflect Bennu for 1.4 Earth radius, at least 75 Delta-IV heavy launch vehicles are needed with a 10 years launch lead time. Such a large number of launches will significantly increase the risk of the failure of the asteroid deflection missions. Many studies have been performed to improve the deflection efficiency of the kinetic impactor strategy. For example, each reversal orbit concept can greatly increase the impact velocity to around 100 kilometers per second, but a great impact velocity makes the terminal guidance more difficult. Next slide, please. For general space mission, the spacecraft rocket separation is performed after the launch vehicle upper stage is sending the spacecraft in the nominal orbits. The reason for the separation is that the upper stage will become useless after the spacecraft enters the nominal orbits. However, for special missions such as the kinetic impactor missions, the upper stage will not become useless. That's to say, the upper stage can be used as a payload to improve the mass of the impactor, thereby improve the deflector efficiency of the kinetic impactor strategy. For example, as for the Long March 5, which is currently the most powerful launch vehicle in China, its launch performance is similar to Delta-IV heavy launch vehicle. The dry mass of the launch vehicle, the dry mass of the Long March 5 upper stage is about 6.5 tons. Next, please. To demonstrate the power of this concept, here we compare the assembled kinetic impactor, which we call the AKI, with the classic kinetic impactor, which we call the CKI. We compare the deflection performance in a 10-year launch lead time scenarios in two objective functions. First is the maximum deflection distance of a single impactor, and the second is the minimum number of launches of 1.4 Earth radius deflection distance. And as for the dynamic model, we consider the gravity of Sun, the gravity of 8 planets and Moon, general relativity effect, and solar radiation pressure and Yarkovsky effect. As for the impact model, we assume the beta factor equals to 1. And next, please. For the optimization method, we combine in the global optimization and local optimization, which includes the genetic algorithm and sequential prophetic programming. Next, please. We choose the Bennu as the deflection object, which has a diameter of 492 meters. The launch vehicle we choose the Long March 5, of which the dry mass of upper stage is about 6.5 tons. Next, please. Okay, for the first objective function, the maximum deflection distance of a single impactor, from the simulation results, we found that compared with the CKI, the addition of the upper stage mass can increase the deflection distance to more than 3 times. And next, please. For the objective function of minimum number of launches of 1.4 Earth radius deflection distance, the simulation results show that compared with the CKI, the addition of the upper stage mass can reduce the required number of launches from 79 to 23 for the Long March 5. Next, please. And furthermore, we discussed the deflection performance of 140-meter diameter asteroid with a 10-year launch lead time. The simulation results show that a single CKI can't achieve a deflection distance of 1 Earth radius, which cannot eliminate the threat of the asteroid impact. A single AKI can achieve a deflection distance of more than 2 Earth radius. Next, please. Okay, after the spacecraft and the upper stage are assembled, there are several new technical challenges we have to face. And here I list 3 of them in this slide. And first, we have to avoid the coupling of the attitude control and orbit control. And the center of the mass of the AKI is located on the upper stage. And at the same time, we need to prevent the threat prompts from affecting the solar arrays and upper stage.
1 minute.
Actually, the ideas of using launch vehicle final upper stage has demonstrated by the LAPRAS mission. And according to the BAO requirement, and AKI platform is preliminary design. And here I list the 2 diagrams of the thrust distributions and the thrust plums analysis. Next, please. And here is a brief conclusion. The AKI is a proposed animation of deflecting Benoit design to demonstrate the power of AKI concept based on the technical data of the Long March 5 launch vehicle. Compared with the classic connecting impactor, we found that the AKI concept can greatly improve the deflection efficiency and at the same time reduce the launch cost. Next, please. Okay, that's all. Thanks for your attention. And here is my email address. And if you have any question, feel free to connect with me. Thank you. Thank you very much.
Thank you very much. The second presentation is given by Dr. Alain Eric of the University of Grenoble, who's going to talk about Jura, the Juventus radar on Hera.
Thank you. Thank you. Next slide, please. I think I'm not going to present Hera mission, which is well known in this meeting. Next slide. On the Hera mission, you have a Juventus CubeSat, 2 CubeSat. One is a Juventus CubeSat, which is developed by GomSpace. Next slide. And I'm going to speak about the radar on board Juventus, Jura, which is one of the main instruments on board this platform. And you can see in this artist view the 4 booms corresponding to the cross dipole antenna of our instrument. Next slide. Okay, in terms of objectives, the question we are addressing is the question of the internal structure of asteroid. In fact, it's very important to have direct measurement of internal structure for science and for spacecraft interaction with an asteroid. For science, it's the way to have more constraints on the physical modeling we can do in terms of mechanical and thermal evolution of such kind of body, and especially validate the structure aggregate and better characterize this structure in terms of stability conditions, the question of the binary formation, but also for the regolith to estimate, to model the origin of the regolith and to determine mechanical and thermal properties. For any spacecraft interaction with an asteroid, we need to have such kind of information, especially for planetary defense, if we are speaking about a deflection mission. And the radar is one of the main instruments to do that, to have a characterization of the heterogeneity, the size of the constitutive blocks typically, from a metric scale to a global scale. Next slide. Is the goal of our instrument. It's a monostatic radar. That means we are using the same antenna to transmit and then to receive the signal reflected, diffracted by the surface of and the volume of the asteroid. It's a low frequency radar at 60 megahertz in order to be able to penetrate the structure, and with 20 megahertz bandwidth in the nominal mode. That means a resolution in the range of 10 to 15 meters. The radar is operating in full linear mode. We are transmitting one linear polarization, receiving two linears, and after the other one, I'm receiving two linears. In terms of data processing, we are going to extract circular polarization, usually done for planetary observations. During the mission in 2027, we are going to have 2 months of operation. First, with a 3-kilometer radius terminator orbit, that means an orbit perpendicular to the direction of the sun for stability reasons. And another month at 2 kilometers, that means flying relatively close to the moonlet. The transmitted power is 6 watts. That means we have at the end a sensitivity in the range of minus 40 dB meter square per meter square for radar speaking people. Next slide. What we are measuring with the radar, in fact, we are measuring the reflected power, the power backscattered by the surface and the interior of the body, and we are going to have a penetration of several tens of meters. It's difficult to say that if we are going to have a penetration of the whole body. That means if we are able to detect an echo coming from the other side. In fact, it's going to depend of the size of the level of scattering. That means the size of the constitutive material and the size of the blocks. If we are blocks and void at the scale of the wavelengths, at metric scale, a large majority of blocks at this scale and void at this scale, we are going to have a large scattering. It's difficult to imagine to have a full penetration throughout the body. With one measurement, we are measuring the signal received as a function of the time. That means we have only one dimension. And to be able to have an image, we have to have an arc of orbits. It's the main difference by regard to an optical observation typically. We need to have a long orbit if we want to be able to rebuild a 2D image. And if we want to go in the 3D direction, to have a 3D tomography, we need several sequences of operation. Next slide. In other words, with only one sequence of operation, we have a 2D image mixing in the same pixel information coming from the surface and from the subsurface. It's important because it's possible with a photo interpretation approach to detect, to identify some subsurface features in this 2D image by comparison with optical image typically. If radar wave penetrates the whole moonlet, as I said, we don't know it. We have some doubts. In this case, it's possible, including with one sequence of observation, to have a direct estimation of the permittivity, of the average electric permittivity, which is very important in terms of estimation of the composition and also estimation of the porosity, the macro porosity on the micro porosity. With a multipass acquisition, we can go in the 2D tomography way. That means rebuild the 3D image of the internal structure of the body. Next slide. In fact, typically we estimate that we need more than 20 revisits of the same area with different geometry to be able to go in the direction of the 3D tomography. And you have in this map of the moonlet the number of revisits we can have in during the sequence of measurement. And as you can see, we have more than 20, more than 30 sequences per on the main part of the body. That means we can expect to have a 3D tomography for the main part of the body. The blue part corresponds to the part facing the main body. That means having in the shadow of the main for some observation. Next slide. In terms of science objective, to go in the direction of the matrix, of the science traceability matrix, we are measuring a backscattering coefficient. That means the reflected power, which is related to the heterogeneity. And our first objective is to study, to image the interior of the moonlet in terms of to identify large structure, voids, layer of subaggregate, and also to bring out the fact that it's an aggregate structure and characterize this aggregate in terms of size distribution of the material. Next slide. The second objective is to estimate the permittivity of the moonlet in the full tomography approach, to have information on the composition and on the porosity. Next slide.
Let's try to wrap it up.
The secondary objective, yes, I'm finishing. The secondary objective is the same for the main, because we are imaging in the same acquisition the main, at least a part of the main, and the moonlet, and we are going to do the same processing for the main. Next slide. And to conclude, we are going to deliver in September the EM model, and it will follow by the QM and the fly model November 22. That means we are on the road of the integration. Thank you.
Thank you very much. Now we have the third presentation by Giampiero Di Girolamo of the European Space Agency. The title of the presentation is ESA's Planetary Defense Neo Coordination Center DevOps Model-Based Operations. The floor is yours. Thank you very much.
Good afternoon, everyone. I'm Giampiero Di Girolamo from the European Space Agency. Okay, we can go to the next slide, which gives the outline of the presentation. It will take less to dive into the presentation itself. I'm going to show the ground segment diversity in the NEO planetary defense environment, the operation activity, the different operation activity, the teams, and I'll talk about the infrastructure which is supporting, which is really driving and leading the mindset change we embarked a few years ago, embracing the DevOps approach, and giving some results in the conclusion of the presentation. Next slide, please. So the planetary defense operational pillars are three vertical pillars where there are different types of operations. So this is already introducing diversity. And the three vertical pillars are also supported by the planetary defense ground segment infrastructure, which complements the demands and also the competence of the very high specialized NEO operators, giving the engineering, development, validation, deployment of the various hardware and software components. This presentation will focus more on the software. Next slide, please. This is a view to give you already a differentiation of the different operation. ESA is cooperating with the major NEO stakeholders around the world, academic institutes, minor planet center. So there is a lot of interfacing. What does it mean in terms of software management demands? We have to manage different software development done in many locations. In some cases, we have only service level agreement to share data with external entities, with our partners. And we do have also operational consultancy with external scientists. So this is already the first differentiation. Next slide, please. Other differentiation is coming from the type of software that we develop. We have, for example, a big software component which we must, it is more efficient to outsource to industry, and they have quite a long turnaround time because these are big components. Next slide, please. On the other end, in our NEO Coordination Center premises, we do have the need to manage, to design, develop, and use small microservices, agile, in-house software development and data pipelines, which we have to do on site in order to complement the outcome of the big software that I showed in the previous slide. So let's move on. Let's go to the next slide. Okay, this is the full ecosystem, which is not worth to be detailed because it's too much, it will take too much time. Next slide. So the different teams, roles, and location. This picture shows the traditional development approach. We do have development, the outcome of the development is handed over to the build, test, and integration team, which does the validation, and then is handed over to operation. What is the big change that we need to face? Next slide. Is the fact that the contributor to all these key and straightforward phases are all dislocated and are also in different contracts. So it is extremely complicated to do this in our heterogeneous environment. Next slide. So this is why we went towards a working model which is known as DevOps, which fuses the development, the testing, the integration, and the operation. Next slide. There is not an academic look map of any type of environment which how we have to change to match to the DevOps approach. What we've done is an analysis of our needs, and that's why we identify all the different peculiarities. So we have long and short procurement, long software development and very short software development. We have high team dislocation outside ESA, inside ESA. So we need to have one infrastructure which is capable to have all these contributors which you see in each of these bubbles to be supported by the same infrastructure. And this is what brings us to the next slide. The continuous integration, continuous delivery in infrastructure. What is that? Because I understand that this is quite different from the presentation you've seen in this conference. This is an infrastructure which allow us to automate in a controlled way all the software delivery, integration, testing, and final deployment. Next slide. So this shows how we do automate this process. So all these steps, the build, the unit test, the static test, the deployment, the dynamic functional test, the artifact hosting, the monitoring, are all controlled via the continuous integration, continuous delivery infrastructure, where basically together with the software, we do manage also the pipeline which are delivered together with the software in order to have all this run in a controlled, automated way. What is the benefits of this? The benefits of this, to be shared with you today, is the fact that we bring down from 200 hours, 150 hours per delivery, the time to deliver, to a few seconds, a few minutes. Then all the rest of the time, which does not change, is the time we spend in doing the functional test, because that cannot be automated or full automated. Next slide, please. Next slide. Okay, this is the quadrant which maps what DevOps means within the NEO Coordination Center team. We need to, on the y-axis, we need to combine NEO high specialized experience with the computer science experience. On the lower part, we have to combine the development expertise up to the operational expertise, and then below there is also the testing. Next slide, please. There is not a chemical, there is a chemical solution in order to understand what is the proper balance within an operational team. the solution is always like, if you would have all the people, if, for example, in the right upper box, where, so NEO high specialized people, high specialized only in operation, of course, we would not be capable to support all the operation. So the solution is the diversity, to cover all the different expertise and level of NEO and computer science development and operation within each of these boxes. So the more you scatter around in this quadrant, the better chemistry you get. Next slide, please. Okay, these are how these are. It looks like a sky tessellation. It is not. This is the dashboard which allow us to control in an efficient way how the automation of the software delivery processes is ongoing. Next slide, please. Next. We go to the conclusion. So this is the DevOps vision as the previous one, please. This is how all this evolution has been is seen by the operators, so those which have the high new expertise. The keywords are continuous monitoring. These allow us to troubleshoot, immediate intervene in case of error. The NEO team is actively involved in the software process, not just waiting weeks in order to get a delivery. So they are they team up and work from the early phases of the software development. The pipelines, the continuous integration pipelines, tend to eliminate all barriers and facilitate the cooperation between the two, the team. We do have automatic control, and this guarantees also configuration. So basically, we simplify the development, the testing, the operation, despite the fact that we are building up a more complex system every month.
Let's try to wrap up.
Say again?
Yeah, time is over.
Wrap it up.
Yeah, okay, let's go to the conclusion. So we are running a new operation under evolved agile and control work processes. Despite the fact that the system is continuously increasing, we are capable to support the increase without having to invest too much in we don't have a linear increase of software support in order to face the, you can go to the last one, in order to face how the system is growing. Basically, this continuous integration infrastructure allow us to support this growth. Last one.
Thank you very much. Yeah, time is over. Apologize.
Okay.
So maybe at the end there's going to be Q&A, and so we will be able to expand on this. So thank you so much for your presentation. Now we move to the fourth one. We welcome Professor Paolo Tortora of University of Bologna, and this talk is titled here, Radio Science Experiments through Ground-Based and Satellite-to-Satellite Doppler Tracking. Please.
Yes, good morning, everybody, or good afternoon, wherever you are in the world. It's a pleasure for me to present this work. My name is Paolo Tortora, and I'm presenting this on behalf also of my colleagues from the HERA Radio Science Instrument team, plus the HERA Mission Technical and Scientific Management, which is also acknowledged here. Next slide, please. So you all know which are the elements of the IDA mission, so I will not get into the details of this slide, which is well known to most of the audience. I just wanted to highlight that for the experiment I'm going to describe now, the two basic elements are HERA, the mothercraft, which will also carry two CubeSats to the Didymos system, and Juventus. So these are the two elements which I will focus on to describe the HERA radio science experiment, in particular the gravity science experiment, which is carried out by these elements. Next slide, please. So that's the description of the HERA gravity science experiment. The two main objectives are the measurements of the asteroid gravity to constrain the interior structure, and the characterization of the post-impact mutual orbit and rotational states. So today we will focus on the first, gravity, and the measurements which we assume to have for our measurements are the ranging and Doppler, so the main link going from the ground on Earth the ground station on Earth and Hera, so the mother craft. I would say these are the classical ranging and Doppler tracking signals. And then the intersatellite link, which is the one going from Hera to Juventus. This is a relatively new instrument which has been built by GomSpace, the same provider of the Juventus spacecraft. It will operate at S-band and has a high precision Doppler tracking capability, which should ensure a very high stability for the link, which will reflect in a very high precision measurement of the relative velocity between Hera and Juventus. You can go to the next slide, please. So we carried out numerical simulation in order to make an assessment as precise as possible of the expected and achievable accuracy that we can get through the real experiment, which will be carried out after 2026, when the Hera and the CubeSat will arrive to the Didymos system. So the simulated scenario has Hera plus Juventus with Doppler data. And as I said, we simulated both the range and Doppler between Hera and the Earth, and range and Doppler between Hera and Juventus. And the duration of the experiment so far, at least what has been simulated, you see the acronyms of these phases in the box in the right bottom part of this slide, is the detailed characterization phase, DCP, and the close observation phase, COP. So we have a total of about 2.5 months for the simulations. You can go to next slide. So this is a description on how we simulated the concept of operation. So our CONOPS starts from the simulation of the trajectory of Hera, which has these hyperbolic arcs connected by impulsive maneuvers. This is a kind of a Rosetta-like trajectory control concept. All trajectory arcs have been simulated and to be used for radio science, and we also assume to have no thruster maneuvers during the arcs. So basically, all the wheel offloading maneuvers plus trajectory adjustment maneuvers are to be done outside of these arcs. And in terms of timeline for each single arc, and by arc I mean, of course, the one connecting two vertex of these triangles. You see in the bottom part of this chart how we simulated the single arc timeline. Basically, we have Doppler tracking on the wings, where we can do it without disturbing any other observations. And then for some specific arcs, we also assume to have Doppler when we are at closest approach, depending, of course, on the operation of the other instruments. So in this case, not all arcs have been simulated with Doppler at closest approach. For the other parts of the timeline, we assume to have optical images, which enhance significantly also the simulation and the results that we can get from the gravity science experiment on Hera. And as you see here in this chart close to the plot, the minimum distance is in the order of 10 kilometers and the maximum is in the order of 23 kilometers. Next chart, please. So here we see the simulation that were carried out, basically doing some parametric studies. So we simulated different capabilities in terms of having tracking between Hera and the CubeSat. We simulated different duty cycles just to check which is the effect on the total accuracy that we can get, going for 20%, which is basically 1 minute every 5 minutes of tracking, and up to 80%, which means 4 minutes of Doppler tracking out of a total of 5 minutes. And you see also here the level of noise that we are assuming on our simulations. Next, please. So I will show you some results here, which is the output of our simulation. Basically, the dimorphous mass, which is one of the basic elements needed by the mission in terms of scientific objectives. We have an accuracy which goes between 0.1% up to 0.05. So this is a quite remarkable result depending on the duty cycle. Next chart. Here, this is the result for Dimorphos J2. Let me also stress that this result cannot be achieved with the HERA only. So if we do simply ground-based tracking, we don't have any access to J2 of Dimorphos. In this case, depending on the duty cycle, we can get to accuracies which are close to 10%, in particular between 10 and 11% for all cases. Next chart, please. Now we focus on the Didymos gravity field. Yes, we focus on the Didymos gravity field. In particular, this is probably the most interesting result that we can get by combining the ISL, the intersatellite ring ranging, and Doppler, plus images, plus, of course, the standard ground-based HERA Doppler tracking. And as you see here, the y-axis shows the RMS of the gravity field which can be observed. And the x-axis shows the degree of the gravity field. The black line is the simulated gravity field, and the other lines with the very same color code as before show how accurate the solution can be. So of course, when we cross one line with the other, it means that the error becomes as large as the simulated gravity field. So we no longer have observability. So basically, we can say from this chart that we can get safely up to degree 3 of the gravity field, and above it will lose observability. Next chart, please. Okay, so that's a summary of my talk. We proved the feasibility of the HERA gravity science experiment using realistic assumptions for the technological capabilities and the trajectory. We saw which kind of results we can get in terms of Didymos maximum observable degree for the gravity field and the Dimorphos mass and J2. And this is a kind of a roadmap of our short-term to-do list, which we are working on. The simulation with the detailed operational constraints, add the other CubeSat, which will be carried out by HERA within the scenario. We know that Milani will be quite far away from the system, so at least farther away from the system than Juventa, so it will likely not add much. But of course, we are intending to add it to the simulations. And then, of course, improve the modeling of the Didymos system, which is still far from being complete. So that's all from my side. Thanks a lot for your attention.
Thank you very much. Now we have the fifth and last presentation for this first half of the mission and campaign design session. It's given by Dr. Albert Falke from Airbus. The title is Hijacking a Satellite for Short Warning Asteroid Deflection.
Many thanks for the introduction, Marco, and hello, everybody. So as just introduced, I will present the shortcomings and results of our hijacking a satellite for short warning asteroid deflection study we did for ESA. On the next slide, I will directly jump into the topic. Imagine an asteroid threat scenario where the asteroid threat is just discovered in order to impact Earth in a time frame of 1 to 3 years from now. And what do we need to prepare or already have prepared in order to enable our deflection capabilities for short warning asteroid threats? So this is the question of all questions in that scenario. Our key objective was to assess the feasibility of modifying a commercial spacecraft platform in order to perform kinetic deflection in the shortest possible time, meaning a driving requirement for launch readiness within 6 months from the threat discovery. On the next slide, you see on the hijacking scenario timeline, we will focus on the left side or the beginning side of the scenario, starting at the asteroid discovery until the launch campaign. We have foreseen a very short political decision timeframe of about 1 month. And once this has been completed, the approach foreseen is to hijack an existing commercial platform, which is already inbuilt in the integration facilities, and with minimal adaptations and additions, convert this spacecraft into a kinetic deflection mission. So you can imagine that the time frame for adaptations and additions is rather short, and we expected this to be in the order of 2 to 4 months maximum. On the next slide, you see some shortcomings from the mission analysis. We revealed the deflection needs for realistic asteroid threat scenarios, meaning smaller asteroids in the order of 20 to 80 meters in diameter. In this context, we found out that the deflection performance primarily depends on the early deflection, the impact impulse itself, and the relative Earth-asteroid geometry. Moreover, higher allowed solar phase angles is very beneficial for the deflection performance, and it as well increases the number of available deflection trajectories. Higher solar phase angles require a navigation camera system independent from the visual light, so that you can, with an infrared detector, for instance, approach the asteroid from the not so well illuminated side and increase thereby the deflection performance. So this is one of the important outcomes that we would benefit from an available thermal infrared-based camera system in order to support the targeting. From the mission analysis, we took 5 representative scenarios and started to provide a generic or enveloping system design, which is then shown on the next slide. Here you see on the illustration on the right-hand side, the telecoms platform payload module in green and the service module in brown. Both parts can be broadly used as is, and they only require small modifications and changes. The largest ones are for the communications payload, which can be removed, as well as substantial modifications need to be performed for the onboard software and the propulsion system, of course. Next to this, we need to add a kinetic deflection module. Sorry, the previous slide, please. The kinetic deflection module, this is depicted here in gray. That's something we need to add to this satellite stack. The kinetic deflection module brings then the unique parts which needs to be there for a kinetic deflection mission, meaning the deep space communication system, for instance, and most importantly, the guidance, navigation, and control system supporting the proper targeting to the asteroid. This kinetic deflection module is a prerequisite which needs to be available right from the beginning of the, let's say, emergency situation. So this is an important activity which needs to be done well in advance. On the next slide, I will spend a few words on the GNC subsystem. Within our earlier study, NeoShield 2, we were able to develop tools and a complete kinetic impactor GNC subsystem, and we were able to validate it up to TRL 5 to 6. Based on these achievements, we applied some modifications for the repurposed telecom platform to comply with these hardware specifications. This means the thruster configuration and type had to be updated, and some further changes had been applied. Based on this, we were able to successfully demonstrate the targeting performance, which you see depicted here for the worst case scenario. The blue crosses in the image indicate the simulated impact sites, which, as you can imagine, are very, or as you can see, are very close to the target center, the object center, and as well very well in line with the specification or the requirement illustrated by the green circle. Moreover, we performed a sizing activity for this narrow angle camera suite, including in particular the thermal infrared detector. And the outcomes here can and shall now be used in order to trigger the critical key technology developments, which must be understood as a long lead item, and therefore it's an important action to start. On the next slide, I'm coming to the conclusion. I can summarize that a fast kinetic deflection mission with a launch requirement of 6 months for short warning asteroid threats is feasible. We identified the prerequisites which are required therefore, and the modification activities to hijack and repurpose a commercial telecoms platform. We also provided a viable preliminary design solution and successfully demonstrated the GNC targeting performance. Both has been largely driven by the 6-month launch readiness requirement, and this requires quite a lot of pre-developments and prerequisites, namely the KD module. Next to this hijacking scenario, there are alternatives. As you can see on the table, the stored dedicated spacecraft on the left-hand side comes with even higher preparation efforts, but at the same time with the fastest launch readiness of about 1 month. At the other hand, the cherry-picking scenario comes with a longer preparation time or launch readiness time of 1 to 1.5 years, while it comes with very low preparation efforts, and this is very beneficial for our situation right now. So in this scenario, we only would need to start detailed design phases, AB1 phases, and to start the key technology developments. And in case of an emergency coming into play, this would then allow to reallocate any suitable hardware platform units from any integration facility in Europe, followed by a fast-track AIT to build and launch the kinetic impactor spacecraft. This only requires very explicit and extensively preparation phases. And this is our key recommendation to trigger and to start this preparation activities as soon as possible in order to establish a European asteroid deflection capability. So that's it from my side. On the next slide, I thank you for your attention, and I'm happy to take some questions later on.
Thank you very much. It's time for the Q&A session right now. We have a couple questions that were posted in the chat. First one for Yuriu. Had a question saying, did you consider the increased fragmentation risk of hitting a relatively small object like the Morpho or the 21 PDC with a much heavier impactor, say 10 times the mass of darts? Or is there a potentially small spacecraft solution that would increase the mass that would also result in a similar sort of effect?
Okay, thanks for your question. And okay, sorry. Yes, for the first question, I think is yes. And of course, the fragmentation risk analysis is very important. However, the work we did now is mainly focused on the demonstration of the power of our new concept of the kinetic impactor. And as for the scenarios that deflecting large asteroids in short running time, of course, we need to improve the mass of the impactor. And like the question that the fragmentation risk analysis, it involves several aspects like the generation of ejecta and the evolution of ejecta and so on. It needs more details about missions. This is a common problem needs to be solved, whether use the new kinetic impactor strategy or classic kinetic impactor. This part of the work is also the next part of our research, and which is mainly focusing on the feasibility of the concept, both of the technical feasibility and the post-meditation analysis. And for the second question, my answer, I think, is yes. And as for our concept, different from a general space mission, the upper stage in the kinetic impact mission can become a payload. As I said before, and the technical feasibility needs to further be discussed. Thank you.
All right, thank you. Next question is for Elaine. Could you explain the advantages and disadvantages of having a monostatic low frequency radar like Jura on an orbiting CubeSat versus a bistatic mode that you would have on AIM or Mascot 2?
Okay, just to explain, with a bistatic, we have a direct measurement of the propagation between the lander landed on the surface to the orbiter, or between two platforms, a CubeSat and a mother craft. And with a monostatic, you have a measurement of the reflected signal with only one platform. In fact, it's complementary measurement. With the bistatic, you are measuring the variation of the average permittivity, that means the average composition, and you have a measurement of you are more sensitive to the smooth variation of the composition and texture of the body. With the monostatic, you are more sensitive to the reflected signals, that means the interface, and the huge variation of the system. In fact, you have to consider as complementary measurement, and with the bistatic, you are limited to body with a size less than 1 kilometer, maybe 800 or 500, something in this range, is not relevant for big object. In fact, with Jura, we can operate both because the architecture is quite the same. We have just a problem of firmware to be modified. That means with the bistatic measurement, which is more demanding in terms of resources, you have to have a lander. You can operate with both instruments, with both mode, with the same instrument, and using the orbiter part to do monostatic. It's not a competition.
Okay, thank you for that. Albert, there are about 3 questions for you, but I'll start with the first one. If we have time, we'll get to the rest of them. How confident are you that the workforce which is needed for this activity will be available if your facility is located in the impact area?
Yeah, that's a good question, affecting several perspectives. So generally, the workforce will be available within Airbus, of course. We are a large company with many sites, and we can join the forces all together. But your question also points out that there might be some people which are going to flew from the impact area. And yeah, that's a question I can't really answer. But I would suggest that a lot of engineers are people which want to do something against a threat, and therefore I would trust in them to stay there and to support the activity to launch the deflection mission.
Okay, the next question that came up in the chat, also for Albert, could this hijacking that you were talking about be adapted to a nuclear mitigation for a larger object?
Technically, I think that's feasible. You should be prepared such nuclear device for the KD module, so to say, the module which you add on top of the commercial platform and which is already prepared before the emergency case. There are, of course, some political constraints. I think this is an open question, and yeah, that's let's say not a solution which can be solved on a technical discussion side.
That's true. Thank you. I had a question for Paulo, actually. You mentioned that to achieve 4th degree measurements with the satellite, you'd have to get fairly low altitude measurements. Did you do any analyses to figure out precisely how close or how low those altitudes would have to be, or how long you'd have to spend that close?
Yes, thanks for your question. The current altitude for Juventus is in the order of 2-something kilometers, so it's quite close, but not that close. We know that there will be a final phase for Juventus as well, where it will be getting closer to the Didymos system. So we know for sure that if the distance was in the order of 1.5 kilometers, with the very same duration, that's the only study we did, we could access the degree 4 for the gravity field. So, of course, as you know, the strength and the sensitivity to the acceleration goes with the square of the radius. So, of course, if you get closer, you get a much stronger signal from from the gravity field coefficients. So basically, with the same duration, 2.5 months, we should get at about 1.5 kilometers to get the degree 4. Of course, this could be traded with having a shorter distance with a smaller duration, as it is clear. I hope I answer your question.
Yes, thank you. We have a few minutes left, so there's one last question for Albert. With all the interfaces for such a big platform would probably have, could you add a couple of observation or data transfer sub-platforms like the CubeSat on board darts that they could be used to receive or store last second data and forward them back to Earth?
Yeah, yes, that's feasible. One CubeSat has already been foreseen in our study, which would monitor the impact and send the data back to Earth. And of course, there might be additional CubeSats added, which observe from different perspectives, for instance. The drawback is a bit that you reduce the impact mass, but perhaps this is not relevant, or not so much relevant because the CubeSat is not so heavy.
Would that potentially increase the timeline for readiness, though, with the number of CubeSats?
No, in that case, I would assume that the CubeSats need to be added to the prerequisite, the KD module in advance. So that's something which is already prepared and can be taken from the stock.
Okay, thank you.
Good morning, good afternoon, and good evening. I'm Nahum Melamed, co-chair of the 2021 International Academy of Astronautics Planetary Defense Conference. We are now continuing activities in what we call the Green Zone, the 3-hour block time designed to fit viewing schedules worldwide. We will start with an update of the very realistic but hypothetical asteroid threat exercise that was introduced on Monday and continued yesterday. Information presented in today's update will be deliberated by disaster response experts in the Disasters Managers Discussion Panel. Just after the panel discussion, Paul Chodas will present the final impact area. In the last panel of the day, heads of space agencies will discuss current activities that support planetary defense. So Inject3 advances the scenario timeline of the threat and gives the latest estimate of possible consequences of impact. The updated information will be provided by Paul Chodas, Director of NASA's Center for Near-Earth Object Studies, or CNEARS, Jet Propulsion Laboratory, and Lorian Wheeler, Risk Assessment Lead for the Asteroid Threat Assessment Project, NASA Ames Research Center. Take it away, Paul and Lorian.
Thank you, Nahum. Let me do my screen sharing here. Tell me what you see on the screen. Do you see the
yes
slides?
Yes.
And
yes.
Do I
hear you loud and clear?
Play swap displays?
Yes, swap displays.
Thank you. Okay.
Looks good.
Great. So here we have the inject number 3. The scenario has moved forward to June 30th of this year, 2021. So that's a couple months after the last inject. That's asteroid day, by the way. It is less than 4 months until impact. The headline we have from the IAWN is space-based infrared measurements enable improved prediction of asteroids' potential impact effects. Astronomers from around the world over the last 2 months have tracked 2021 PDC nearly every night using some of the world's largest telescopes, and that has enabled a significantly more accurate estimation of its orbit. So we have been able to predict the impact zone much more accurately than before. It's narrowed down considerably to mostly within Germany, Czech Republic, and Austria, which I'll show on the next slide. Importantly is the NEOWISE story, however, that little observatory that could, on its extended mission, observe the region of sky in which the asteroid passed. And that was in early June. It's a very narrow field of view, however. And that the asteroid 2021 PDC was not detected by NEOWISE. You heard yesterday when Joe Masiero talked about what NEOWISE could do in this regard. However, as he explained yesterday, their team changed their survey pattern to repeatedly scan the asteroid's predicted position for a period of 3 weeks, tracking that narrow field over where the asteroid would be. And then by combining the results of hundreds of exposures, they achieved a marginal detection of the asteroid. Their estimate for the diameter of 2021 PDC was 160 plus or minus 80 meters. Now, this result provides an important upper bound on the size of 2021 PDC, and that significantly reduces the worst case size and the corresponding worst case impact energies of the impact effects. That's my summary bottom line of the news of the day. You see the URL at the bottom of this screen. That URL should be live right now. The predicted impact region looks like this. We have 3 red contours, which are much narrower now than we saw yesterday. The probability that the impact point will be inside the outer contour is 99%, inside that middle red contour 87%, and inside the dark red contour 40%. That's a wide view of Europe with those contours, and this is a close-up of where those contours lie. Now, all I am dealing with here is where the impact itself occurs. Lorian, who speaks next, will talk about what the impact effects would be, which of course could be much broader because the damaged regions will extend for tens or even hundreds of kilometers around the actual impact point. I'll pass it now to Lorian for the discussion of the impact effects on day 3.
Thank you, Paul. I could share my screen.
Yes, you will be made the presenter.
All right. I don't think that's the right display.
Yeah. Okay.
There we go. Is that looking right?
Perfect.
Okay, great. All right, as Paul said, my name is Lorian Wheeler, and I work on the Asteroid Threat Assessment Project at NASA Ames Research Center, and I'm going to present the updated impact risk assessment for today's hypothetical impact scenario. So starting with our sort of snapshot overview of the current impact risks, given our new updated knowledge about the threat, the big difference between today's scenario and the day 1 scenario that we presented on Monday is that we've gone from the 5% impact probability with potential locations spanning the globe to now having a certain impact somewhere over Central Europe. Observational data have also reduced the maximum asteroid sizes a bit, as Paul mentioned, but the most significant factor here is the known impact region. This has changed our basic risk picture quite a bit from what we had on Monday, whereas previously we had a high chance of no damage paired with a small chance of extreme damage. We now have the opposite situation with a high likelihood of damage affecting large numbers of people. And of course, as Brent showed in his mission options talk yesterday, we don't have the on-demand launch resources to mitigate the object or get more recon data about it before the impact occurs in under 4 months. So now we are faced with a short warning emergency response situation in which we still have a large amount of uncertainty about the object size and potential damage ranges. So today we're going to look more at the potential local ground damage risk factors for disaster planning. And I introduced this more thoroughly in my first presentation, but here's a quick reminder of how we assess these impact threats. We use our probabilistic asteroid impact risk model to evaluate millions of cases representing the potential asteroid properties and impact locations. For each case, the entry and breakup is modeled to estimate airburst altitudes or surface impacts, and the resulting damage is then modeled for various hazards. For today's scenario, we are looking at just blast and thermal ground damage since our impact region is entirely over land now. And also the object is not large enough to expect larger scale global climatic effects. The number of people affected within the various damage regions is estimated from world population data, and results of all the cases are aggregated to determine the likelihood of different consequences. So for more specific information on each of these modeling factors, please do check out related PDC talks. I'll have references to those at the very end. So starting with an update on what we now know about the object. Now that we have a specific impact region, the entry parameters are also well known and don't vary significantly from place to place. The entry velocity is a little over 15 kilometers per second, and the entry angles are between 50 and 55 degrees. The asteroid size and properties, however, are still very uncertain, but we did infer a slight size refinement from the weak NEOWISE detection that Paul mentioned and that Joe Maciero presented yesterday. This eliminated the very largest low probability objects from the tails of the distributions and brought the maximum diameter down a good bit from 700 meters to now around 500 meters. And it brought the maximum energies down substantially from around 13 gigatons to now under 4 gigatons. However, the main size distributions remain similar to the previous estimates. Average sizes are now around 136 meters diameter, or coincidentally, also 136 megatons of energy. The distributions skew towards the smaller end, as I talked about more on Monday, with likelier ranges still falling around 100 meters or several tens of megatons. So overall, we have a little relief from the worst case maximums now, but we're still faced with a pretty broad range. Looking first at the total population risks, we now have a very high probability of affecting large numbers of people, likely in the range of hundreds of thousands. The average is around 580,000 people, and the maximum worst case modeled is up to 6.6 million. The histogram on the left shows the chance of affecting different ranges of people, with a more than 50% chance of affecting between 100,000 and 1 million people. The exceedance risk plot on the right shows the probability of affecting at least a given number of people or more. So you can see, for example, that there is now a 97% chance that the damage will affect at least 10,000 people on the lower end, and a 21% chance of affecting over 1 million people on the higher end. Fortunately, the worst case potential damage has also decreased by an order of magnitude compared to our initial globe spanning scenario on day one. And it's now down in the millions rather than the tens of millions that we had before. But unfortunately, we've also eliminated nearly all the cases that either sailed blissfully by the Earth or air burst harmlessly over the ocean. So as a result, the average affected population has increased by an order of magnitude compared to our last assessment. So now we know the overall odds are definitely not in our favor, and we've got a big disaster management problem on our hands. Now that we are dealing with disaster planning for an impending impact, we care much more about the specific local consequences. The potential affected population ranges, of course, depend on the population densities, which vary substantially even across our very small swath here. These plots show the average and maximum affected populations for each sampled entry point, given the range of asteroid properties and resulting damage. The averages on the left are between around 200,000 and 1.3 million people, with the highest average occurring for the entry point that approaches toward Prague on the very edge of the entry region. The maximums are in the range of several millions, with the single worst case occurring at the very northwestern tip of the entry region in Germany. It's interesting to note that both the highest and average maximum entry points for this scenario just happen to occur around the lower probability borders of the potential impact zone. But moving on, to figure out how to protect as many of these people as possible, we need to understand the size and severity of the potential damage areas around these points. But first off, here is a key to the ground damage levels that we will be looking at next in our damage regions. Our model evaluates both blast and thermal damage at 4 severity levels shown here, with each level affecting a certain fraction of the population within the region. The lowest outer level that we model is what we call our serious damage level, which is estimated to affect roughly 10% of the population in the region. For blast damage, this is defined by a 1 psi overpressure threshold, which could cause window breakage or other minor structural damage. We then have increasing severe and critical levels of damage affecting 30 and 60% of the population, up through unsurvivable blasts or incineration affecting 100% of the population. The various blast and thermal regions are independent of each other, and they're not generally the same size for a given case. So the larger of the two is used to define the combined damage severity area for each case. Blast tends to be the largest hazard for the cases in this scenario, as I talked more about on Monday. Same is still true today. Thermal damage can occur along with the blast damage, but it tends to be smaller and less severe than the accompanying blasts. So the damage zones we will be looking at today mostly represent the extent of the various blast levels, although the assessment does include both, and all 4 levels can be reported separately for each hazard type. So this damage map shows the full range of regions potentially at risk to the different damage severity levels. It covers all potential impact points in asteroid cases, including the very unlikely maximum sizes. Paul earlier showed the rings representing the probabilities of where the strike could occur, and this plot now shows the maximum potential extent of the damage regions extending out from each potential airburst or impact point. The risk region is around 1,400 kilometers long by around 700 kilometers wide, extending from the northern coast of Germany down to around Sarajevo. To be clear, not all of these areas are likely to be subject to the damage levels shown, but they could potentially be. Within the potential risk region, the actual damage area and location could vary widely. We could have anything ranging from very small areas with only the lowest damage levels, perhaps located over lower population areas, like the little point you see there with the arrow, to more typical or likely damage sizes, up through the very largest unlikely worst cases, and everything in between. So looking first at some more typical damage sizes, here we have the estimated average footprint sizes shown over several major cities within the swath. The average damage radii for the different severity levels range from around 10 kilometers for the highest unsurvivable level out to around 80 kilometers at the lower serious blast damage level. The range and likelihood of the different damage sizes is similar across the swath, since, as I mentioned, the entry parameters are similar everywhere. And the variation among the damage sizes is due mostly to the range of asteroid sizes and properties that affect its potential breakup or airburst, and all those varying factors. So now, everyone always wants to know about the worst case scenario, so here it is. Of all the 25 million potential cases that we modeled, the single worst case affecting the greatest number of people was this one here. It's a blast from a 400-meter diameter, 1.3 gigaton asteroid located at the very, very corner of the potential impact zone. The damage area extends over around 190,000 square kilometers of northern Germany and is estimated to affect around 6.6 million people. So this gives us another example of how the worst case extremes can be very unlikely and not necessarily a good representation of the outcomes. This case is both at the very edge of the impact uncertainty region, meaning it's much less likely than the more central points, and it's also in the unlikely large size range. Less than 1% of cases are over a gigaton of energy, or in terms of diameter, less than 0.1% are over 400 meters. But we're going to look at it anyway. So keeping the relative likelihood in mind, here we have a closer look at the damage region sizes for our worst case example. The blast damage radii for the different severity levels range from around 28 kilometers for the highest unsurvivable level out to around 250 kilometers for the serious damage level. The thermal damage regions for this case are much, much smaller, falling entirely within the unsurvivable blast zone. And I have not shown them here, and they only reach up to the second severity level. Now, what makes this the worst damage case is the number of people affected within the damage zones. There are roughly 45 million total people estimated within this entire damage region, around 6.6 million of which are estimated to be affected according to the different damage levels that I showed earlier. Here I've shown a breakdown of the affected populations for each damage severity from around 0.4 million people within the unsurvivable zone to nearly 4 million people affected in the serious blast damage zone. The key point here is not these specific numbers, but that the population risk is driven much more by the larger, less severe damage area than by the smaller but more severe damage areas. In other words, even though the lowest level is much more benign and affects only an estimated 10% of people, the area is so much larger that it affects more people overall than all the other levels combined, and in this case, 10 times more people than the unsurvivable level. Another important thing to note about our worst case here is that it is not centered over a high population city. Instead, it is centered in between the larger cities, such that the outer damage levels span multiple higher population regions. So when you envision the worst case scenario, keep in mind that it may not be a direct strike right over the biggest city in the region like you might expect. So now that we've entertained the dreaded worst case, we should remember that the very extremes are unlikely and also that they can be too large to realistically be completely evacuated. So in order to develop effective disaster response plans, we need to consider both the severity and likelihood of the potential outcomes, and then weigh those factors against realistic response capabilities. Here we have examples of the statistical range of damage sizes shown at a sample point near Vienna. The geographic scales and landmarks are a little hard to distinguish here in our lovely green mountains, but I've tried to enlarge a couple key cities here and there as reference points. The average and median damage regions are both around 80 kilometers in radius, significantly smaller than the largest possible region. The percentile sizes on the bottom row indicate the fraction of cases that are smaller than the regions that are shown. So for example, looking at the 75th percentile size, if you were able to evacuate or shelter a region out to 120 kilometers radius, you would have a 75% chance of covering at least as much area as needed and a 25% remaining chance that the actual damage may end up being larger. So for the hardcore disaster response planners who like statistical plots more than pretty bullseye pictures, here are the details of the damage radius probabilities for the outermost serious damage level, similar to the population risk plots I showed at the beginning. Again, the histogram on the left shows the relative likelihood of different damage ranges. So here, for example, we can see that the 20 to 60 kilometer ranges are more likely, comprising around 40% of cases. The exceedance plot on the right again shows the probability that the damage regions will be at least the given size or larger. So for example, here we have a 38% chance that the damage will exceed 100 kilometers, falling off to an 11% chance of exceeding 150 kilometers, and a 1% chance of exceeding 200 kilometers. So this gives us a more robust way of capturing risk of different damage sizes. For example, even though 40 kilometers is right in the middle of the most likely range that pops out on the histogram there is still an 80% chance that the damage could be larger than that when you consider the full range of possibilities. So expanding on that even further, we can also, of course, look at similar probability estimates for all the damage severity levels. Emergency response plans may want to consider these damage severities in determining how to evacuate or shelter different regions. For example, perhaps you might want to evacuate within just the critical radius and only advise people to board up windows and shelter in place within the serious damage region. Or perhaps you would want to consider the damage sensitivity of critical infrastructure within different regions. So to be perfectly clear, I don't have the expertise to say what levels of response are appropriate for these specific damage levels, but I did want to provide an example of the kind of risk information that disaster response agencies could use to determine the most effective strategies for their particular regions or capabilities. So now we can come up from air from the statistical information and sum up the main takeaways that we've learned about this threat. We know we need to prepare civil response plans for an impact in just 4 months, with large uncertainties remaining about the range of potential damage. Blast damage is the main hazard and could extend out tens to hundreds of kilometers around a large airburster impact. Damage severities could range from minor structural damage or burns to unsurvivable blasts or incineration. And in terms of the population risks, damage is likely to affect hundreds of thousands of people, potentially up to several million in the rare worst cases. The population risks are driven most by lower severity damage levels that cover larger areas. And finally, worst case locations could span multiple urban areas rather than centering directly over a single major city. So closing with a few more general notes about how risk assessment can support disaster planning for an impending uncertain impact scenario like this. Risk and damage assessments could continue with increasing fidelity as more information is gained about the incoming object. Risk modeling can provide rapid assessments that capture the uncertain ranges of outcomes for emergency response. These include probabilities of damage region sizes and severities to inform the most effective achievable civil response efforts. And damage region maps and ranges can be provided to local emergency response agencies for specific infrastructure or evacuation planning. Also, higher fidelity modeling and simulation can further refine specific damage estimates by providing more accurate modeling of impact effects for specific cases. Now, given that there are still a lot of remaining uncertainties about what the impact will be, risk models can continue to identify critical cases for these simulations to run. So that's a picture of what we know about the threat scenario and how we can start figuring out what to do about it. And again, I'm going to leave you with this slide referring you to more information in related PDC talks in the impact effects sessions, mostly, and a few other sessions. We have Mike Aftismus, who has information on the high fidelity blast modeling that's done for the PAIR model, and Ashley Coates talks about the thermal radiation, about tsunami modeling by Martha Berger, and a number of other. And of course, Jesse Dawson has the property inference model that I mentioned yesterday. So these references will all be up on the version of the slides that's on the impact effects. And that wraps it up from me.
Thank you, Paul and Lorian. Really fascinating set of information. We have maybe a couple of minutes for questions. So there is a question for you, Lorian. Can you clarify the meaning of affected in affected population? i.e., does it mean fatalities, injuries, something else?
Yeah, that's a nice little vagary we like to rely on. So it can be anything from affected by damage. This is why we have the different scale damage levels in our assessment. It's not necessarily casualties, but it's kind of represents a sort of vague notion of how a population may be affected either by lots of people having low damage levels or fewer people being actual casualties. And these are taken, these use the approach that was used in the science definition team report that was done in 2017, looking at how to optimize survey missions for planetary defense, and relies on a value of standard life sort of breakdown by the Department of Energy or Department of Transportation, I think.
Thank you. Yeah, there is a comment that this is an interesting communication issue. What does it mean to the public by saying affected? So I guess it's an ongoing debate. And also another point is that this is just a specific location. It could randomly happen anywhere in the world. So anybody could take those insights into its local area and project. So this is just an example case. And I don't see any other questions on the chat. It's mostly a good communication between the attendees. Okay, one more question that came up here. We'll have about 1 minute for it. How much additional impact location refinement is likely in the remaining 4 months?
So I think, yeah, that's more Paul's question.
Yeah. Yes, that's a good question. Yes, the asteroid will be tracked pretty well continuously for the remaining time until impact occurs in October. So the size of this impact region will slowly decrease, and it will get down to on the order of a few hundred kilometers in size. But the key thing and the key question, and we can anticipate this, is that when radar detects the object and when it becomes within range of the Goldstone radar, then we will be able to really shrink that prediction, and we'll know really locally where the impact will occur. So it will be a gradual process, and then when radar data becomes available, the predicted region will shrink to be a very small size. Stay tuned.
Thank you, Paul. There's a good comment from Detlef here, is that with proper preparation, nobody will be killed because we'll have time to respond. And so he recommends to use the word affected. It will be affected, but not necessarily killed.
And particularly getting ready for an asteroid impact event and how it's different from other emergencies. So we just got the IAWN, or the updated information from Lorian and Paul. And what I want to do this morning is have us discuss the detailed information on what the possible impact consequences in the region are, how you would plan for that, how you would talk to your manager about that. And some of the questions that I presented to my colleagues was like, how important is it for you to have one source of information? In this scenario, who would you go to for that information? Would you go to your primary space agency, or would you find some other source? What do you need to tell your decision makers? What do you want them to consider? An additional problem that we have this year is the fact that we're in a pandemic. Everybody's responding to a pandemic. How might that change what we might want to do to respond to this? And does it fit do you have existing plans that you can adapt? Here in the United States, we do have a National Near-Earth Object Preparedness Strategy and Action Plan. I helped write Goal 5, which is concerning alerting the emergency management personnel and what is the public messaging that's going to be with regard to responding to this emergency. And then give me your impact area, how it's looking now. It's going to be a Central European impact. How might you react to that? One of the things I noticed in this, and we could talk about it as we go around, is 4 months, Paul said that we'll be getting updated information all the way to the impact point. And also a question to consider with Lorian information she gave us worst case, gave us minimum case. I think that 75% case is the best thing for us to aim for, because the number is small on one end and really large on the other end, and there may be political or other considerations that might not, saying that you need to evacuate 1.6 million of your citizens is a tougher problem. Then also the idea that it may not actually impact a major metropolitan area, but a lot of those areas are surrounded by suburbs, exurbs, or outlying towns. And even if it does not land or impact between major cities, what if it impacts significant infrastructure, which is going to prohibit or hinder some of your evacuation or preparation events? So those are the kind of things I think we should aim for. And I'm just going to go around and everybody can speak, think about 5 minutes each, so we can have enough time for anybody who wants to participate with questions afterwards. And let's start off with Einar. Einar has over 20 years experience working for the UN, using satellite imagery and support to sister agencies and governments. He is director of UNOSAT, the UN Institute for Training, Research, Operational Satellite Applications Program. So starting off with you, Einar.
Thank you very much, Ale. Yes, it's a pleasure to be here. Thank you so much for the invitation, and especially thanks to my colleagues at UNOSA and the SPIDER program for inviting me to be part of this event. From my side, what we see is the value of exercise. Now, this is, of course, an exercise that has been going on in the last couple of days. What I would like to focus on is to see also how this type of quite special type of event, I would say, how that can be blended with the more normal emergency management response and planning. And to do so, I think it's important to note that there are, of course, as you know, many entities that have this kind of a specialty in terms of search and rescue, in terms of evacuation, in terms of responding to disasters. So I would, from my side, although we work, of course, with satellite imagery, and I would assume after such an event, that would be quite easy to get up-to-date satellite imagery of the impact area, depending on the cloud cover, of course, as well as, of course, aerial. I would assume also easy access to aerial surveys as well, probably drone footage and what have you. But I think it's important to nevertheless also practice this with relevant entities. So one entity also, as Tom de Groove here is well aware of, is GDAX. It's a GDAX system, and we are able to basically bring scientists and I would say also the early responders together and exercise various scenarios. So I think this, what you have come up with, of course, with impact areas, etc. If you want to make also a real case scenario out of this, and really beforehand, I'm not so familiar with what you have in the US, but having this information then readily available and exercised within, let's say, the international normal search and rescue system would be quite beneficial. You have INSARAG, the INSARAG mechanism, the International Search and Rescue Mechanism, that are professionals in this. They go out after, for example, earthquakes, etc., and tsunamis, and anything that we have a lot of structural damage. So that is a network that could be very much involved here, I would think. I would also think that many other actors within the EU, of course, in this specific scenario would be very relevant. I'll let the other panelists speak to that. But from the UN, from the international perspective, I think yes, exercising this in advance would be extremely beneficial. Not, of course, just done in the European context, but also at a more global scale. And one very nice entity or system or platform is the virtual OSOC. This is managed by the UN Office for the Coordination of Humanitarian Affairs, and they specialize in this. And they also, they're of course very operational, and that is one thing. But in addition, they specialize in exercising together with the various countries and also international, let's say, mechanisms, such as INSARAG and also others, also more thematic areas in terms of health, in terms of more logistics, etc. So I think, blending this together into the existing mechanisms would be very important. So, and also what I saw in terms of the outreach and the mechanisms to inform the population, this is of course also something that would have to be well planned out in advance. And from my side, yes, I would just think that having this possibility to immediately task satellites, of course, the sooner we have an area well defined, the better it is. We have the International Space Charter, for example, that could be activated in a situation like this. There's also many, of course, companies and other entities that could easily take photos and take pictures. Although this takes place on the 30th of July, I believe it was. Then nevertheless, we are ensured sort of daily coverage, of course, depending a bit again on the cloud coverage on that specific day. But we do have daily coverage now of the whole planet. So I do think that having all these tools working nicely together would be extremely important. And for future scenarios, of course, what you have to do then is to really exercise this well in advance and exercise it. Again, just to conclude, by bringing together the specialists like yourselves, but with the people that have a huge experience and also work at the local level. So it's a combination of international efforts, of national efforts, and local level efforts. And I think this is where exercising in advance is extremely important. Thank you.
Thank you, Einar. Great remarks. And I was going to mention, you answered a question that I was going to have, is should we have a separate exercise that concentrates with the emergency and disaster types with our scientist colleagues, giving us the information and kind of working it through for real. So thank you for asking that, mentioning that. Next, we'll go to Tom DeGrove. He's the Deputy Head of the Disaster Risk Management Unit of the European Commission's Joint Research Center. The unit focuses on bringing science into EU's disaster prevention and response, including through early warning systems and a Copernicus Emergency Management Service. Dr. DeGrove is currently chair of the JRC's COVID-19 Task Force and to coordinate multidisciplinary and cross-sectoral responses of the JRC. Tom. Thank you, Ale, and thanks a lot for inviting me to the panel and to have the opportunity to speak here, but especially to learn about this topic. So, as Ale introduced me, I'm part of the Joint Research Center, and this is a research center that works at European level in the European Commission. So it's transnational, and obviously a case like this is transnational and would activate all the EU level mechanisms that exist, and there are many. And I think my colleague Miguel Roncero from the Emergency Response Coordination Service will go a bit more in detail on those. So to our knowledge, there is no contingency plan in place for such an event, or at least not in the circles, the disaster risk management circles that me and Miguel were moving in, which is perhaps a gap. No, this is an interesting fact by itself. So if this is the case and there is no plan and we are in such a situation, then we can think how it would work. And I think the experience from COVID is really good to understand, because this was a similar situation where there was not a lot of no plans, not many plans, and you needed to put networks together to talk about this. Lots of science, lots of statistics, difficult graphs to interpret, things you need to translate to decision makers, and this is our specialty. So in the Joint Research Center, first thing we would do is make a task force, on this, and go cross departments with economists. What would be the economic impact of this? With social scientists, how can you see the behavior, check the behavior of people? Is fear building up? What is the media saying? Monitoring media and the build up to this. Putting all this together, like we did for COVID, is very, very important to bring this multidisciplinary expertise to the decision makers, in this case, the European level. I mentioned activating networks. There's a lot out there. We have volcano experts that are experts in evacuation. So we would perhaps look at them to plan evacuation scenarios, not for the Vesuvio in Rome, but instead transpose that to the place where it would be it in Germany or Austria. So there's a lot of this knowledge we really have to pull together. And there, this year, the EU will launch a new animal, a new part of the civil protection mechanism, which is a knowledge network. And this brings together preemptively scientists from member states, because remember that in Europe, really, it is member states that are independently acting, and the European level can only coordinate. So we need to involve all these people. So this is a very good step already, and could be a vehicle or a place where the results of this exercise can come in and can be discussed now to come up to a real network or some kind of knowledge related for if this happens for real. I would like to mention also the Copernicus Emergency Management Service, which is the space program in the EU, which would clearly be activated in this case immediately for post-disaster imaging of the situation, provided that, of course, the satellites are not taken out by the asteroid themselves. So we have to see for that too. Luckily, the Copernicus program can use any satellite, so not only the Sentinels, but there's a program to buy from anything, so also Planet and what have you. So probably there would not be a problem to get the imagery there. Maybe still from lessons from COVID is that it would be very, very important to communicate well. In the commission for COVID, this went directly to the president, who activated a special cell for this and got from all departments inputs. The same may be happening for this case. And communication is key, which was mentioned. So there's a whole department for communication in the commission that was working very, very closely with us, the scientists, to come up with the message, to keep talking to the population, lines to take, what can we say, what can we not say, and this will be, of course, extremely important here. Both Miguel and I had an immediate question to the previous presentation, which was, when is that radar available and how much time, when will we know for sure? Because you can lead up to that, of course, and you can then in the last, what be it 5 days or a week, it would be enough probably to prepare for this. But in the build-up time to that, we need to communicate clearly to the communication about this risk. These would be some of my first remarks. I think the socioeconomic situation could be important, because if a whole area is destroyed, there will be economic consequences. In the COVID situation, these were initially a bit underestimated, and it was very, very difficult to link the communities, the economic modelers and physical modelers. This is something that we have a bit more experience in now, but could be also in this case an important thing to consider. I'll leave it at this, LA, for now. Hey, thank you very much, Tom. And I didn't see your note, so I'll go right to your partner there, Miguel. Miguel leads the Situational Awareness Sector under the Security and Situational Awareness Unit of the European Commission's Directorate General for European Civil Protection and Humanitarian Aid Operations. So over to you, Miguel.
Thank you, LA. Thank you, colleagues. It's a pleasure being here, and coming after Tom is actually great because I don't have to repeat a few things that he said. One thing I would say is that, of course, well, there are several different coordination instruments within the European Union, and one major response coordination instrument, that this is the Union Civil Protection Mechanism, which is under DG ECHO, the DG that brings together humanitarian aid and civil protection. So for the American colleagues, imagine you put FEMA and USAID together, that's DG ECHO in a sense. So this Union Civil Protection Mechanism coordinates or would coordinate 27 EU member states plus 6 participating states in Europe but outside the European Union, but also will be the element, the instrument that will be coordinating with other international partners. I mean, here, unfortunately, we see that Central Europe is going to be impacted. So one of our first reactions would be, how could the colleagues, friends in North America, FEMA in the US, or through NATO, Canada, the US help? How could Russia help as well? How could other big players in the other side of the world that are not going to be affected can help us? So coordination here is going to be key, because unlike perhaps our naive view for most of us in January 2020, that this disease starting in Wuhan might be contained. Now we know in this scenario that it's going to hit, and we have a map. Second important point would be not only communications, but panic control. When I saw the map that Loreen was showing with the impact area, as a human being, the first thing I thought is, well, my political family is in the high impact area. So, they need to get out. Of course, 4 months before the impact and 4 months before that big area is narrowed to a small area, that's going to create panic in the population. That's going to create, well, the need for people to live. And this has to be very carefully considered. We should not underestimate millions of people seeing a map like the one Lorraine showed, not being able to understand it, and just acting in, based on irrational consequence, information on their side. Ele, I went through the questions that you gave us. I'm afraid that in 5 minutes, I will not be able to really reply to all of them, but I have a few elements here. We are talking basically about, in my opinion, in my view, 3 key elements. One is preparations, planning for evacuation, worst scenario, median scenario, this is important. I think that in the context of COVID, so if this was to happen now, it will be very natural for decision makers to look at the worst case scenario. Why? Because COVID has shown that the worst case scenario can really happen, particularly when, again, back in January 2020, today, April 2021 was not considered necessarily. So there will be a natural reaction to that. But here's about planning. Here's about what can we do when to save as many people as possible, to evacuate people. This is not only about evacuating people, there's going to be cascading effects. Tom mentioned the impact on the economic side. I can add a few other things. Energy networks, transport networks. The area that is going to be impacted has several nuclear power plants, has several big chemical facilities. How can we ensure that those are adequately taken care of so they don't trigger an additional crisis, a cascading crisis, which might be, also quite bad? How we are going to ensure that this central area in Europe, which is the neurological corridor between north, south, east, and west, how is that going to be bypassed if the transport networks are destroyed? Not only for evacuating people, but for transporting, for example, food assistance, for transporting in and out support in many ways. The healthcare system, we are talking here potentially about millions of people affected. I would assume would be dust, ash, of course, the blast itself. How are healthcare systems going to be able to cope with this? And you have the really relevant question, put a pandemic on top of that, then we are really entering into a very, apocalyptic scenario where you have a healthcare system nearby the line of collapse, and to that you can add a high influx of people affected or potentially affected. And of course, together with evacuation plans for the worst scenarios. And again, here we need to know, as Tom said, we really need to know the narrow area as soon as possible. So this is a question that I repeat that Tom posed, because this we need to, it's a question to the scientific community. We need to narrow this down. But besides evacuation, we need, shelter options and a surge capacity to potentially shelter millions of people. This is not easy. We are not talking here about a few thousand people or a few thousand, containers to have someone for a few weeks. We are potentially talking about permanent displacement of millions of people. And this is also going to create potentially other issues. Maybe you can relocate within the same country. Maybe the evacuees need to relocate in other countries. And we know that this can trigger also other effects later on. I would just perhaps stop it here just to mention that, when this, under the scenario, of course, when this would happen, the European Union, through the Emergency Response Coordination Center in Brussels, which fortunately in the scenario has not been affected, Brussels has been spared, so thanks a lot. But through the Emergency Response Coordination Center, through the Union Civil Protection Mechanism, and in this case, this is a global event, so likely through different international partners and friends, well, the ERCC would be coordinating the response efforts. here we are talking about such a big magnitude of things that I could just echo what Tom said. To my knowledge, there is no contingency plan for this. So this is a gap perhaps for us, something to sit down and think, what can we do in an effective, efficient way after the asteroid impacts? You know, what is that can be done that is relevant, is meaningful. And here I would stress that there is a lot more to do before, and this would be the key thing. But then afterwards, there would be absolutely quite a lot of work to do. The UCPM has many years of experience in multiple crises, from COVID to volcanic eruptions to tsunamis to you name it. So I'm sure that in terms of civil protection, the professionals all around Europe and all around the world will be able to contribute meaningfully. But we should limit the task by saving lives, saving livelihoods as well, as much as we can before this takes place. Thank you very much.
Thank you very much, Miguel. That was great. Really good getting your perspective, especially from the ERCC perspective. So let's go to my colleague who's going to be helping me tomorrow as a co-session leader on a lessons learned. Sarissa, you're on from the UN?
Yeah, I'm there. I'm
here. Please, go ahead, sir. Good to see you again.
Thank you, LA, and it was great to listen to all other panelists. I think I have challenge of not really repeating so much, because almost all the aspects they have touched, right from technologies, space satellite uses, or the challenges for the response. So I will try to be a little shorter and not so repetitive. But as a part of the United Nations Office for Outer Space Affairs, that has this platform called UN SPIDER, United Nations Platform for Space-Based Information for Disaster Management and Emergency Response. We have a certain role to play and contribute in this. Also experience that has been drawn from the advisory missions that we have conducted in several countries. So this particular scenario, whatever we have seen, is really unprecedented, because this has never been really visualized by disaster managers and responders, also, as well as the risk reduction players. So as a UN SPIDER, what we feel is it is very, very important to incorporate this particular disaster in the Sendai framework for disaster risk reduction. I mean, the framework is out already, but I think there are a lot of regional, national level and international level consultations takes place now for implementing Sendai framework for disaster risk reduction. And this particular topic has not been visualized, and it is very important because, as our colleague said just now, that we have to avoid panic situation. And one of the important things to avoid panic situation is the frameworks should incorporate this kind of information, so that people know that yes, there is a good amount of tracking and information is available. We will be having quite adequate early warning, and there will be enough time to prepare, so the panic can be avoided. So that is the role of international framework probably, and its consultations that we would like to push forward. Everyone has touched COVID-19 situation, how we really miserably failed in understanding its impacts, and second wave is coming, and third wave has come in Europe already. And what would be the situation by the time this impact happens? Will it be fourth wave? And so here it comes to another important point, that is multi-hazard early warning system. That is what is important, not just looking at that disaster alone, but multi-hazard early. And this is where I would like to point to International Network for Multi-Hazard Early Warning System, which has been launched as one of the outcome of Sendai Framework for Disaster Risk Reduction, of which we are also part, UNOSA. Of course, World Meteorological Organization is also leading it. So this network can come very handy in order to provide the information, multi-hazard early warning information in the, so this is one. That of course the other information platforms have been talked of, GDAX, but one important thing everyone has talked that okay, the response can be monitored by activating International Charter or Copernicus Emergency Management System, but we have to also remember that the area is huge, and it is very difficult to get those kind of images within certain time period. So we have to also use the power of frontier technologies, especially crowdsourced platform, location-based services. Like everyone in today in mobile, they have the location-based apps that can be installed. So this kind of information is very, very important in order to narrow down where to task satellite and where to collect the images in order to see the impacts. Another thing is that we are thinking of European scenario right now, but world has got a lot of experience. Like especially Europe doesn't have experience of evacuating millions and millions of people, because that kind of cyclones and disaster don't happen here. This would be the first, as we've seen, scenario. But think of countries like Bangladesh. When cyclone comes, they evacuate like millions of people. So there is something called Cyclone Preparedness Network, which has 70,000 volunteers. They take the early information and they go to communities. So those kind of lessons also, I think, can be taken from some other countries. What is value of this particular simulation exercise I see is how really benefit of science and technology can be incorporated in the formal framework like Sendai framework, and how developing countries, especially least developed countries, small island countries and other, which are not much benefited from power of this science, technology and governance, how they can be benefited. So this particular simulation exercise can serve probably as one of the examples that can be taken on multiple platforms, and people can become aware that this is also one of the things that can be handled very, very well, and there is no need to really panic. So I think these are some of the interventions I would like to offer. So over to you, Ele. Thank you.
Thank you very much, Luis. And next we'll take our colleague Richard from the ESA. Richard coordinates the mitigation activities of the European Space Agency's Planetary Defense Office. The main task of the mitigation pillar of the PDO is to ensure optimal transmission of all relevant data gathered and derived from observations around the world, and also inform international warning networks, decision makers, and disaster management entities. So over to you, Richard.
Thank you. Thanks very much for all the things that were said before. I wholeheartedly agree with everyone. We at ESA, we are not executing the disaster management. On the contrary, our mission is to inform. Our observation pillar gathers the data from all over the world, as was said, and then our information provision part derives all the relevant information, and together with the mitigation activities, we want to get the right information to the right people at the right time. And as has been mentioned a couple of times, the right time is before these things happen. The right time is preparing in an exercise or in multiple exercises. And therefore, we have actually run along with this exercise, and we have developed recently an automated and semi-automated warning system that could, in near real time, inform disaster management agencies or national or multinational warning networks in a very quick and efficient way. And in fact, we've managed to put together warning messages, our close approach fact sheets, but also the automated warning messages within a few hours. And as a test, they have been transmitted already to the German warning network chain. So one thing that I can highly advertise here is that we, while we are going on to develop these mitigation or information tools, to also be able to transmit them to the European and UN warning networks so that you can include our information in your work. And even ahead of that, as I said, the right time to do something, to act here, is in advance to do exercises. So that's one thing we also offer, and we've recently also done that with the German authorities, is to provide scenarios like this nice scenario that we've had here for the PDC, with a focus on training our partners. So we offer to go through these exercises, give you the warning products or the information products that we have at hand or that we're developing, but also train and teach what this means, what is behind of this. As we've seen, a lot of this is based on uncertainties or statistical properties. And this is, as you've easily seen, it's hard to digest all this statistical information. So how likely is the worst case? How much should that inform the decision? So we plan to also produce guiding and information material on all of this, that together with impact effects warning tools that we can distribute to everyone in the world who is willing to take them. So yes, because if we do that, if we prepare ahead of time, we get one massively powerful tool. It's education and knowing what to do and not having this gap, as was referenced, of not having a strategy. There are individual partners we've worked with who have a strategy or at least dossier level preparedness, but we would like to expand this to, yes, we've trained for this. We know how to deal with the statistical properties. We know the specific language in which it's transmitted. This is all very important, and it gives the most powerful tool of all. It gives for the public communication, once the time of crisis should arrive at some point, it gives the very powerful message of, look, we've trained for this, we have an idea of what to do, you're not doomed. I think this is one of the most powerful tools you have available to mitigate against the panic, against irrational actions, or against politic turmoil. If on a European level, if on a UN level, if on a national level, people have been training for this, and it's no wizardry work. I mean, there are certain physical processes, and once you know them, you can train disaster mitigation forces on the ground to act directly on this. Yeah.
Richard, thank you very much. That was great. I really appreciate all my panelists. Lauren, I had a question that maybe you can clear up for the panelists. You know, there was some discussion here about the statistics. In our U.S. exercises we've done with NASA and FEMA, one of the things we always talk about is things like histograms and stuff like that are not necessarily understood by a lot of the public. So what do you think of the remark of narrowing down the most probable impact area for the disaster managers? How practical is that? Is that a function of how much time or how much data you have? And how would we incorporate that into our plan? Because at a certain point, and I'll get back to Miguel, maybe he can answer this, we're going to have to know what the target is or what the main impact area is so we can help the most people immediately. And I think that this is such a specialized thing. In the U.S., we have people who are used to hurricanes. We have a couple of large-scale disaster plans made up for events for like the Cascadia zone for the West Coast or New Magic seismic zone in the United States. But I'm not sure if there's something similar, a large-scale plan like this for my colleagues in Europe. So, Lauren, what do you think about the possibility of making that data more specific for disaster responders?
Absolutely. I mean, that's one of the primary goals of exercises like this, is to start that communication, because we can provide any sort of range of probabilities. We can focus on most likely regions. But in order to know what information is most valuable to you for disaster responders, we really need that exchange of information and feedback from you guys as to what your capabilities of planning are, what your risk tolerances are. And that also may differ between different agencies, different countries, what their risk posture is. So that's why, to start with, we try to focus on results like the exceedance risk. So someone coming in with their own capabilities and their own level of risk tolerance can sort of figure out where along that risk line they fall, whether they can fully address 100% of the cases, 75% of the cases, that sort of thing. But it is important to develop more sort of formal products and metrics that everybody understands going in, and that do bound those risks in a way that makes sense on both sides. So it's definitely an ongoing challenge, and one of the good aspects of these exercises. And I think something that what you mentioned about possibly having a more focused exercise focused on disaster response would be really beneficial for working out things like that.
Okay, thank you very much. Miguel, you mentioned that since this might be a gap, how difficult would it be for you to gather, you and Sharice, for example, the UN Spider and your organization to get together, grab the requisite experts? Because in our exercises, there was an economic part of it, and we did have some analysis done by one of our national laboratories on the economic impacts of that, especially with critical infrastructure. How many power plants are in that way? Are there any major rail hubs in the impact area, and how that would affect? Also, timetables based on experience. How long would it take you to move a certain amount of people? And in the United States, as an example, for our hurricane-prone areas, the individual states in the United States have already set up agreements on how many evacuees from each impacted area that they would take, so that there's not a flood of massive people going to just one place. Here, the federal government doesn't have any authority to make someone evacuate. It's a recommendation. That's under control of local and state governments only, not the federal government. We just can recommend. So a lot of people are going to go to families in other places, et cetera, et cetera. So over to Miguel or Sharice, how you guys would think about handling that? Will we need to convene an immediate special project board to oversee something like this?
I can perhaps go ahead. Well, I hope that events like this or this particular conference helps us realize about the gap and helps us with the connections we need to start elaborating the different elements for a possible scenario. I mean, we rely, for example, in DG ECO, the European Commission, we rely heavily on our colleagues at the Joint Research Center, and ESA being an agency of the European Union, of course. In this regard, it's not only, I mean, we will already be working with them and through them with the external actors to make sure that we are bringing everyone around the table. And I hope that as a result of, this could be one of the conclusions of the conference, that, should this happen in Europe, what could Europe do and what could also the world do, and knowing that we just have to change also Europe for anywhere else in the world. Now, when it comes about your second question, the big plans, in Europe, there are plans for certain events. So Italy, for example, has plans should Vesuvius erupt and should they need to evacuate Naples, which is an area in the metropolitan area, more or less has 3 million people, and this is something that could be relevant to learn from. However, in Europe, we are relatively lucky when it comes about natural disasters. We don't have hurricanes hitting our shores like the US or the Caribbean or other parts of the world with tropical cyclones. They do. And whenever there are earthquakes in Europe, they are rather localized. I mean, they can destroy one town, nearby towns, but they are not events of the scale what we are seeing here. So I'm afraid that our geography is, making our planning not up to the standards that we will need for this particular scenario. It doesn't mean that we cannot, and we probably should, consider scenarios like this one, because as we have learned from the COVID experience, the unthinkable really can happen. And we also have experience of things that imply large movements of people, but not in this scenario. I'm thinking about the so-called migrant and refugee crisis that started in 2015, where hundreds of thousands of people flew into Europe in a very short period of time. There, the European Union was a catalyst to help member states affected, mostly Greece, not only, with the setup of sheltering options for these migrants and refugees. That is a lesson and an experience we can learn from for this case. But what I can say is that even though there are member states in Europe with plans for this massive evacuation. This is nothing we have necessarily, at least not that I'm aware of, or at least not at the levels I work in for this kind of events. Now, this also being said, I mean, Europe is a relatively highly nuclearized continent, and there are many nuclear power plants in relatively densely populated areas. And I'm saying this because member states also need to have evacuation plans for these facilities. So there are elements from which we can learn to put into context and into practice for this particular scenario.
Thank you very much. Suresh, do you have anything from the UN side, Suresh, that could add to this? We only have about 9 minutes left, so I want to make sure I get Suresh in here. And if there are any questions from our attendees, put them into the chat. We'll try to get to them when we have the experts here. This is a very important topic. I think for here in the U.S., we would adopt a lot of plans that we already have if this scenario came into place. We just take pieces of other plans and come up with an overall idea. So, Suresh, over to you, sir.
Eli, you said my name because sometimes your voice is not clear.
Yes, sorry. Yes, over to you, sir.
Okay, thank you. I think almost most of the topic from this angle have been touched. Yeah, but what is critical is, tagging all these, that has been made the point, tagging all the critical infrastructure. And this is where the, power of geographic information system lies into. But one element that I wanted to bring into discussion, probably, Eli, you can probably contribute to it, is that, see, this is different kind of disaster wherein, see, impact of cyclone, earthquake, or, avalanches, people know what is going to happen. But here it's blast. So how that blast is going to impact the critical facilities, what is the potential of damage? And when we look at FEMA experience, we also have the system that's called HAZUS that also simulates, kind of potential impact and economic impact and other kind of thing. And probably I'm sure that this kind of scenario is not fed into systems like HAZUS. So I think this simulation can also trigger those kind of things, that being a different disaster, how one can use those systems to, simulate the impact. Economic impact of the physical impact and all that. I think those things also need to be a little bit brought into notice. And as I said, this whole exercise, although focused on Europe, as a UN agency, INR will agree with us, we are committed to take this experience to developing countries, or least developed countries, island countries, or we also call the countries in distress, which don't have really access to those technology and this kind of information. I bet that not even few developing countries are part of this conference. So our commitment is basically take lesson from this, so that when they listen that this kind of network is available and this kind of information can be provided in future, I'm sure those disaster managers back in their country will put that things into their national disaster management strategies, and that will create quite good awareness, so that if this comes once in 100 years, like pandemic came once in 100 years, but we are facing it now. So now it is a good time to tell them that some disasters might come once in 100 years, but we need to have that, our vision to prepare for it and respond to it and mitigate it. I think these are some of the points I wanted to put. But if you wish, you can reflect on HAZUS kind of point on the HAZUS. Thank you.
If I can answer that real quick, we are working on incorporating infrastructure risk into our risk metrics. We have started working with FEMA on preliminary ways of ingesting that material, and we can do infrastructure at risk within our regions using the HAZUS database here in the US. For other regions where we don't have access to the infrastructure data, we have ways that we can produce sort of generic geographic shape files that other agencies can then ingest into their own individual infrastructure databases or disaster response plans, however those are used. but these are still developing areas, and we're working towards that. In terms of more economic models, we're also starting to look at how to assess more downstream, more regional economic effects. Our team is working with Tim Titus at the USGS. They've got a talk in the impacts effects session on that. So those are definitely areas we're working towards incorporating into our risk metrics.
Thank you, Lauren. So we have about 4 minutes left. So are there any questions that want to come in to the chat, or is there anything else one of the panel members want to mention? The economic aspect. Oh, Tom, please go ahead.
Yes, thanks, Ale. I would like to make one comment back to communication, how important that is. And there was a question whether we need more statistics or less statistics or easier. Well, my answer would be we need all the scientific data from this group. No, we need everything, because it would not be directly served to the decision maker. But there's a lot of people at the European Union level, so we would be involved and we would look at it, but also in the member states, it would activate all the scientists. No, you would quickly have the experts that can easily deal with this data. I'm saying this because communication is very cultural, and it's also very political. I think you have to shape your message for the moment, and there are experts in this, of course. You gauge the mood, what is this population doing now, and it may not be the same in Germany or in Austria or something. We see this now. There are a lot of different strategies for communication on the pandemic. Some are very successful, some others, and population behaves differently. It will be the same I expect it to be the same also for an impact scenario like this. And we have to avoid that people believe conspiracy theories and believe that we are controlling the message too much and not saying the truth. No, transparency is very important, as well as a simple message. And I think this needs to be left to professionals, but with all the data available from NASA, from the experts here. Some of this has been described in a book we wrote, and I just mentioned it here. Science for Disaster Risk Management. We have 2 editions now built from by the Joint Research Center with 300-400 authors from around the world that look specifically at some of these aspects. So this may be an interesting resource also for working further on this area. Thank you.
Thank you very much. We have about 2 minutes left. Richard?
I fully agree with Tom here. It's about getting all the information that is relevant and available out there. I just wanted to add and ensure that the proper information hits the proper experts at the proper time. This is the only thing I could add, because I fully agree with you.
Oh, great. Thank you. In our exercises here in the United States, we assume that every piece of information is going to get out to the public. So there's no point in trying to make anything classified that is counterproductive. There are a lot of civilian scientists, experts who are out there who will also be making their own analysis. So we'll be competing against those guys also. So we got 1 minute left. Who wants the last word? Einar.
Thank you very much. I think it's extremely important, this issue of training that also Richard mentioned and also Sherish mentioned. Especially we in the UN, we have these tools that we can very quickly inform and take the latest science that you guys will provide and being able to inform other member states of what exists. So I think here we have a good tool of both a combination of science and also how we can make sure that other countries, especially as was mentioned, those countries that do not have this capacity themselves can also benefit from this. So I know it's going to take much time, but I think that is extremely important to also have that, let's say, knowledge transfer inclusion as part of this process. Thank you.
Thank you very much. Ladies and gentlemen, that concludes our session. I don't want to go over time. Nahum, I turn it back over to you, sir. Thank you very much, everyone.
Thank you, LA, Lorian, and panelists. Thank you, everyone. Just to hit on some of the very interesting topics that were discussed here, we talked about pandemic powers and differences and we looked at comparisons with other frequent and infrequent natural disasters. We talked about disaster tourism, and there is an ongoing example with a volcano erupting now. Earliest preparation and training as possible was mentioned, very critical for preparedness. Reliable communication and information coordination and sharing was one of the topics that was mentioned a few times. And developing impact effect assessment tools is critical to understand the effects and how to prepare for this. So thank you very much, LA. This was a fascinating panel, a new element in the conference with a good emphasis on disaster response and management. And next, Paul Chodas will present the last exercise update. Take it away, Paul.
Hello, Nahum, I'm here. And I'd like to share my screen if possible, Ramona. Thank you.
Yes.
Let's see. Okay, I'm given 5 minutes now to wrap the whole thing up, and that's a real challenge, I must say. Let's get this screen shared. Can you see the right screen?
You need to put it in a presentation mode.
How's that?
Yep.
Yes, okay. So, final inject. The chat has been very interesting. I've been following it, and some of it was about the radar. So, of course, the radar does indeed become very important in the final days before impact. The date of this inject is October the 14th, which is 6 days to impact. And finally, asteroid 2021 PDC has been detected by the radar, and the size is smaller than previously thought. And I'll get into that in a minute. And of course, the impact energy is expected to be around 40 megatons, according to the radar measurements. My co-author here is Lorian Wheeler. I'm going to try to summarize up the orbital part, the radar part, and Lorian's results all into this 5-minute presentation. So here's the information for this inject. With only 6 days left, 2021 PDC has finally approached within range of Goldstone radar. As was mentioned in the chat, the radar would have been pinging the predicted asteroid position for many days, not knowing the precise size of the object or its other properties. But we feel that it could detect the asteroid at around 7 million kilometers of something of this size. And today it's down to 6 million kilometers. It travels about 1 million kilometers per day as it's approaching the Earth. The radar images show the size of the object to be around 105 meters, plus or minus 10%. Radar cannot give us an exact measurement of the size, but within 10%, we feel we know the size. This is the effective spherical diameter. Now, the optical tracking over the last 3 months has led to increasingly accurate orbit impact region estimates as well, as was mentioned in the chat. But now that the radar astrometry has been incorporated, that's enabled the most accurate prediction yet of the impact region, which is now centered near the border of 3 countries, Germany, Czech Republic, and Austria, as you will see on the next slide. The impact location, in fact, can now be predicted to within about 23 kilometers, 3 sigma, and the time to within 1 second. Some statistics, the entry velocity we know will be 15.2 kilometers per second. That's 34,000 miles per hour, by the way. And there was a chat question about, whether satellites could be influenced by this asteroid on the way in. It's not spending much time through the constellation regions of the satellites. It's going so fast. The size is still a little uncertain. The size, the shape, the bulk density, we still don't know those, and therefore the mass. And this will lead to still a range of possible impact energies that go all the way from 9 megatons to 156 megatons, according to Lorian. And Lorian tells me the average is around 40 megatons for this final inject and the distributions on mass. The worst case damage region is about 300 kilometers across, the average 150 kilometers. And I'll show those in the next couple slides. There at the bottom is the URL for our final inject, and you'll see a fact sheet there as well. So the impact region is here. 6 days before impact. As I say, it is right on the borders where Germany, Czech Republic, and Austria come together. I again show this depicted as red shaded regions. Inside the large envelope, the probability is 99%, and then increasing, it concentrates towards the middle contours of this area. Now this is just the impact region, the projection of the trajectory to the surface. The next slide indicates the damage region, and this is from Lorient. It, of course, still is large, depending on what the mass of the asteroid is. You can see that the full worst-case damage swath is as large as 300 kilometers across and just reaches to the city of Prague. The average size, though, of the damage extent is about 120 to 150 kilometers across, as indicated by those line contours. That is then the best prediction we can make 6 days before impact. Now, radar will continue to observe this. And so this region, the predicted region, will shrink a little bit as we get closer, but it won't change the damage risk swath size much at all, because this depends on the uncertainty in the mass, and that still is quite uncertain. If I may, I have just a minute or two left. I have some takeaways I'd like to give, and these are technical takeaways, and these have already been anticipated by the chat to some extent. But I would like to kind of summarize the scenario by saying some pretty obvious things. A short warning scenario poses extreme challenges for in-space mitigation. So this was challenging from the beginning. It was kind of intended to be challenging from the beginning, from the in-space mitigation point of view. We were really focusing on the disaster management topics with this scenario. Had a more sensitive asteroid survey, such as NIASM or the Rubin Observatory, been in place back in 2014, it would almost certainly have detected this scenario object. And because it wasn't that far away that last time it passed by the Earth. And the 7-year warning of a potential impact would have opened up a host of different possible outcomes. In particular, space missions would have been feasible for reconnaissance or simple kinetic impact or deflection. So finding them early, if possible, would have totally avoided the extreme challenges we had with this scenario. Another interesting point that we tried to draw out in this scenario is the role of precoveries. And they could play a major role in assessing the impact probability of a threatening object. And the importance there is that all these sky images taken by asteroid surveys need to be archived, and the images need to be searchable. And we have that pretty well, that infrastructure pretty well in place. But that's a very important element, and this is the first scenario exercise in which we've included a significant role for precoveries. Final point, and it's become pretty clear, and including in the chat room, the large end of the estimated size region becomes the dominant factor in a scenario. Capabilities that can put an upper bound on the size of the object are invaluable, and those obvious capabilities include space-based infrared, such as NEOWISE in this case, or NIASM. Planetary radar, of course, but the asteroid has to come within range of the radar. And recon missions to actually investigate the asteroid up close. And those would be possible if we had an early discovery. There were several other ideas that were forthcoming in today's chat, including occultation and correlations with other parameters, such as colors and polarimetry, and how those might factor into the distributions of physical properties. I think more work needs to be done in looking at those factors. I'll end there. That's the end of the exercise.
Thank you, Paul. Certainly a few windows will be blown out in somebody's home. So that is quite a fascinating scenario to think about. In 15 seconds, just a question that came up was about what happens if Goldstone radar goes away. Is there other alternatives to radar detections?
Well, Arecibo, of course, is no longer with us. Right. So Goldstone is the only possibility. Now, there are other antennae which can be used to detect the object by radar, but they're not as sensitive. So right now, Goldstone is really the only way to detect an asteroid of this size that is, millions of kilometers away. When it gets much closer in the last few days, yes, there will be other radars that can detect it.
Okay, something to think about. Thank you so much. Lindley. Lindley is head of NASA's Planetary Defense Office, Coordination Office, or PDCO, and Detlef is acting head of the Planetary Defense Office at the European Space Agency, or ESA. Lindley and Detlef, the floor is yours.
Yeah, okay. Thank you very much, Nahum. So in the following hour, I have the pleasure, together with my colleague Lindley, to chair this panel session. We will actually start with an introduction by Simonetta, and then we'll take it from there. So Simonetta, would you kindly open the session?
Thank you so much. I hope you can see and hear me well. So distinguished heads and representatives of space agencies, really let me take this opportunity to welcome you at this 7th IAA Planetary Defense Conference hosted by UNUSA in cooperation with the European Space Agency. Space agencies are important partners for the Office for Outer Space Affairs, and with many of your space agencies, we have long-standing cooperation agreements that enable our office to broaden access to space for all and work with you on some of our flagship initiatives and projects. For example, the Access to Space for All initiative, Space for Climate Action, Open Universe, Space for Youth, and the annual gathering at our flagship event, the World Space Forum, to name just a few. Well, space activities have witnessed an intense growth and diversification. International cooperation in the peaceful uses of outer space has evolved enormously. It provides the impetus for developing international mechanisms and infrastructures for space cooperation and coordination at the national, regional, and international levels. If at the beginning of the space age in the late 50s, there were only two space powers, and 2 satellites had been launched into outer space. Today, we see more than 3,300 operational satellites orbit the Earth, with nearly 90 countries having operated their own satellites and establishing space agencies or space offices. This means more players, more interest, more capabilities, more need of international cooperation. Strengthening preparedness in case of a potential near-Earth object impact hazard to our planet and population is an important part of this collaboration. While UNUSA works with the Space Mission Planning Advisory Group, SAMPAGE, and the International Asteroid Warning Network, IAWN, on a coordinated international response to the impact hazard posed by NEOs. The goal is to strengthen information sharing at the global level on discovery, monitoring, and physical characterization of potentially hazardous NEOs, and enable that all countries, in particular developing countries, with limited capability in predicting and mitigating the impact of near-Earth objects, are aware of potential threats and prepared for effective emergency response and disaster management efforts in the event of such threat. I'm very pleased to have you join this conference and specifically in this dedicated panel to address, from your perspective, the angle of international collaboration in the area of NEOs and planetary defense. And also, I would like to thank you and to thank your space agencies and others who have not been able to participate today in joining our work to build more resilient societies, bring the benefits of space to everyone everywhere, and strengthen preparedness in case of a potential NEO impact hazard. And I really look forward for this panel discussion. Thank you very much. Thank you very much, Lindley. Thank you.
You're muted, Detlef.
Also, everybody else, please mute because sometimes it causes an interference when you don't.
Okay, see, it's good we are too. Thanks, Lindley. Okay, thank you so much for the introduction, Simonetta. We have in this panel asked representatives of space agencies to share their plans and thoughts on the following field related to planetary defense. What do you think should be done or are you doing in terms of NEO Discovery's mission planning? Then focus on cooperation with other space agencies in planetary defense. How do you see that point? And how do you see the role of your agency linking to disaster management communities and decision makers? And in particular, what are your thoughts on what we're still missing, both in different agencies or on an international level? And before we can really start having the panel itself, the people that are here having their thoughts shared with us, we have a number of video messages. And could we please have the first video message, which is coming from the Director General of the European Space Agency, Josef Aschbacher.
Distinguished colleagues, dear friends, ladies and gentlemen. Unfortunately, I cannot be with you at the 7th IAA Planetary Defense Conference today, but I wanted to convey my best wishes for the Heads of Agencies panel on near-Earth objects, planetary defense, and international collaboration. The topic remains of utmost significance. Planetary defense, being prepared for a possible asteroid impact, is a central element of the ESA pillar, space safety. We take the associated challenges very seriously. This can also be seen by the strong ESA involvement in this conference regarding the Hera asteroid mission, as well as the planetary defense team, which takes care of observing asteroids, computing their orbits, and building up interfaces with the emergency response agencies. I would also like to stress that this panel focuses on international collaboration. Space is inherently global, and asteroids do not know country borders. Therefore, international cooperation is essential, and I'm grateful to the United Nations Office of Outer Space Affairs for engaging various international bodies and entities to this end. I'm convinced that the Planetary Defense Conference, and this panel in particular, will raise public awareness and provide a stimulus for space agencies and other institutions worldwide to scale up their efforts in the important domain of planetary defense. ESA is ready to contribute its share. I wish you all an interesting panel and fruitful discussions. Thank you very much.
Okay, thank you very much to the ESA Director General. We do have a full slate of space agency heads, quite a turnout here, and that's exciting to see all the interest from across the space agencies. With another video address for us that is being loaded up, we will now hear from Kunanaka Hitase, the Vice President of the Japanese Aerospace Exploration Agency, JAXA, and the Director General of the Institute of Space and Aeronautical Sciences in Japan.
Hello everyone, this is Kunanaka Hitase, Director General of ISAS and Vice President of JAXA. It's a great pleasure to join you all on this video today. I would like to express my sincere gratitude to the organizers of the 7th IAA Planetary Defense Conference in spite of this difficult time. Planetary defense continues to grow in importance, while the recent study has been identifying more objects that can cause damage to us in the event of impact. I would like to take this opportunity to share JAXA's diverse contribution in planetary defense, such as exploring near-Earth objects by Hayabusa and Hayabusa 2, surveilling such objects by JAXA observation facilities, and developing detection technique to identify them utilizing innovative image analysis technology. In the light of international collaboration, JAXA participates in HERA, an ESA-led planetary defense mission, through provision of instruments and science collaboration. The details of JAXA planetary defense activities will be presented by our specialist, Dr. Yoshikawa Makoto. JAXA strongly wishes to continuously play an important role in defending us from potentially hazardous objects. I am sure that this conference will be successful under great global collaboration. Thank you for listening.
Okay, thank you very much for that video address. And next, I would like to ask the China National Space Administration. We also have a video address there from Vice Administrator Wu Yanhua. I'd also like to point out we do have in the panel participants from the China National Space Administration. We have Yao Yanting, Vice Director of the Department of International Cooperation, and Yang Hui, Division Head of the Department of International Cooperation. But let's at first go to the video address from Vice Administrator, please.
尊敬的吉碧鹏女士，与会的各位嘉宾、女士们、先生们，大家好。近地小行星撞击地球风险是影响人类生存发展的重大威胁之一。加强近地小行星撞击风险防范应对，是国际社会共同面临的重大责任和挑战。 近年来，国际社会高度重视近地小行星撞击风险应对。在联合国架构下，我非政府层面成立了多个组织，联合开展国际监测预警、在轨处置、灾害救援等工作。中国政府高度重视近地天体的研究，自上世纪50年代起就参与了 国际近地小行星监测活动，在哈雷彗星回归、彗木相撞、海尔波普彗星和狮子座流星雨的观测和预报中做出了积极贡献。2018年2月，中国国家航天局加入了国际小行星预警网以及空间任务规划咨询组，积极参与国际合作与交流。 2018年11月，由中方主导的亚太空间科学天文台项目获得了亚太空间合作组织理事会的批准。近地小行星研究是该项目的主要科学目标之一。目前，中国正在论证小行星探测任务，计划采用一次发射任务，实现 一颗近地小行星的取样返回和一颗主带彗星的绕飞探测。中国首次小行星探测任务将对国际社会开放，在小行星探测技术、国际监测与预警、在轨操作等方面与国际社会开展广泛合作与交流，为加强防范近地小行星撞击的工作。 中国国家航天局将启动近地天体监测、预警等相关技术研究，筹建应对撞击风险的组织体系和工作流程，并积极参与相关国际组织活动。各国国际组织构建的 协调交流机制，愿与国际社会共商联防机制，共建联员力量，共享联测数据，为全球行星防御工作做出中国的积极贡献。谢谢大家。
Thanks very much to the Vice Administrator for sharing his remarks with us today. With that, now we will be able to move on to the heads of agencies that are here with us live. First, we have Colonel Carlos Augusta Teixeira de Moura, the President of the Brazilian Space Agency. President de Moura.
Dear colleagues, ladies and gentlemen, cosmic hazards and planetary defense has galvanized the attention of institutions worldwide. Given the different types of actors in this field, combined with the sizable number of threats, it seems reasonable to assume that the first step is to explore what cooperative processes are presently underway and develop consistent strategies to build relationships that can make planetary defense an increasingly feasible and concerted effort. An interagency approach is highly welcome, provided caution is taken not to duplicate the global space policy development process undertaken by the UN COCOS. I quote here my IAWS colleague, Dr. Joe Felton, who pointed out the work of the UN COCOS is aimed at developing new broad space policy for the overall forest in this technically complex area. Brazil follows the example of countries coordinating with ground-based observatories that report sightings of NEOs. Brazil was one of the 14 members countries of the Action Team 14, whose efforts eventually led to the establishment of the International Asteroid Warning Network and the Space Mission Planning Advisory Group. So far, we have two initiatives that support us in NEO's observation, called the Southern Observatory for Near-Earth Asteroids Research, the SONIAR, and the Brazilian Meteor Observation Network, BRAMO. In this decade, they have provided significant information about comets and asteroids close to Earth. In terms of space weather, the Brazilian National Institute of Space Research assembled EMBRACE, an acronym for the Brazilian Studies and Monitoring of Space Weather, which culminated in the establishment of an official space weather program. And also we have there the cooperation with some Chinese colleagues. One of its concrete contributions to the safety in the daily life is its cooperation with the Brazilian air traffic control system. We know that we have hurdles ahead, especially concerning what to do once a real threat is confirmed. How to address, for example, the significant deflection dilemmas regarding potential impactors. What about the side effects? What about the event where we need to use nuclear explosive devices? These and many other questions remain unclear and call for increased coordination and collaboration amongst established and emerging spacefaring nations. I understand that events like this conference add to such purpose. There is much to be discussed, lessons to be learned, and practices to be benchmarked. In Brazil, we have distinguished astronomers and experts, and we know that Brazilian initiatives as SONIAR, BRAMO, and EMBRACE can contribute worldwide. The Brazilian Space Agency is committed to keeping such tradition alive and enhancing multilateral collaboration. This seems to be an excellent opportunity to exercise this intent. Thank you very much.
Well, thank you very much for your statement and kind words there. Highly appreciated. I would like now to call to, well, we stay in the Southern Americas, so I'd like now to give the word to Salvador Landeros Ayala, Director General of AEM, the Mexican Space Agency.
Detlef, I believe DG Landeros is not online yet, so could you proceed?
Okay, do we maybe have Rosa Ramirez in the panel?
No, not yet. Please proceed.
Okay, then I hand over to Lindley to introduce the next speaker.
Okay, well, it's my great pleasure to introduce the Acting Administrator, Steve Zurchik, of the U.S. National Aeronautics and Space Administration, NASA.
Hey, thank you, Lindley. So first, I want to thank the United Nations Office for Outer Space Affairs for hosting the 7th IAA International Planetary Defense Conference in collaboration with the European Space Agency, and thank my colleague Josef Osbacher for speaking, and for ESA's collaboration with UNUSA. Gatherings like this remind us of the importance of bringing the world's planetary defense leaders together to ensure that we, as an international community, are ready for a potential asteroid impact threat should one arise in the future. At NASA, we take planetary defense very seriously, as we established the Planetary Defense Coordination Office 5 years ago, which Lindley runs for the agency, to manage the agency's increasing efforts in this area. The Planetary Defense Coordination Office, or the PDCO, works diligently to sponsor U.S. teams to find, track, and study near-Earth objects, and has a leading role in coordinating U.S. government planning for response to an actual impact threat should it become necessary. So Lindley leads our coordination with other government agencies within the United States to respond to an impact, and coordinates internationally. The PDCO efforts help bring technologies and techniques for deflecting an asteroid off of a predicted impact course with Earth to readiness status, and the Double Asteroid Redirect Test, or DART mission, launching later this year, will be the first test of an asteroid deflection through use of the kinetic impactor technique. Through the international collaboration of the Asteroid Impact Deflection Assessment, data returned by NASA's DART mission, and OSI's, the Italian Space Agency's Lycia Cube, riding along with it, as well as ESA's subsequent Hera mission, will produce the most comprehensive and accurate study possible for planetary defense and solar system science. So very exciting time, and very exciting missions upcoming. They're going to return a lot of data and improve our ability to potentially mitigate a potential asteroid impact. Like others have said, international collaboration is critical to planetary defense, and NASA's significant participation with international entities such as the International Asteroid Warning Network, IAWN, and the Space Mission Planning Advisory Group, SAMPAGE, shows our commitment to fostering and maintaining this collaboration. 2020 was certainly a challenging and difficult year for everyone in ways we never thought possible. And I do want to take a moment to reflect on the loss of the National Science Foundation's Arecibo Observatory. This facility has been an important emblem of Puerto Rico's commitment to international science research and education, and the discoveries enabled by this incredible facility inspired future generations of scientists and explorers. NASA is committed to working with both the U.S. and international partners for an appropriate future planetary radar capability. Deep space radar facilities and ground-based optical observatories across the globe are an integral part of NASA's strategy for finding and tracking near-Earth objects. Chelyabinsk was a chilling lesson to us all, and it serves as a constant reminder not to become complacent of the natural hazards in space that can cause a disaster here on Earth. We must continue to diligently watch the skies from the ground, but also enhance those observations with space-based capabilities like NEOWISE, and the future much more capable NEOSurveyor to find the remaining unknown asteroids more quickly and identify potentially hazard asteroids and comets many years before they are an impact threat. I'll end by again thanking the host of this important conference and all the participants who are virtually attending to contribute to planetary defense and science. You are all working to help protect the planet, and your work will have a lasting impact in helping to safeguard our future together. So thank you.
Well, thanks to you, Dr. Jurczyk, for these words. And I would now like to ask the president of the Korea Astronomy and Space Science Institute to tell us his thoughts.
How are you? This is Young-Duk Ba, the president of KASI, the Korea Astronomy and Space Science Institute. I'm grateful for the invitation of the UN-USA, and I'm pleased to participate in the panel discussion with the representative of contributing space agencies in the area of planetary defense. KASI was designed as an R&D institute in the area of planetary defense in 2015. Since then, KASI is striving to prepare for threats from space objects. In 2017, a natural disaster due to the impact of asteroid and meteor has been included in the Basic Act of Disaster and the Safety Management by Korean government. And the Safe Korea training is conducted annually under the supervision of the government. KASI joined the IAWN and the same page since 2016 as Korean delegation and has been contributing to the international response system for natural space objects. Particularly, KASI activity participated in the IAWN ground-based observation campaign of the last 3 times, 2012 TC4 in 2017, 1999 KW4 in 2019, Apopis in this year, by using the KMT-NET telescopes located in South Africa, Australia, and Chile. Recently, KASI announced that the spin change of 2012 TC4, a tumbling asteroid, was caused by the YORP effect as the first case of the near-Earth asteroid. KASI is also conducting a preface study on the Apopis Langdeb mission. As you all know, Apopis approaches within 31,000 kilometer distance from the Earth in April 2029. KASI is expecting a wide range of international collaboration for the Apopis Langdeb mission. An in-situ investigation of the effect of near-Earth phase on the 400-meter class NEA will be a great opportunity to future contribute to the IAWN and the same page activity in the future. The number of asteroids found bigger than 140 meters of the size is less than 50% of the known model value so far. For the planetary defense, the most important task is to detect threatening asteroids which can cause a worldwide disaster, as many as possible. Currently, KASI is building a 1.5 meter class wide field asteroid survey telescopes in the southern hemisphere, dedicating to PHA discovery. The cooperation of Catalina Sky Survey program and the KASI has been ongoing. The collaboration of Catalina Sky Survey facility located in the northern hemisphere and the KASI's asteroid survey telescopes with similar capability in the southern hemisphere is expected to create a very productive contribution on PHA finding and planetary defense. Thank you again to UNOSA and all the participating space agents in the panel discussion today. Thank you.
Okay, thank you, Director Park. Now we'll have a turn the floor over to Rolf Denzing, who is the Director of Operations at the European Space Agency, under which their space safety program is managed.
Rolf, you're muted.
Thanks, Detlef, and thanks, Lindley, for the introduction, and thanks to the host for having ESA participate so prominently in this conference. Now, asked about what ESA is doing in the area of planetary defense, let me first of all point out that we have a very prominent planetary defense office in ESA, actually headed by the one and only Detlef Koschny. And so 15 office people are there to prominently contribute to this conference with presentations. And also previously by the Vice Administrator of NASA, the DART mission was mentioned, and ESA is quite a sizable part of it. So NASA would deploy the impactor on the DD Moon, and ESA would do the analysis afterwards with our HERA mission. And I believe we even had a dedicated mission on HERA earlier this week. So we're doing something. Actually, we have just refurbished our NEO Coordination Center, which is hosted in our center in Rome, the ESA Center in Rome, called ESRIN. Plus, we are about to establish a wider space safety center in the European Space Operations Center in Darmstadt, which will not only address the threat from near-Earth objects, but also other hazards originating in space, such as space debris and such as space weather, where we're also very well cooperating with our US friends. Of course, we're also deeply involved in same page, also to be under the chairship of ESA. And I understand that Gerhard Trollsagen, former ESA colleague, who knows each and every asteroid by name, if I remember right, he has just been reporting back on activities to the UN on this. And to IAWN, of course, we are a member also. Now, what do I think can be improved in the future? First of all, I must compliment people being active in this area. This is highly relevant. And I know that you all have ideas on what can be done hardware-wise. So I leave this up to you. What I believe what it needs is we need even more political coordination, political visibility, and political attention to really be prepared for the real case. It needs international coordination, and we need missions beyond that, beyond the first ever asteroid deflection demonstrator. And the Chelyabinsk event was mentioned previously. Events like this statistically happen about every 5 years. And so I'm firmly convinced the question is not if, but when a populated area will be struck. And we need to be prepared for this. This is not a game that we are playing. This is about the protection of humankind and the planet. It's no less than humankind and our planet that is on the line. And therefore I have great respect and admiration for you experts for what you are doing. Thank you very much.
Thank you so much, Rolf, for that. Thank you for being here. And we heard already before from the video message from our JAXA colleague, we have also in our panel now Yoshikawa Makoto, Associate Professor of the Institute of Space and Astronautical Science of JAXA. And Makoto, you also will address in a bit more detail the thoughts of JAXA on our topic. Go ahead.
Okay, thank you, Detlef. I'm Makoto Yoshikawa from JAXA, and I will talk on behalf of Director Kuninaka. Let me talk about the situation of JAXA a little more. As Director Kuninaka said in his video, JAXA has 2 asteroid missions, Hayabusa and Hayabusa 2. The targets of these missions are asteroid Itokawa and Ryugu. These are small near-Earth objects. Now we have understood the physical natures of these NEO quite well. As for Hayabusa 2, we have the samples of Ryugu now, and we will soon start the analysis of the samples. JAXA has a small observatory that is called Visay Space Gas Center. The main work of this center is to observe space debris, but we also observe asteroids and NEOs. And one of the JAXA members has developed a special technique for discovering small, fast-moving objects, such as asteroids approaching the Earth. And speaking of future mission, JAXA has a collaboration with Hera mission of ESA, and we will provide one science instrument to Hera. And JAXA and Hayabusa 2 is on the way to the new target, which is a very small NEO. We are also planning Destiny Plus mission, which is Phaeton flyby mission. Finally, JAXA is one of the members of same page, and we hosted PDC in 2017. So in this way, JAXA cooperating with many issues of planetary defense. Okay, thank you very much for your attention.
Thank you very much, Makoto. We appreciate all the efforts that JAXA is doing in this area. And congratulations on the success of the Hayabusa 2 sample return mission. Now we're here from our host country for this planetary defense conference, Klaus Seiner, who is the managing director of the Austrian Research Promotion Agency. You have the floor.
Lindley, thank you very much for your kind words. I would like to thank the organizers of this important workshop. It's, of course, the cooperation ESA. Thank you very much to the ESA friends, but also, of course, to Simonetta. Thank you very much for taking the initiative. Well, the engagement of Austria in planetary defense can be seen as Austria's overall contribution and support to space safety. Austria has contributed to ESA's space safety program right from the beginning, and this is now more than a decade ago. Currently, we are working on an update of our own national space strategy, and I can assure you that the context of planetary defense will play an important role in our deliberations. Based on our technological expertise, we have the focus on ongoing missions and on future missions. As Lindley, you rightly asked at the beginning, what is now and what will come next. So our current contribution, for instance, to the ESA Hera mission is a 3D reconstruction asset specifically for the asteroid impact region to provide a visualization tool for science teams and to assist in planning scientific observations. For future missions, we have 2 areas of interest. One is astronomical instruments, including optical telescopes, and we are working intensively on electric propulsion systems for efficient orbit changing maneuvers, specifically in deep space. So in the international fora, we are active in the SAMPAC group, of course. We contribute there in the field of specialization on asteroid impact assessment. We have an expert on the legal working group, on the subgroup of the legal reporting working group. And we follow the deliberations quite closely. Austria also sees itself as a platform enabler in the field of the cooperative efforts, which were mentioned rightly. So we give there a great importance, specifically as a host country, to UN COPUS. So Austria looks forward to the continuing of the discussion and deliberations on the related planetary defense context on UN COPUS and its two subcommittees taking place in the United Nations office in Vienna. We also do believe that the European Space Policy Institute, ESPI, located also in Vienna, is able to play a strong role and be a forum for international discussions and exchanges in the subject context of planetary defense. And last but not least, we are also supporting ESA's program board on space situational awareness. At the moment, Stefan Meyer is chairing this board and giving in a lot of attention because this subject is important for you. So, Lindley, summing up, being a small space nation, nevertheless, we address this topic seriously and we give it a quite strong importance. Thank you very much.
Thank you very much, Dr. Pseiner, for these words. Let me, before we open the discussion round, ask whether we may have a representative of the Mexican Space Agency in the panel now, because we skipped over you in the beginning. I don't think that's the case. So then I think we have some time for discussions and questions. So for the audience, please remember, put your questions in the chat and address them to everybody. So send to everyone rather than to participants, so that everybody can see it. Yeah, I would need some help here because I'm not sure I'm reading everything. So
yeah, okay, Detlef. One comment I'd like to make quickly on Klaus's remarks is that just because you're a small country and have a smaller footprint in space programs doesn't mean you can't make significant contributions in planetary defense. Some of our observations that are critical for determining the orbits of near-Earth objects that can represent a hazard to the Earth come from very small observatories and some even from amateur astronomers that provide to the overall effort in providing observations to the minor planets and orbit determination. So big isn't necessarily necessary in this business. As I always like to say, planetary defense is a team sport, and it takes skills from all over. So with that, we do have about 10, 15 minutes for discussion. Some of the issues that have been talked about at this conference is so if we had a threatening object detected and headed toward Earth, how exactly would the space agencies be able to get together and develop a internationally coordinated plan to determine what the best way is to respond to such a threat? Do any of you have any thoughts on that?
Hey, Lindley, this is Steve Jerzik. Hey, so, one of the things we've talked about is improving our ability to detect and characterize near-Earth asteroids. And so, it's really important to be able to improve our detection and characterization capabilities, both from observatories here on Earth as well as space-based observatories. And so the response, our response and across agencies will evolve as those detection and calculation capabilities evolve. As everyone's seen with the exercise this week, if we don't detect an asteroid until it's fairly close with not a lot of time, there's not much we can do. But we need to evolve capabilities so we have years or even a decade more time after we detect and characterize for agencies then to get together and cooperate and determine what the best course of action is amongst the international space agencies, and also work with our emergency response, depending on the nature of the threat, work with our emergency response organizations nationally, and even coordinating nationally on how we would respond if there wasn't a way to mitigate. So yeah, right now it's because of our somewhat limited capability in detection and characterization. It's our response is more challenging and somewhat more ad hoc, right? But it's really important to improve our capabilities, so then we can have the time to collaborate, discuss, get more data, process that data, and really work collaboratively to figure out the best approach to avoid an impact.
Okay, thank you, Steve. I understand that we now have a representative of the Mexican Space Agency, Julio Castillo, that is available to speak.
Hi, Lindley. I think he was to join, but I don't see him among the panelists. Julio, can you hear us? Maybe you just proceed.
Okay, well, that's live TV, right? Okay, well, I solicit thoughts from many of the other representatives, heads of agencies that we have here. Go ahead and jump in.
Lindley, may I respond to Stephen's?
Yes, Claude.
Thank you very much. Just one learning I take from the message I just got from Stephen is due to this number of uncertainties and due to the level of in-depth preparation we have distributed amongst us, I think one common denominator is working on relevant and critical technologies, independent of the mission which will and can possibly take place later on. And so this is one safe side of the coin to prepare the technology readiness. Thank you.
Yes, very much so, and that is the basis of the same page. Go ahead, Dalla.
Yeah, I see we have now questions coming in from the chat. The first question would be from Artash Nat. COVID-19 global pandemic has shown that when global threat strikes, UN agencies such as the WHO and now it disappeared, it can spur countries to act, but then nationalism takes over. We have seen that in terms of vaccine nationalism and underfunding of global initiatives. What lessons does it hold for planetary defense if such a threat materializes? Would one of the panelists want to answer that? I think it's more really a question to more us on the technical level, but I don't know. Lindley, you want to say something there?
Well, I think that points out the importance of us talking together and working together, collaborating on technologies and techniques well before any actual threat is identified, so that we have already set up the avenues, channels of communication, if you will, between our agencies and our governments on what the nature of the threat and what a viable response might be.
Yeah. I now do see Julio Castillo with video, and the question is, Julio, were you prepared or did you want to say a few words on behalf of your country's space agency?
Thank you very much, sir. Yes, I would like to speak on behalf of space agency and to Leros, our general director, if or is the shape. Thank you.
I'm having issues with the audio here.
Can you hear me now? Can you hear me?
Now it
Can you
seems
hear
to
me?
Yes, now you're back.
Okay. Okay. So you let me know if I'm ready now.
No, go ahead. Let's try again.
Okay, thank you very much. So I appreciate the kind invitation to participate in this remarkable and relevant conference organized by the International Academy of Astronautics and the United Nations Office for Outer Space Affairs. Based on the scientific evidence, the greatest impact of an asteroid on Earth happened approximately 66 million years ago, which marked a major boundary in the Earth's history known as the KT, or Cretaceous Tertiary boundary, and also marked the end of the Mesozoic era. According to the evidence, the above happened in southeast Mexico, what is called now the Yucatan Peninsula, in a region called as Chicxulub crater, which in Mayan language means the devil's tree. This crater creates a diameter of more than 108 kilometers, and it's reckoned that the meteor that hit at the time on the Earth's surface had a diameter of 11 kilometers. As we all know, the above is considered to have extinguished most life on Earth that were existing. Having said that, near-Earth objects are a real threat to our planet and existing life on Earth. Needless to say that humanity has learned one of the most painful lessons ever in the past year due to the appearance of COVID-19. By early 2019, we never thought that something invisible to human eye was going to be able to change, in the wink of an eye, our way of life, bringing death and destabilization to the international system as we know. In the same lines, I believe that we should increase our level of awareness in a very serious way to the potential threat of a near-Earth object. As an example, we know that the Apophis asteroid, which is considered to have a diameter of approximately 340 meters, and it is estimated that by 2029 it will approach about 31,000 kilometers from the surface of Earth, which according to scientists is a potential danger. Apart from that, according to the information available, there are over 25,000 known near-Earth asteroids, NEAs, over 100 short near comets, NEXs, and a number of solar orbiting meteoroids large enough to be tackled in space before striking the Earth. So thank you very much for the time, and this was my statement.
Thank you very much. All right.
Okay, we have about 5 minutes. Maybe we go touch base with the panel here and see if anybody has any last thoughts. President Demura, Brazilian Space Agency.
You're on mute.
Thank you very much for the opportunity. It's really inspiring to exchange some thoughts with you. We have heard about planning, researching, mitigation, legal aspects. So we do have a myriad of challenges to overcome. We also should link the scientific work of the astronomers to our real capability of reacting to those challenges. So I would repeat my initial words. I believe here in Brazil, we believe that the role of UNOSA is really very important because they have the ability to join all those great and small countries, advanced and in the middle of the way countries. So we should join our capabilities, scientific engineering, and so many others. And here in Brazil, we are open to improve our participation in this forum. Thank you very much. Success to all of you.
Thank you very much for those remarks. I understand that the delegation from China has a few remarks they'd like to make too.
Okay, thank you. And it's midnight in China, but we are very pleased to give us small remarks regarding to the small bodies prevention. And CNSA is now preparing some office or organization to coordinate regarding to the mission to the space. And especially for the small body missions, we are open this, now the status for the mission is near finish of the feasibility study. We are open for international, if any space agency are interested, we can to more detailed discussion. And for the international organization for this prevention, and I think we are thinking to some organization, international organization, for the defense, United Defense Mechanism, which means we normally, for example, each year or each half year, we can organize some platform for all the space agency to talk the status for its agency and to talk to detail and they are interesting, and to build mutual assistance technically, or maybe including the rules, the regulations. Of course, based on a shared monitor data and alarm and the monitor data, including the data from the space mission or the data from the ground facility, both in the data from space and the ground observation. And anyway, where we are open, we are welcome. We can maybe establish a mutual or multilateral organization to share everything. Thank you very much.
Okay, thank you. And a lot of the data is actually already shared. We have observations from Chinese observatories that come into the Minor Planet Center on asteroids on a regular basis. Okay, with that, Detlef, did you have anything else before we wrap up?
No, I think in the interest of time, I think we should say thank you to everybody for your participation, and let's continue working together like this. And latest in 2 years from now, we will meet in person again, and then we can hopefully proudly look back to 2 years of fantastic progress.
Yes, I echo remarks, and I thank all of the heads and representatives from the space agencies around the world in your interest and participation. With that, we'll turn it back to the chair of the conference.
Thank you, Lindley, Detlef, and
Thank
a
you.
truly international panel of government space agency leaders for captivating and path-setting discussion, emphasizing the importance of global communication, cooperation, and coordination on science and discovery, and help address open questions on the asteroid hazard.
Take a moment to highlight all the great e-posters that folks have submitted online and encourage people to view those at their leisure. And we will have a Zoom session later today to have a live Q&A on the e-posters. Our first talk is by Mary Berkey et al., Progress on Developing a Simplified Model of Energy Deposition for Nuclear Mitigation Missions. Mary, go ahead.
Is my audio okay?
Yep.
Okay. So yeah, thank you. Like Megan said, today I'm going to talk about progress I've been making on constructing an analytical model for initializing the X-ray energy deposition in nuclear mitigation simulations. And next slide. And though a kinetic impactor is preferable, utilizing a nuclear device, as we've heard the past few days, is an alternate option. We would most likely use this option in the event the asteroid is either too big for a kinetic impactor, or much like the exercise, if we're on a time crunch, in which case we may be sending a mitigation mission to an asteroid without having a clear idea of what properties it has. That said, a nuclear device is a very versatile mission option. Once detonated next to the asteroid, it will, whoops, wait.
Sorry.
Once you detonate the device next to the asteroid, it will release a few neutrons and gamma rays, but most of the energy will be from soft X-rays. The radiation will illuminate the surface of the asteroid and cause material to rapidly heat up, vaporize, and be ejected. If you want to keep the asteroid intact and just give it a push, you can detonate the device at a standoff distance for a successful deflection mission. If you want to blow it into tiny, fast-moving, and non-threatening bits, then you can bring a big device as close as you can to the asteroid for a successful disruption mission. However, if you end up somewhere in between, with a few large, slow-moving pieces that are still heading towards Earth, that would be a failed mission and possibly a disaster. So it's important to understand the risks and uncertainties beforehand, which you can do by simulation. Next slide. However, this particular problem is very, very difficult to simulate. The X-ray energy deposition happens on the scale of centimeters and microseconds and requires radiation transport, which is expensive to simulate. Meanwhile, the hydrodynamic response of the asteroid happens on the scale of hundreds of meters and could take anywhere from seconds to weeks, depending on what you're trying to do. Thus, a good simplification is to divide the problem into two parts. First, generate an energy deposition based on a full radiation hydrodynamics code, and then use it to initialize a less expensive hydrodynamics code such as Spheral. Next slide. Up until this point, as an example with Patrick King's presentation earlier today, we've been utilizing an energy deposition taken from Mercury, which is a Monte Carlo particle transport code. And though these depositions didn't capture all of the physics and time dependencies, such as re-radiation, they can easily be fit to a summed exponential that is scalable by the fluence and the angle of incidence. And if you know the total re-radiation, or it could be guessed or obtained elsewhere, then that would be considered a decent approximation. However, Nick Gentili, who also gave a talk this morning, he recently joined our group and has been helping us build up some capabilities in another code called CUL, which is a full radiation hydrodynamics code and can capture the full physics of X-ray energy deposition. We eventually found, by comparing the blow-off momentum between the full CUL calculations and then CUL initialized within Mercury profile, that even if the profile was scaled to the correct radiation, the discrepancies could be well over 50%, especially in the high fluence cases. Next slide. So that said, we still need to actually create an energy deposition model that works well in as many cases as possible. So rather than using Mercury, I'm going to try and take an energy deposition time slice directly from CUL to make my model. Eventually, when we publish this, we're hoping to cover silicon dioxide, forced ice, and iron in terms of materials, and use a 1 keV blackbody source with a variety of yields per area, or fluences, that range from just melting a small surface layer at low fluence, or a full disruption case, or high fluence. A few first pass tests in 1D can be seen on the right for the 4 materials at 3 different fluences, where we've varied the incident angle in the scatter plot on the left, and then the duration of the radiation coming from the device, which is the scatter plot on the right. Each dot represents the % deviation between a simulation initialized with an energy deposition taken 5 nanoseconds after the source is shut off, and the pure call calculation. The cases that we care about the most are the black dots, the normal incidence at the 10 nanosecond source. And for the most part, they stay within 20% of the full call calculations, so this method has some promise. And for the remainder of this presentation, just because I haven't done all the other materials yet, I'll only be looking at the silicon dioxide case. And I'm going to use a test geometry with a device at a 50-meter standoff distance and an asteroid that's 300 meters across. Next slide. So the simulations that I showed before were in 1D, but we wanted to make sure that our true energy deposition, which happens over a 3D surface, matches roughly what we would at least see in 2D. And based on the plot on the right, we found pretty close agreement between the 2 dimensions in terms of both the energy deposition, and then the blow-off momentum can be seen on the table on the right. And there's close agreement between the 2. That said, we're still upgrading our 1D cull deck, and we're hoping to have a time-dependent source implemented in there soon. And once we have that, the energy deposition profile should match even more closely. So that said, since these already agree so closely, I'm going to use the less resource intense 1D data to build up my my deposition profile in 2D. So next slide. Okay. So after trying out various functions, I found that a piecewise combination of an ellipse, an exponential, and a linear function with a cutoff to be the best way for fitting the deposition thermal and shock waves that you can see in the plot on the left. Some of my first pass fitting to 1D deposition profiles over 10 different angles of incidence for the high and low fluence cases are plotted on the slide as well. On the left is what the actual energy deposition data looks like. The middle is my functional fit, and the right is a rough residual between the 2. And these surfaces are only fit for the test case geometry, so eventually I will have to do a more global fit on a full range of fluence and source duration combinations, which are dependent on on all different geometries, and that'll eventually need to be done. Next slide. However, just as a first pass, the results seem to be very successful. A comparison of the blow-off momentum between full 2D call calculations and ones with the deposited function yield differences of 7, 30, 2%, and then 9% for the 4 different fluence cases as seen on the table. For fun, I also added an exercise case, which is our most likely PDC asteroid, which a few days ago was 120 meters across, and then with an attempted disruption of 1 megatons at 9 meter standoff distance, which is our high fluence. And though the high fluence fitting function was not made for this exercise geometry, the final deposited blow-off momentum was still within 50% of the true value from the full 2D call calculation. So the machinery is well underway, and all that really remains is to keep tying up loose ends and to do proper global fittings to all of the remaining materials. Next slide. So here are my conclusions. As it turns out, you do need a full rad hydro simulation to handle the X-ray energy deposition. The analytical model of the deposition is progressing quickly, though, and once it's finished, the simulating nuclear mitigation missions will be both easier and more reliable. The movie that's playing is our first pass at putting the new cull deposition into spheral, which is an SPH hydrocode, for the 2021 PDC exercise asteroid. As you can see, it's being disrupted quite effectively, and colored material has positive velocity that's heading towards the right of the slide. The plot on the left is a comparison of the change in velocity between our original Mercury deposition and the cull deposition in spheral. And there's a big difference, so that means the effort's been worth it. And with that, I'm happy to answer any questions in the chat and or answer any at the end of the session. And thank you for your attention.
Great, thank you, Mary. All right, we'll move on to next speaker, which is Angela Stickle, my co-chair. And if we could transition back to, yes, other people presenting. Great.
All right,
Right, so
thanks.
take it away.
Thanks, Megan. So thanks everybody for coming back for our second part of this session. If you can go to the next slide, please. And we're talking about a lot of work that was done by a lot of people that you saw on the author list to help us prepare for the DART impact. And so just to remind you, DART is scheduled to launch this fall, and we will be impacting into Dimorphos, which is the moon of Didymos, and attempting to change the period of its orbit around the Didymos primary and measure that to better understand how effective the kinetic impactor is in this case. And this is a really important experiment for a couple of reasons. It's the first time we will have done this for real, at a real scale for a kinetic impactor. But if you go to the next slide, please. It also represents, one of only a handful of planetary scale impact experiments that we have in our sort of experimental knowledge. So DART is joining Deep Impact and LCROSS and to kind of tangentially the SCI impact as well. That's a slightly smaller scale to show us, what really happens at real planetary scales when you do these impacts. And these are really important because they give us a very well-controlled experiment, at least on the impactor side. So we know a lot about the DART spacecraft as we are building it, right? We know what it's made of, we know its size, we know where things are, and what things are going to look like when they impact. But what we don't know, if you go to the next slide, please, is going to hit. We know very little about the object Dimorphos, actually. We have some information about its size, and we think we know kind of the composition that it's made of, but it could be sort of a wide range of different things. It could have a wide range of shapes. It could have different slopes and things like that, and we don't really know what we're going to hit until we get very close to the object. And if you go to the next slide, I apologize for these sort of animation slides, but it's really important to understand the experiment and understand kind of what happens is understanding Dimorphos and kind of filling in that other half of the sort of well-controlled experiment parameter space. So we want to understand sort of what the material properties and what the structure of Dimorphos are so that we can really get a good estimate for beta. And if you go to the next slide, and this is because beta really is telling us, how much of a deflection we're actually getting. And so it can range from something that's very small, where maybe you don't have a lot of ejecta and you don't have a big crater that's formed for a certain type of material, all the way up into having a lot of ejecta and a large momentum increase and a large crater that's formed. And we don't know kind of where Dimorphos is going to fall within this range, which, makes it a little bit harder to predict. And so this is, of course, where impact simulations come in. And we've seen a lot of great examples of the ways that we're trying to better understand that this week. And one of the things that the DART impact modeling working group is doing is sort of testing how well those models have taught us what to expect. So if you go to the next slide, please. And we're doing this in what we're calling the DART impact modeling inverse test. So inverse problems are really useful, of course, in that they tell us about parameters that we can't directly observe, right? You can see an effect of something and back out, the best fit model parameters that would have caused that effect. So we observe a deflection and we can do the inverse problem and pick up kind of what the model parameters were, what the strength parameters were, the structure, the porosity, things like that of Dimorphos. And there's a few different ways that you can do this. A very common one is sort of trial and error, right? You pick one set of properties, you run the simulation and see if it matches. And you can kind of iterate back and forth based on sort of a priori knowledge or kind of your intuition on how things affect There are lots of different types of optimization algorithms for doing inverse problems as well. Cody Raskin, who's talking next, will discuss one way that they're doing this at Lawrence Livermore to look at these sorts of things, and also for the Dart inverse problem. And so we're really using this to answer a few questions. One is like, what are the expected uncertainties following the Dart impact? So given a set of material properties that Dimorphos has, how well can we predict what the momentum enhancement factor is, and how do the different target properties affect this prediction? We want to know how well the impact scenario can be recreated from very limited information. This is also sort of a test of our tools in our pipeline right now for the DART mission. Do we have currently the correct data analysis procedures and handoffs in order to do this adequately, or do we need to adjust things before the actual impact occurs? And then lastly, we're trying to understand how long these simulations take so that we have a better idea for planning and how many different sorts of simulations we need to run following the DART impact. So if you go to the next slide, please. The way we've set this up is to have sort of a different type of controlled experiments. We have one set of folks on our team who are providing a truth model, and they are doing an end-to-end impact simulation and getting our result. And then we are taking limited information from that, so just kind of the impact geometries and the what DART will measure, which is the period change, and providing that to the rest of the team. And the rest of the team then takes that information, which is essentially what we will receive after the DART impact, and then do this inverse problem to turn it into a deflection velocity and a beta to try to back out material properties. And we're testing to see how well we can actually match the initial sort of truth model. So I'm going to run through quickly just the first test that we did. So if you go to the next slide, this was a very simple test. We tried to make it simple. We weren't trying to trick people on this one. We just assumed an oblate spheroid for Dimorphos and ran both 2D and 3D simulations. These are some examples in CTH. We also have collaborators at Los Alamos who ran it in their flag code. And we provided the sort of adventurers team, which is what we're calling the rest of the team that are doing this problem, the properties of the impactor, very limited target properties. We told them it was sort of a coherent basalt type of a material based on what you might see from images, what the impact geometry was, and then what the measured deflection velocity. And if you go to the next case, or sorry, next slide. Yes, thank you. And this was actually what the truth model was, and the results were. So this was not provided to the team, but in this case, we had a deflection velocity of about 0.1 centimeters per second. So this is sort of a DART scale type impact. And we ended up with a crater that was a few meters wide and about a meter deep. And so we kept these results to the crater size to ourselves, and then asked the team to come back with what they thought happened. If you go to the next slide, we know that a range of different strength and porosity values can give us the same momentum enhancement. And so we were expecting maybe not quite, we were expecting a range of values to come back from the team. So this is some simulations that were done by Sabina Radican. And she talked a little bit about some of these things, similar things earlier, but you can look at strength properties. So if you look at this upper left plot, you can look at sort of strength properties and porosity properties. And for a given combination, you might get one value of beta. And for a different combination, you might also get that value of beta. So it's a non-unique solution, which does make it a little bit tricky. And so we were really interested to see what the team did and how they kind of dealt with this uncertainty. So if you go to the next slide, and we sort of got what we expected. So this is an example showing you a few different things. So I have put on here the depth, the diameter, and the sort of strength properties that the teams came back with. And you can see as we kind of thought might happen, there is sort of a range of properties that were found to give us that same beta and deflection velocity. Depending on, if you have a 2D or a 3D model, that affected it a little bit. And so, we kind of see the scatter, which we expect because it was, as I just said, a non-unique problem. However, everybody got pretty close to, they're all kind of within the same general sense of each other. And, had we given the team sort of more information later, like if we gave them the crater size, you can see you might be able to like narrow down. I'm pointing at my screen like you guys can see it. You might be able to narrow down which of these is the correct one. So the next slide. So that was the initial test, and right now we are in the middle of conducting our second exercise to provide a more stressing case. I promise I'm almost done, Megan. And we're going to use a much more complicated impact target and use some simulations that the DART team has come up with in order to see how well we can then recreate this using this more complicated target. So if you go to the next slide, stay tuned for those results. That's underway. So we have a few implications for DART. It's really important the communication is clear end to end. We had to kind of go back and answer some questions during this. We know that beta is not uniquely tied to one set of material parameters, and so having other information is really important to limit the range of possible values or to constrain it after the fact. But given all of that, we're still able to reproduce beta values within about 10 or 15% of the truth value, which I think is great. And we're still optimizing how we want to do this following the impact, so stay tuned. But I think this is a really good test, and I want to thank the team for playing along and doing so well. And if folks have questions about this or the setup or want to play in the second one, let me know. So
great, thank you, Angela. And then do you want to introduce the next speaker?
Yeah, thanks. So our next speaker is Cody Raskin, and he will be talking about accelerated route finding for the DART inverse test using machine learning decision trees. So Cody, take it away.
Can you hear me?
Yes.
Okay, good. So let's just go ahead and start on the first slide. So yeah, this slide. So just to sort of rehash what Angela was saying, this is from Livermore, we worked on the DART inverse test. And what we were given was that it was a triaxial rocky body. It had a constant density with no porosity. We were given the impactor mass and momentum and the impact angle, which was that it had no angle. And from my point of view, I wanted to vary as few parameters as possible to try to drive to the observed, so to speak, delta V. And so I varied yield strength and density in my simulation. So let's go to the next slide. And I did this in 3D with SPH using the Tillotson equation of state. I didn't have any damage model in the simulations that I'm going to present now, because if I ever included a damage model in these simulations, the beta was way too high, and I couldn't get anywhere near the delta V that we were trying to reproduce. I also, with guidance from the red team, used just monolithic material with no boulder-like inclusions. And in our implementation, we can ratio the resolution away from the impact site so that we can have really fine resolution at the impact site. So our resolution was 10 centimeters there. And because I wanted to treat it like a real inverse test, I didn't assume any information about the total mass or the density of Dimorphos. I had only the volume, and all other things were free to move about in the simulations. So let's go to the next slide. Let's actually skip this slide. Let's go to the next one as well. Okay, so typically when you're doing inverse problems, and at Livermore we have a lot of experience doing inverse problems in other applications, you have some arbitrarily large input space, that's the blue box here, and through simulations you map it to some arbitrarily large output space, and the goal you're trying to reach is that green circle there. It's some small subset of your output space. But you don't know a priori what that mapping is. Usually, we don't want to treat our simulations like black boxes, but they're usually very nonlinear processes that get you from input to output. So what you would do is you would run a few simulations, see where you are in the output space, and then that would inform your guesses as to the next inputs to try, and you would keep cycling this process over and over to try to get you closer to the green circle. Or if you're lazy, you just run thousands and thousands of simulations and come back a month later and hope that one of them is inside the green circle. And so I wanted to try something a little bit more intelligent. There's some methods that I've been adapting to inverse problems at Livermore using machine learning to drive this cycle process in a more intelligent way. So let's go to the next slide. And I wanted to apply those to this problem since this was a fairly simple tabletop problem that would test this method pretty well. And so I used a decision tree regressor because it's really fast and it's a supervised machine learning algorithm, which just means that the data is labeled so that it knows what's in and what's out and what it's trying to get to. And one of its benefits is that it's not you don't have a chosen parametric equation or function for mapping the input to the output that it is trying to fit parameters to. It just doesn't know anything about how those match, and it doesn't make any assumptions. So that's good, but it usually requires a really large data set to be accurate. On the other hand, it's steerable, but then on the other hand, it's very naive. So let's go to the next slide. And you might be asking, is applying machine learning to what is essentially just 2 inputs to 1 output, is that overkill? Probably in this case, but in the future it wouldn't be. In the future we might have a lot more input and output parameters. And if you're dealing with these multidimensional spaces, it can be really difficult for humans to spot any trends in there. And if you were just doing guessing and checking, you may never get into that green circle. But it's easy for computers to see these things. And also computer cycles are really cheap. So if you're letting a machine learning algorithm run all your simulations for you, you can spend your own time doing something more valuable because human cycles aren't cheap. So let's go to the next slide. So initially I just did a regular Cartesian scan of density and maximum yield strength. And even in the initial scan, I already had 2 successes, 2 correct simulations with the correct delta V. And that was actually pretty good because then that meant that the machine learning algorithm, the decision tree, could sort of anchor on those 2 points to try to figure out where to go next. So if we go to the next slide, you can see what the computer is doing now is the light blue area is everywhere it thinks those 2 parameters yield the correct delta V. And like I mentioned, it requires a large data set to be accurate, and this is probably not accurate, right? This is way too much space in the input space that it thinks is going to give me the correct result. But it is steerable, like I said. So I'm steering it with a Mitchell's best sampling algorithm, which just uses a tree code to figure out where's the best place to run the next simulation. And the nice thing about this design is I didn't have to do any of this. I only ran the initial Cartesian scan and I walked away. And the machine learning algorithm decided this light blue space is the space I want to explore. And the triangles are the runs I want to run next. And it submitted them on its own. So if we go to the next slide, red dots here means it was successful. It got the correct delta V. And the black crosses are unsuccessful simulations that had a delta V that wasn't inside the box. So now it's refined its prediction space. It's a lot smaller. And, to a human eye, you can kind of already see, it's obvious there's some sort of curve here. But, maybe if this was multi-dimensional space, you wouldn't be certain that there weren't islands of correct input space. So it's just best to just let the computer do its thing. And again, I wasn't watching this. So now it had refined its prediction space, chose new simulations to run. So let's go to the next slide. And now it got some more successes and some more failures. It refined its prediction space again. So let's go to the next slide. And then we'll go to the next slide. This is, again, it's refining its space. And now at the end here, this is what I came back to. Oh, sorry. This is what I came back to after, let's go back to the previous slide. after about a week of unattended running where the computer was submitting its own jobs and checking the result, all of these red dots were successful simulations, successful in the sense that it got the correct delta V. And so it has mapped out, it thinks there's 2 islands of correct inputs here, but we can use our human intelligence at this point to say there's just a curve, there's a function of density and strength that maps to that correct delta V. So let's go to the next slide now. So for some key judgments from the inverse test, as an inverse test, for Livermore, we found that these synthetic observations were most consistent with this density range and this strength range. Like I mentioned before, I only changed maximum yield strength. I'll come back to, I could choose something else as well. I didn't include any damage model because if I did, I had to make it something unlike rock or I had to make it something unlike damage. And I didn't assess porosity because of guidance from the red team. So let's go to the next slide for the major things to try next. So like I said, density and maximum yield strength, they're probably not a sufficient parameter set by themselves because there's a curve of possible choices that yield the same output. I could also have used Y naught and porosity as input parameters. And maybe we could use those in the next one. And with no damage model, it's simplifying, but it's not realistic. And then on the output side, delta V doesn't need to be the only output parameter. We could also use crater size that we might get from Hera, or we could use velocity dispersion of the ejected debris that we would get from LichCube, or we could use the flavor profile of the debris that we would get from Guy Fieri. All of these things could be our output parameters that we could use to drive the decision tree and get a much more robust and maybe more constrained answer in the future. And that's all I've got.
Thanks, Cody. I like your last point there. All right, so if you've got questions for Cody, please put them in the chat. And we'll move on now to our next presenter. Mallory DeCosta will be talking about projectile geometry effects on momentum enhancement of hypervelocity impact simulations. Take it away, Mallory.
Let me start my timer. Hi, I'm Mallory DeCosta from the Johns Hopkins Applied Physics Lab, and my talk discusses an investigation into the effects of projectile geometry on momentum transfer predictions for hypervelocity impacts. This investigation is in support of NASA's DART mission, NASA's first planetary defense mission, and is meant to provide a roadmap to efficiently simulate the impact with, otherwise computationally expensive models as we've seen just previously. Next slide, please. So cratering processes and ejected distributions following a hypervelocity impact are directly related to the momentum enhancement. The literature reported on this is really quite limited. On the right, I'm showing some experimental results published from a 2017 study by Akita et al. That looked at the effect of 5 different projectile shapes on momentum enhancement. This was an experimental investigation. They found that when the input momentum was held constant, the highest beta values were achieved for the more complex looking projectiles, so mainly like the cup and the punch shape. Interestingly, the most ejecta mass was generated by the spherical projectile, which actually resulted in sort of smaller betas. So this is a bit of a counterintuitive result because we expect ejecta mass to be strongly correlated to beta. Additionally, it's also important to note that the scale of the DART impact is quite different than what was experimentally investigated here, where the input momentum for DART is 6 orders of magnitude larger. So since it's not possible to obtain experimental results on the scale of DART, we've decided to perform a simulation study using Sandia's CTH hydrocode to test the effects of projectile shape on the momentum enhancement. And, this is really done generally for simplicity and to conserve computational costs. Simulations of the DART impact are often used we typically use like a solid or a porous aluminum spherical impactor to represent the DART spacecraft. However, the DART spacecraft structure is much more complex, and the effects caused by the spacecraft geometry on both crater size and morphology on the momentum enhancement are quite unknown. Next slide, please. So here I'm showing the general overview of how we set up our simulations in CTH. We modeled the Dimorphos target as a 30% porous basalt sphere and chose standard equations of state and relevant material models to describe it. We modeled a aluminum spherical impactor in both 2D and 3D, and also the full three-dimensional DART spacecraft. At impact, we had the solar panel arrays fully extended. I'm also showing a nice zoom in of the spacecraft bus, where you can clearly see that we capture the complexity of the spacecraft, including the Draco camera, the Next-C propulsion system. And you can see that the bus is made up of many materials and complex shapes. Next slide, please. So this figure here shows the temporal evolution of the momentum enhancement factor. We see that the 2D and the three-dimensional results for the fully dense aluminum spheres overlap quite nicely. And this is good. It sort of indicates consistencies within our input decks, and also, the lack of a dimensionality effect, which we saw previously in the inverse test. Notably, we see that the DART spacecraft results in a approximately 10% smaller beta compared to the fully dense sphere at about 12.5 milliseconds after impact. For reference, we also modeled a highly porous aluminum sphere projectile in order to see if this might be a better representation of the spacecraft impactor. We chose to induce a porosity of 90% in order to achieve an effective density that approaches that of the DART spacecraft. We see that the porous 2D sphere does reduce the beta compared to the fully dense spherical projectile. However, it still overpredicts the beta by about 5%. While a difference in 5% is quite small, we really don't recommend that using a highly porous 2D spherical impactor is a good representation of the full DART spacecraft, because it's actually quite difficult to choose the appropriate material models to realistically represent the material in the code. And you can kind of see this is represented by the very different temporal profile that we generate for the 2D porous impactor compared to the other impactor geometries. Next slide, please. So here I'm showing a snapshot of the craters at about 12 milliseconds after impact by each projectile. We see that the crater for the three-dimensional spacecraft is much different than that of the sphere. In contrast to a singular transient crater that's wider than it is deep, the spacecraft produces a much more complicated looking crater shape that contains sort of a single asymmetrical main crater that's generated from the spacecraft bus, and then also two side lobe craters that occurs from the solar arrays. Next slide, please. So here's a more quantitative representation of the craters showing the temporal evolution of the width and the depth. The 3D sphere is shown in blue, the 2D sphere is shown in green. We see again that the crater profiles are quite similar between the 2D and 3D spherical impactor test cases. The sphere projectile results in a very traditional impact transient crater. And we see that the DART spacecraft crater produced by the bus is much smaller compared to the spherical impactors. Next slide, please. Okay, so the momentum enhancement factor is this equation that's captured there, and it contains components from the input momentum as well as contributions from the ejecta momentum. So in order to understand the ejecta momentum contribution a bit more, Here I plot the cumulative ejecta mass that was generated by each projectile as a function of the ejecta velocity. Each variable has been normalized by the impactor mass and the impactor velocity respectively. I also would like to point out the log scale on both axes. I've drawn a line at a normalized cumulative ejecta mass equal to 1 to kind of help you visualize the results better. Data that falls above this line implies that the projectile generated more ejecta mass than merely the mass of the impactor itself. We can clearly see that the blue line representing the spherical impactor results in significantly more ejecta mass compared to the spacecraft. There also appears to be a larger population of very fast-moving ejecta material. Also an interesting note is that the spacecraft does produce a small population of very fast-moving ejecta that exceeds the range of the ejecta velocities measured for the sphere, as shown by this extension of the data at the right trailing edge. Next slide, please. I'm almost done. So actually, let's just go to the next slide, which is the summary. So in total, we find that the asymmetrical interior of the spacecraft structure, accompanied by the solar panels, affects the crater and ejecta evolution in comparison to a simple sphere projectile. The sphere produces about 3 times more ejecta mass than the spacecraft. We see that the spacecraft does generate some faster moving lightweight ejecta. However, that material contributes very little to beta. Although the sphere only overpredicts beta by about 10%, we caution against using a simplified sphere as an accurate and precise representation of beta that is experienced by the full spacecraft geometry to represent the DART intercept. Thank you for your attention, and sorry for going over time.
Thanks, Mallory.
Great. Could I drive for the last talk and I'll share? Great, thanks. All right, so Mike Owen will be wrapping up this session, speaking on spacecraft geometry effects on cratering and deflection in the DART mission.
Okay, thanks, Megan. Can everybody hear me? Sure it's.
Yep.
Oh, good, okay. Yeah, so this is, go ahead and go to the next slide. This is following on, it's related to the work Mallory was just talking about. We were kind of doing this stuff together. Looking at the effects of spacecraft geometry on what you might expect from the measurable things like beta and crater geometries out of the DART experiment. I did a first pass at this at the last PDC, where I looked at simple spheres, cubes, and a solid spacecraft model that was based on Dawn at the time, where I found that these quantities could be affected by sort of 10 to 15%, with the realistic spacecraft model tending to give you lower betas and smaller craters. And it could also affect the crater morphology. And this year we wanted to kind of finalize that study, with several improvements over what I presented last time. For Spheral, which is the tool I'm using here, I improved material modeling to make the damaged rock behave more like granular materials rather than a strengthless fluid, which is the case a couple of years ago. CTH already had that model, so that was just a Spheral change. And also, the big thing is we have much higher fidelity models of the spacecraft itself. We're using realistic materials. Before, I was just using silicon and aluminum. We're using the realistic CAD geometry. The prior simulations actually modeled the spacecrafts as solids, full density solids, just with a funny shape. And so we shrank the volumes to match the mass. So they were significantly smaller than they should have been. And we're also going to compare a couple different codes for this. I'll be talking about Spheral and show some of Mallory and Dawn's CTH results here. Next slide. Okay, so this is the basic spacecraft model we used. We used some STL models for each part. There's like 50 individual components or so that we created here. And there's about 4 material models that you use for the different components. There's aluminum, there's a titanium aluminum alloy, stainless steel, and silicon. Spheral actually takes each of the individual STL parts and models with ASPH, adaptive SPH, so it just fills in points in each STL shape. And CTH paints in those components on an AMR mesh. On the right here, you can sort of see the top is a rendering of what the DART geometry looks like if you render the STL models and so forth. And the bottom image is Spheral's polyhedral reconstruction of that from the points after we put the points in. And I cut it away because it has voids and openings on the inside of the tanks, which you can see there. Now, the total spacecraft mass is 535 kilograms, and it's distributed between the materials kind of like I show on this table here. And so you can see the aluminum is the bulk of the mass, and that's mostly in that central bus there. But the stainless steel, that last component, is like 60 kilograms, and a lot of it is out in the booms and rollers for the solar panels, so that's not negligible. Okay, next slide. Okay, so to compare the CAD geometry with, we ran a variety of idealized impactor geometries. So the game is we're going to maintain we're going to fix the impactor mass and the impactor velocity. So we're fixing the momentum and just vary the geometry of the impactor. So in both Spheral and CTH, we looked at two impactor geometries, the full CAD model for DART and a sphere, a solid sphere. And then in Spheral, I also ran a few other cases. I ran a hollow cuboid that has the same moment of inertia as DART. And I ran a series of cylinders varying from things that look like rods to flattened discs. And that's just what the stuff on the right is showing you there. I ran 4 different cases there. Now, in all cases, we modeled Dimorphos as the simplest thing possible. It's a uniform silicon dioxide sphere of 160 meters diameter and a bulk porosity of 30%. Okay, next slide. Okay, so the full DART model gives you a pretty complex crater. In this model, we impacted with the DART spacecraft aligned parallel to the surface, so the wings are at maximum extent compared to the surface. If you go ahead and hit next, it should play the video here. And so, oh, there it goes. So that you saw the DART model there slam into the surface, and hopefully you can see that to the sides there, those wings did give you a fair amount of extra ejecta and they're digging into the surface. So the crater you're getting is not a simple bowl. You get that central crater shape that you expect from the central bus, but there's stuff happening on the sides because you have a fair amount of mass out in those steel booms. So let's see, next slide. Okay, this is just a rendering of the density right around the impact site. On the left, you can see the mass density 50 milliseconds after the DART impact. And the areas where it's sort of darker blue and red, that's where you can actually see the densities going up because the porosity has been compressed out. And you can definitely see the imprint of where those solar panels, particularly the booms and the rollers on the end of them, hit. So it's more like a crater complex than a simple crater. And if you compare that to the image on the right, where we just had the sphere impact, you get your more classic, simple, single bowl-shaped crater that is larger and deeper in that bowl, but doesn't have these extensions. Okay, next slide. Okay, so this is sort of showing a whole spectrum of our impactors here. These are all slices through 3D calculations. So on the left, we have all these slices through DART and the sphere and the cuboid, and then the family of different cylinders across the bottom. The cylinders are interesting because they do tend to form a progression. The things that look like rods, which are impacting end on, tend to make bigger craters. They're wider and deeper, and they eject more mass. And as you go to more flattened structures, more like disks, it's a less effective penetrator, and you have a smaller crater and therefore less mass being ejected. And so if you look on the right side here, this plot, what we're showing here, this is a plot of crater width in meters versus depth for all these different calculations. The green dots and green line, that's the cylinder calculations. And again, they sort of form a family. And it's interesting how the other things scatter around that. You can see the sphere kind of falls on that same relation with in terms of the crater geometry with the disks. The cuboid's it tended to go a little deeper and not quite as wide. It actually dug a deeper, narrower crater. DART, the spheral model of DART, which is that sort of solid star, is sort of on the low end. It's making a smaller. We're just measuring the central crater geometry here. We're not paying attention to the wings in this measure. So it's tended to make a shallower and not as wide crater, although it does kind of fall in line with the relations we're seeing from the cylinders in that regard. And I also plotted the CTH results that Mallory was just talking about here as well. And you can see that CTH did get a smaller crater out of this. But in particular, I'd point out that the DART calculations at 13 milliseconds, and now all the sphere results I'm talking about are at 50 milliseconds. So we're not quite at the same time. So it's not clear how to compare those when they're not on the same time like this. Okay, next slide. Okay, so the beta, the momentum enhancement, which is one of our primary things we're worried about here. Let's see what this looks like. So spheral and CTH agree reasonably on beta for the sphere, although spheral is a little higher. The middle plot here shows the DART and sphere calculations using spheral and CTH in the time history of beta. So the solid lines are sphere, and the dotted lines are CTH. And you can see that the red lines there, the red dotted line and the red solid line for the sphere match pretty well up to the 20 milliseconds, which was as far as the 3D CTH one went with the sphere. And then the black lines, the solid black line is the beta history for the DART calculation in spheral, and the dotted one up to 13 milliseconds was CTH. And you can see we're seeing a little more beta out of spheral than CTH, but they're fairly consistent on the scale of these things. So the final beta we're getting, is sort of 1.2 to 1.25, with DART being a little lower, is what we're saying, 50 milliseconds out of spheral there. The left plot is showing that same beta history now for all the different models we ran with spheral, including the cylinders and the cuboid. And you can see the cuboid kind of following its own thing. That's the dotted line. That's one of the lower plots there in that time history of beta. And then the various colors of the dashed lines are the different cylinders. And they definitely form, again, a family with the rod. It looks like a rod giving us the highest beta. It actually gives a higher beta, penetrates better than the sphere. And as you go to more flattened cylinders, beta falls quite a bit. And so you can kind of span the space of betas from like 1.25, say, down to like 1.05 by varying just the geometry and the elongation of that cylinder. Now, the right side is also kind of an interesting plot. This is a plot of the beta you get versus the ejecta mass. And again, the green points are the cylinders, and they're connected by a line because those are a family of things. We can see those form a definite sort of linear relation in this beta versus mass, ejecta mass plot. The interesting thing there also is the sphere, which is the red circle, and the cuboid, which is the brown square, also fall right on that relation. So in terms of beta per mass, the sphere and the cuboid look like the cylinders, and they all form this linear relation, a pretty tight relation. The DART model is an outlier. You can see that it got more beta for less ejecta mass, which is why it's above that line. And then I also have the CTH results here, but they're at different times again. So they're similar betas, but since they're different times, it's hard to make a direct comparison. Okay, next slide. And this is looking at the ejecta velocity distribution. Mallory showed these plots as well. Here I'm plotting them with spheral and CTH. So on the left, we have the spheral and CTH DART and sphere calculations. The dashed lines are the curves that Mallory showed before. And then the solid lines are the spheral results. And we can see that all the codes are kind of finding these sort of characteristic power laws in sort of the resolved regime for the ejecta mass. The DART calculation, these spherals finding that at sort of moderate velocities, you get a little more mass at moderate velocities, which is why that beta came up a little more for DART versus the amount of mass you got out of it. I'll get to Martin's question and the question section. And then on the right, we've plotted all the spheral calculations, including the very different kinds of impactors. So we have the cuboid, which is again following its own line there. It's the lowest thing in terms of ejecta mass versus the distribution function there. And we have the family of cylinders again, which are definitely, again, forming a definite trend where the rod made more high energy, high velocity ejecta. And as you go to flatten things, you're just pulling back that ejecta mass across the spectrum. And next slide. Okay, so overall, we do find the impactor geometry can affect the measurable quantities for things like this. So in terms of the crater geometry, we're seeing about a 15% effect in what you would measure as the main crater. That's about a 1 meter variation in terms of width and depth for DART versus the sphere. The ejecta shows some larger differences. The sphere produces significantly more ejecta mass. We're seeing about 2x in spheral versus 3x in CTH. We agree that the sphere makes a lot more ejecta mass, but a lot of that stuff's moving slower. That's consistent with having the different crater volumes. That effect is a little mitigated in beta because the DART model produced slightly more ejecta at moderate velocities than the sphere. So the sphere still produced more beta than the DART CAD model. We saw that deficit not be quite as much in the spheral model as in CTH, but we both agree that the CAD model produces beta. One thing I found very interesting was that varying the impactor geometry in a systematic way, like those varying cylinders, produced very measurable and predictable changes in beta in the crater dimensions as you go from a rod to a flattened object. And in fact, if you plotted on beta versus mass, the spheres, cylinders, and cuboid all produce very different kind of ejecta clouds and crater volumes, but when you plot them on beta versus mass, they all collapsed onto one line. The DART model did not, and I suspect the DART model might that's because it looks more like a crater complex. I think you're seeing some effects from interacting craters there. But overall, the broad conclusions we got were pretty similar between spheral and CTH, and that is that at sort of the 10 to 15% level, you do need to worry about spacecraft geometry in these sort of studies. And I guess that's it.
Okay, great. Thanks, Mike. We all went a little bit over, so we only have a few more minutes left for discussion. A lot of comments or questions were handled in the chat, so thanks for that. One of the most recent questions, Alberto asked, at deep impact after the collision, a lot of dust was kicked up and it lasted quite a long time. If this occurs in your project, have you modeled this phenomenon? And there are other people in the DART project that have modeled this, I believe. I don't know if anyone, Angela, do you want to speak to that?
Yeah, I mean, we haven't done like specific deep impact models. I know you guys did a few last year. We are looking at that. There are definitely folks on the team who are looking at the ejecta and what sort of it will look like so that we could, compare it to the images. A lot of that is being done using sort of results from deep impact and also from sort of scaling rules. And we just, one of our participating scientists that was just selected by NASA is going to be doing a lot more of that. So stay tuned, and I think we'll have a bit more information on that coming up.
Great. And Martin asks, Mike, what is the size of the damage region in the target? Does it vary with impactor type?
So yeah, so the extent of the damage was varying. Now, I actually modeled the entire dimorphous object, and we're going at pretty high resolution now. It's about 5 centimeters at the impact site. So I cut off the damage modeling for efficiency at 50 meters out. And so they all saw some damage going out to the point where the damage modeling was stopped in the bulk. But the extent of like where the fractures got to and whatnot was a little different between the different cases. And it's sort of similar to what you got from the crater volume in terms of the comparison between the different impactors.
Mike, do you think one implication might be future kinetic impactor missions, we should design the shape to optimize the delta V?
So for an idealized target like we had here, I think you could do that. I think you could design, like you could, if you threw a long rod, you would be more effective. I'm a little worried about how that plays with topography. We need to look next at, what happens if one of these things runs into a pile of boulders, because that's going to break up that ideal geometry of that impactor. It's going to cause it to probably divert to one side or the other. And I think that effect might wash out the sort of effects we're seeing here. We need to actually look at those cases and see.
Mallory, do you want to add to that?
Yeah, well, and excellent question, Megan. I would like to just direct the audience to an e-lightning talk that I spent 3 minutes sort of discussing a preliminary study on the effects of impactor geometries and how we might optimize them for the next generation kinetic impact mission. But we've certainly seen evidence that, right, when the topology of the target surface is held constant, which that's a big if, that we can certainly design the geometry of the spacecraft to be a more efficient impactor and generate more ejecta mass with a higher velocity distribution.
Our first presenter, Dr. David Perna of INAF. So take it away.
Yeah, okay. Thank you, Andy. Can you hear me?
Yes.
Okay, so hi all. So I'm David Perna, and first of all, let me thank all of the co-I of this work. You can see the list here. We come from different universities and observatories in Italy. So I'm here today to present you this ANIME cube submission concept, where ANIME means asteroid nodal intersection multiple encounters. And next slide, please. So if you are attending this conference, there is no need to remind you that near-Earth asteroids represent a risk for our planets, but also an opportunity, in the sense that their proximity gives us the possibility to visit, maybe also with a single transmission, more than one target at once. So we have the possibility to constrain, let's say, the huge diversity that this population shows in terms of physical properties. And in particular, as they are very close to the Earth, we can discover and study very small bodies down to the meter size scale, so which have been unexplored up to now. And so this gives us the possibility to constrain, let's say, those cohesion forces, how this cohesion work in low gravity environments, so to constrain the models for planetary accretion during the first stages of solar system. Next slide, please. So with these goals in mind, we developed this proposal in response to a call for future cube submission by ASI, the Italian Space Agency, in the framework of a GSTP program by ESA, with a 50-month development plan and 2-year operations. So our goal is to characterize targets which are interesting at the same time for science and for planetary protection. So the final goal is to rendezvous with small decameter size near-Earth asteroids, which are also highly ranked in the impact risk tables. And also during the trajectory, we will fly by 2 potentially hazardous asteroids, which are also, let's say, appealing in terms of physical properties. So the idea is to build a spacecraft with commercial components, which are in most part already flight proven. So to have a low cost, low risk, and high return mission, which is kind of a dream, but I'm here to convince you that this is kind of a lucid or realistic dream. And next slide, please. So here there is the baseline mission profile and targets we selected. So in the baseline scenario, we have a launch in late 2026, and then we will fly by 2 potentially hazardous asteroids in mid and late 2027, and then rendezvous in 2028 with the final target, which is 2000 SG 344. As I said, it is a very accessible target. It's also it also has several impact solutions with the Earth in the next century, and it's just around 40 meters in size. So it's an order of magnitude smaller than Itokawa, which is the smallest asteroid visited today. And also the 2004 QD14, one of the 2 PHAs, probably has a diameter below 200 meters, so would be the second smallest asteroid visited, and still could be below, let's say, the rotational breakup limit for rubble piles. Next slide, please. So here, just to say that basically we have a quite flexible scenario. So we have a quite large margin for propellant, for the delta V. So this allow us in the next study phases of this mission concept to change the launch dates, or to select alternative targets, etc. Next slide, please. Here you have the preliminary design of the spacecraft, which is a 12-unit CubeSat, as I said, with mostly commercial components. Most of them have already flown in the Earth environment. Also, the thruster will fly with the Artemis 1 mission. The payload is composed by 2 RGB cameras, which have been renamed NEMOCAM and PHAROS for this mission. And the initial wet mass of a CubeSat is around 20 kilos. Next slide, please. So here you have a table with the main characteristics of the 2 cameras. And so for both of the flybys, we will have minimal distances around 50 kilometers at relative velocities of around 10 kilometers per second. So we will be able to get decimeter scale images, and so to study, for example, the morphology, the boulders, the craters, etc., so to constrain possibly the internal structure and formation mechanism of both the PHAs. And then we will rendezvous with our final target. We have a nominal campaign of 2 months, during which we can have very close, let's say, flybys. So to get centimeter scale images, and we will also perform a radio science experiment. So the idea is to get very detailed data that will be also the input for some numerical simulations that we are already planning within the AMINI mission. So using both streaming instability and body codes. So to constrain again how, let's say, we can pass from grain size bodies to meter size to kilometer size bodies. And let me say also that the constraints that we will put to the heliocentric orbit of this asteroid, the measurement of its Yarkovsky and Yorko effect, possibly will also help to constrain the impact solution with the Earth. Next slide, please. So just to conclude, I say that this proposal just a few weeks ago passed the technical and scientific screening by ASI. So now the financial evaluation is ongoing. And just to repeat that this is really a flexible, low-risk, high-grade arm mission concept, which can be useful for both planetary science and planetary protection, and also for the validation of new technology in this space. So if you want more information, you can contact me, you can see the full manuscript that I have submitted. And I thank you very much.
Andy, you're on mute.
Okay, next presenter will be Dan Shears from the University of Colorado Boulder.
Okay, thanks, Angie. Hope you can all hear me. So I'm going to talk to you about Janus. It's a NASA simplex mission that will explore 2 separate NEO binary asteroids. Next. So here's a artist representation of the flyby occurring. Janus is a real mission. We're currently in phase C, and we are being, the spacecraft is being built by Lockheed Martin, and it will be operated out of Lockheed Martin's Waterton campus in the Denver area. The science team and the mission oversight is being led by University of Colorado Boulder. I'm the PI. And our instrumentation are from Malin Space Science Systems. This talk is a bit more focused on the science goals. So what I'm going to do in this live talk is actually talk a little bit about the programmatics. I also have a recording that's been uploaded, which will go through with animations all the different science goals. So for this live session, I'm just going to focus more on the mission itself. Okay, next slide. So as I said, it's a simplex program. So here's our where we fit into NASA. It's a Class D mission, which means that we can take slightly higher risk which does make it easier. Sort of an engineering way of thinking about it is we can design to 2 sigma instead of designing to 3 sigma events. We have, it's also cost capped at $55 million. So it's much less expensive than, say, a discovery mission, which is about 10 times that. We're a launch share. We launched with the Psyche mission in 2022. And we have our flybys of our target asteroids in early 2026. As I said, it's a partnership between Colorado, University of Colorado, Lockheed Martin, and Malin. Our science team is small but very focused and very well experienced. We have, and it's listed here for your for you to take a quick look at. Next slide, please. So why do we want to go to binary asteroids? Next slide. So binary asteroids are ubiquitous in the solar system and in the asteroid population at about 15%, maybe more. We think they form when you take a rubble pile asteroid and you cause it to spin very rapidly due to the Yorp effect. Then it sort of falls apart and can reassemble into a binary asteroid format. It's also just one of several pathways that we think these small rubble pile asteroids travel down. So by better understanding binary asteroids, we'll be able to better understand rubble pile asteroids in general, which of course has a strong motivation in terms of planetary defense. Next slide. So this is sort of a cartoon showing our current understanding of all the different transitions that a rubble pile asteroid can go through. And these would be rubble pile asteroids, say less than 10 kilometers in size, that are affected by the Yorp effect. The 2 bodies that we're going to fly by and look at are 1991 VH and 1996 FG3, which are at different points in their overall transition through the through these life cycles of rubble pile asteroids. 1991 VH is still in its very dynamic phase. It hasn't settled down yet, whereas 1996 FG3 is a very stable end state binary asteroid. Next slide, please. So these are really ideal target asteroids for us to fly by because they've both been well observed on the ground photometrically and with radar. So we have shape models for both of these bodies for their primaries. For 1996 FG3, we also have a shape model for its secondary, and we have overall size constraints for the VH secondary as well. They're very distinct systems. The 1991 VH system is actually in a chaotic phase. If I was able to show movies, I could show you some cool movies of the secondary. We know it's not uniformly locked spinning around with its orbit, but it's actually spinning in a very chaotic way. FG3, on the other hand, is in a locked, very stable, steady state. Always has this sort of like the Earth-Moon system with the same face, always facing the primary. So we'll get to study 2 very different binary asteroids with our flybys. They're also different types. VH is an S-type, FG3 is a C-type primitive. On the right, you see some of the basic details of the sizes of the binary asteroids and our planned close encounter or close approach distances and encounter speeds. Next slide, please. We have a very basic payload. Instruments from Malin Space Science. We have a visible imager, and this is similar to some of the imagers that flew on OSIRIS-REx. And we have an infrared imager, which is also flown and has heritage. So we'll be able to get good visible viewing of the body across the whole range of phase angles as we fly by, and we'll be able to basically map the temperature on its surface as well. Next slide, please. So this sort of shows a schematic of the science observations that we take during our flyby. This is a very small satellite. If you fold up the solar arrays, you could fit it into an overhead compartment on a plane. Maybe you'd have to push a little bit. On approach and on departure, we'll actually take photometry measurements of the binary systems. And then as we fly by, we'll actually track, because we'll be able to turn the spacecraft as we fly by the system and be able to take observations at the whole range of phase angles through that closest approach. And we'll be measuring temperatures before and also taking visible images. So these are some images taken from the Hayabusa 2 and the OSIRIS-REx mission, sort of showing the relative pixel scale resolution that we'll have at different points. Next slide.
You have about 1 minute, Dan.
Okay, so we have a couple of main goals for the mission. One of the goals is to understand how binary asteroids form. Go to the next slide. The other goals are tied up to the specific asteroids that we're going to. And again, you can see my recorded presentation for a little more detail on that. For FG3, we want to measure the binary Yorp effect. Next slide. And for VH, we want to understand why it's in its chaotic state. Next slide. So to summary, we'll provide the first high-resolution scientific observations of NEO binary asteroid systems with a significant diversity between them. We'll provide insight into the mechanics of robopile bodies and into microgravity geophysics in general. As being part of the Simplex mission, we really define a new spacecraft and mission type of profile that provides a responsive scientific and planetary defense capability for NEO characterization. We've passed our PDR. We've been confirmed by NASA. We're currently in phase C, and we're going to start to bolt things together this summer. And so we're ready and able to serve as one of the inaugural members of NASA's Simplex program. So with that, thanks very much for your attention.
Our next speaker will be Dr. Sarah Sonnet, Planetary Science Institute.
Hello, can you hear me?
Yes.
Okay. Hi, I'm Sarah Sonnet at Planetary Science Institute, and I work on the survey simulator for the NEO Surveyor mission. Next, please. And we've
Sarah, your audio is not good.
Can I?
No, not better.
Can you hear me back?
I think she's gone.
Okay.
No, you're just breaking up.
Okay, I'm not sure what the problem is.
That's
I can
better now, whatever
just
you
try
did.
to keep talking and results. Okay, I just turned off my video, so maybe that's better. Okay.
Yeah, it's better.
All right, I'll try to. Great. Okay, I'll try to speed through the rest of this. So a NEO Surveyor is a space-based infrared mission. It will be a 50-centimeter telescope going to L1 inside of Earth's orbit, and that gives us a nice vantage point for looking in the near-Earth environment. On board, we'll have two infrared chips that will image simultaneously. The first will run from about 4 to 5.2 microns, and the second will run from about 6 to 10 microns. These filters, I think you've already heard about them a little bit from my colleagues' talks earlier this week, but they are especially designed to detect, track, and characterize near-Earth objects. We will nominally launch in 2026. So we're currently in extended phase A. We have a phase B review coming up very soon. The objectives are to discover, track, and characterize hazardous near-Earth objects that are larger than 140 meters diameter. We don't need cryogen, which is a big advantage. We can cool the spacecraft to operational temperatures just by employing a very efficient sunshade and pointing away from the sun. The mission will be led by the Planetary Defense Coordination Office, and Amy Meinzer at University of Arizona is the survey director. As with NEOWISE, if you're familiar with that mission, we will have images and photometry publicly released every 6 months via URSA. Next slide, please. So we planned a 5-year mission, but since we don't need cryogen, we can extend the mission if approved. The field of regard is very large. It runs from about minus to plus 40 degrees of the ecliptic plane in latitude, and then about 45 to 120 degrees in solar elongation. So the diagram on the right is a top-down view of the scan regions. The blue cones are the scan regions, and they highlight that we will be able to sample the region interior to Earth's orbit just a bit, and that gives us an advantage in terms of characterizing hazards coming from that direction. The field of view is large, but so is the scan region. So it will take 11 days, roughly, to complete the scan cycle with our nominal survey pattern. Ultimately, we're going to get about 4 asteroid detections within an 8-hour time frame, and then another set of 4, or another quad, about 11 days later. And if the object continues staying in our scan region, then we will continue to collect quads every roughly 11 days. This gives us a really nice long baseline for pinning down the orbit very well of objects that we detect. And that lets us do all of our own follow-up, so we don't need any follow-up from the ground. We can, if we need to, interrupt the survey for targets of particular interest that can't be followed up from the ground and have an interest in terms of planetary defense. Next slide, please. It's useful maybe at this point just to define a couple of terms. What our cadence is going to give us is about 4 detections within an 8-hour time frame. So what we're going to require is that there be at least 4 viable detections within a 12-hour time frame. So those 2 pairs of detections have to be separated by no more than 12 hours, and that will give us what we call a tracklet. But a tracklet by itself is not long enough to pin down the orbit very well of objects that we detect. So what we instead need is at least another tracklet, and that second tracklet has to be separated by at least 12 hours, no more than 30 days. If those conditions are satisfied, then we formed what we call a track. And if we form a track, then we consider an object recovered. Next slide, please. So the simulator is a pretty important part of the survey at this point. We're using it not just to evaluate the survey efficiency, our progress towards meeting the primary objectives, but also we are tweaking some of the design parameters so that we can optimize the results. We will also be able to use the simulator to quantify biases and help us debias the results. One of the other features of the simulator is that almost all of the parameters that pertain specifically to NeoSurveyor, like the spacecraft properties, the survey properties, the instrument properties, sensitivity overheads, etc., those are all defined external to the main pipeline. So we can change those parameters to be reflective of a different survey like NEOWISE or PanSTARRS, and we can run a survey model of those surveys. That will allow us to potentially debias them, do a more apples-to-apples comparison with our own input models of the results, etc. So these plots on the right show the results of a 1-year simulation using 7,500 synthetic near-Earth objects in our model. And they show that the upper plot shows that a typical track length just within 1 year of operations is about 60 days. And I just want to point out that a typical track has many more than just 2 tracklets. And then a typical tracklet length is about 8 hours. Note that that's a logarithmic scale on the vertical axis. Next slide, please. So the simulator tells us ultimately that, shows us ultimately that we'll be able to recover about 2/3 of potentially hazardous asteroids just within the first 2 years of of survey operations. That fraction will be higher if we're able to combine with another sensitive survey like LSST. The simulator also, as I mentioned, lets us quantify some biases. So we have a known bias against smaller objects, and that's because they tend to fall closer to our sensitivity limits. And we also have a bias against more distant objects because they're colder, so their thermal flux is not as high. The bias against smaller objects is kind of demonstrated in the plot on the right, shows that the fraction of input objects recovered falls off as you get towards smaller objects. Next, please. So in summary, we expect that in the prime mission, in the 5-year mission, we will be able to detect, track, and characterize about 300,000 NEOs. That's about an order of magnitude increase over the known population. For comets, it'll be about a factor of 2 increase. For MBAs, main belt asteroids, it'll be several factors increase over the known population. Within the 5-year mission, we'll reach about 75% completeness in NEOs larger than 140 meters. That completeness goes up by 10% if we extend the mission by 10 years. The completeness for PHAs is even higher, and the completeness will be even higher in all those circumstances if we can combine with LSST. The extended mission will not only give us higher completeness for these populations, but also better orbital, physical, and rotational characterization of the detected objects. That's all I have. Thank you.
All right, our next speaker is Brent Barbie of NASA Goddard Space Flight Institute.
Thank you, Andy. So today I'll be talking about risk-informed mission design for the 2021 PDC hypothetical asteroid impact scenario. So this will include some of the remarks that I made previously during the panel session on behalf of Same Page with the mission options, but I'll elaborate on a few other points in this talk. And here I'd like to acknowledge all of my co-authors and collaborators in the work on this analysis. Next chart, please. Okay, so a quick overview, a little reminder of the scenario that we're studying here. By now, we're all very familiar with it. This is our 2021 PDC hypothetical asteroid, 16-degree inclination orbit, discovered April 19th and impacting October 20th, only 6 months after discovery. And deflection is not practical here. Too much delta V would be required, and so we're considering mission designs for robust disruption. Next chart. So we've been developing what we refer to as a risk-informed mission design process. And so there are many aspects to this, and I don't have time to go into all of it by any means. But what I want to point out is that we're endeavoring to enhance our mission design processes so that we account for the full spectrum of uncertainties, uncertainties in the execution and the outcome of the mission itself, as well as uncertainties in the potential Earth impact effects and a range of other stochastic parameters. We're rolling all that up in an integrated way so that we can design missions that are optimized to improve risk outcome and move away from the current approach to planetary defense mission design, which is based on extremalizing astrodynamical quantities, such as, for instance, achieving a minimum deflection distance for the deterministic simulation of the asteroid's post-deflection motion. Now we're going to be trying to instead optimally affect the risk outcome, which includes the potential damage from an impact. So in this exercise here, what we've done is we've incorporated the NEO properties uncertainties to a certain extent in our analysis. And then we've also fed back the performance envelope predicted for the mitigation mission into the damage risk model outputs. And I've already gone over some of this in my prior remarks, and I'll elaborate on a few points as we go. Next chart. Okay, as you all have seen, Lorian presented the uncertainties in the neophysical properties. And so what we're doing is we're making an assessment of what size of nuclear device would be capable of disrupting, what portions of that set of uncertain NEO properties in parameter space And then what we're doing is we're saying, all right, well, we can't, for example, prescribe a NED yield that would provide a certain level of confidence, for example, 2 or 3 sigma of disrupting the asteroid, because its uncertain properties are so very uncertain. So instead, we're designing the mission in this case to deliver maximum mass and therefore maximum nuclear device yield to the target, using sort of an intermediate class launch vehicle model that would be representative of a repurposed commercial vehicle. I want to emphasize here that this is a double hypothetical. It's a hypothetical scenario, and launch for this scenario would not be possible in practice given current capabilities. We can't turn around a launch in a matter of a few weeks for a mitigation mission. So that's capability yet to be developed. But we want to examine here what we could do in principle if that rapid response capability was in hand. And so that's the purpose here. Next chart. Okay, so one of the things I did not talk about during my presentation of mission options on behalf of SamePage was the effect of NEOWISE observations, which Paul and Lorian discussed after it was revealed in the scenario that NEOWISE was going to be able to help constrain the physical properties of the hypothetical asteroid. And so I don't want to go through all the numbers in these tables. I'll remind everybody that these charts are available online, including an extensive appendix in which I provided all of the technical background. So for those who are interested, I encourage you to check out the charts online and look through the details. But the bottom line is that, prior to the NEOWISE observations, even just to get to a 1 sigma confidence of disrupting the worst case realization of the asteroid would require tens of megatons of device yield under the current assumptions, and just really isn't tenable. After the NEOWISE observations, that slashes the requirement by about half, which is fantastic, but we're still in that tens of megatons requirement regime, which is really, it's difficult to define a requirement there. Next chart, please. Okay, we also found that rendezvous missions are impractical for such a short warning scenario. Low thrust propulsion just doesn't have enough flight time available to it to make a significant difference. We looked at earlier arrivals and later launch dates and found that reconnaissance missions would be viable, again, if rapid launch were possible. And we find that we could disrupt an asteroid up to, perhaps about 210 meters in size, depending on the density of the object. And that's all with delivering roughly 3,000 kilograms to a high-speed flyby with the asteroid. Next chart. And as noted before, I'll remind everybody that a reconnaissance mission that can reduce the diameter uncertainty to plus or minus 10% could substantially reduce the uncertainties confronting disaster response planners. And so the value of a reconnaissance mission can't be understated. Next chart. As well, even if a nuclear device were launched in the face of uncertainty, statistically, it would be able to deal with almost 2/3 of the statistical cases that Lorian was considering, and it would therefore, have a, significantly reduce the chance of damage affecting any population by as much as 57%. So there is value in launching even in the face of uncertainty when the stakes are high. Next chart.
Got about 1 minute, Brett.
Thanks. Once the NEOWISE observations are included, that means that we can reduce the chance of damage affecting any population from 100% down to 33%. So in this scenario, if we had launched, we would have learned after launching that it would have been even more statistically efficacious than we had supposed when the spacecraft left the launch pad. Next chart. Okay, we also found out the actual asteroid turns out to be 105 meters, which would have been easily obliterated by the nuclear device had it been launched, even though we would have known that at the time of launch. Next chart. Okay, so in summary, deploying missions in the face of uncertainty does offer statistical benefits. Rapid launch capabilities are complementary to enhanced early detection. And comprise a complete planetary defense enterprise. I'll leave it there and happy to take questions during the Q&A period. Thank you.
Okay, while we're looking for the next slides, the next speaker will be Jim Bell, Arizona State University.
Okay, can you hear me, Andy?
We can hear you, but we still don't have your slides yet.
Copy that. I can do an interpretive dance.
Yes, there we are.
Okay, thank you. All right, thanks. I'm Jim Bell from Arizona State, and I've talked at this conference in the past about a relatively new organization called the Milo Space Science Institute. I'll just give a brief update about what this is. I'm the chief scientist for Milo, and we're basically trying to test a new model for deep space science-focused missions. Next slide, please. So Milo is a nonprofit. It's a research collaboration led by ASU with significant support from Lockheed Martin. The idea is that we build collaborations, we build consortium of domestic and international universities and space agencies getting together, pooling resources, kind of like the European Space Agency, for example, pooling resources to provide affordable access to deep space, planetary science-focused and science-focused missions, not necessarily just tech demos, but really focusing on trying to check off some of the boxes in decadal surveys with this kind of a model. So we're also interested in having the members of the Institute, and it's a member organization, members join, giving them hands-on experience for workforce development, for education and training, for advancement of commercial space industry and products and supply chain in their own country or in their own university. So it's kind of a big blanket model. We're not trying to compete with NASA or ESA. We're trying to pick off pieces of low-hanging fruit, if you will, that the larger space agencies just aren't able to do because there are so many ideas for missions and limited resources to pull them off. Next slide, please. Major goal is compelling science, decadal survey quality science. We have identified a series of missions to try to start off with, to pitch to members, and we're getting a lot of interest, and I'll talk about two of them. And those missions, those initial inaugural missions for the Institute, are focused on sort of in the neighborhood kind of activity, Moon, near-Earth asteroids, maybe Mars and Venus. We're trying to demonstrate and validate this concept, this entire model, with something, kinds of missions that can be done relatively quickly. And we're trying to keep it relatively low cost. So we're not talking about billions of dollar missions. We're talking about tens of millions to perhaps hundreds of millions of dollars in the kind of class that Dan Shears and others have talked about with Simplex, and that NASA is thinking about with other small sat kind of missions. Next slide. So two of these early concepts that we're pursuing with members and potential members are focused on near-Earth asteroids. One is called Apophis Pathfinder. The mission would use a pair of small spacecraft to do a flyby of the potentially hazardous asteroid Apophis, and the flyby would be designed to occur well before the famous encounter in 2029 that everybody knows about. It's such a big part of this community. But the idea would be to provide some feed-forward information to missions that are going to encounter and perhaps even rendezvous with Apophis in 2029, associated with that close Earth flyby. So that's one. And the second one is called NeoShare. And this is a more generic version of a similar mission designed to launch a cluster, a small cluster of up to 6 small sats to a variety of near-Earth objects that are close to Earth. I mentioned that we're targeting emerging space agencies around the world, universities, space science institutes, and departments domestically and internationally, new space companies, and of course, philanthropy, although our model is not primarily based on philanthropy. Okay, next slide, please. First one, Apophis Pathfinder. Obvious goals, you've heard about them from me previously and from others in this session and others, surface geology, surface topography, crater size, frequency distribution, some information on surface composition and mineralogy, thermophysical properties from infrared observations, and really trying to assess some of the geophysical parameters in the before case. This is observing Apophis before it makes its close flyby of Earth. And that's, in a sense, providing a baseline for the during and after measurements that would happen in 29. Of course, there are planetary defense goals. This community doesn't need to be beaten up about that. Mass, shape, regolith properties, all the things that have been talked about at this and other meetings. Next slide, please. Lots of opportunities to visit Apophis. The 29 close flyby is the absolute minimum on this plot. You can see it there at 0.0003 astronomical units. But you can see all these other local minima where the Earth and Apophis are swinging past each other. And for example, the opportunity in 29 is only about 0.3 AU distance, so can maintain some pretty good communication rates. It said there was just an opportunity last month at 0.11 AU that, of course, we all missed that, but there are plenty of almost annual opportunities to do this. The first launch opportunity that we're looking at is 24, and we could do it again 6 months later. And then in 26, we could also launch, and those would give us encounters, all of those in 27 and 28. So again, well before the 29 flyby to try to feed forward some useful information into those future missions for planning. Next slide, please. Like some of the other small sats you've heard about, simple payload, simple mission goals, RGB color camera, resolution down to the meter scale during the flyby, near IR spectrometer, maybe a point spectrometer, thermal IR imaging multiband for thermophysical properties. And because we're a member organization, individual members have been talking with us about, hey, we'd like to fly a demo of this. We'd like to fly our country's version of that. These are all open for discussion. One of the things we'd really like to test is this concept that recently published by Ryan Park and one of his students, Lou Christensen, in Journal of Spacecraft and Rockets, of trying to get a mass of extremely small objects like Apophis using a dual spacecraft tracking system, multi-spacecraft tracking system. In the case of the Christensen et al. Paper, it was multiple probes, but we have an idea of how to do it with a concept of how to do it with 2 spacecraft, sort of a mothership and a daughter ship. Just by tracking radio or optical tracking of these objects, we believe we can get masses for even small hundreds of meter class objects. Of course, we can't do it with the traditional Doppler methods, but since we'll be in the environment, we'd like to try that out. And so we'd like to test this for Apophis with very, very small probes. They would not impact Apophis. They'd be on well-known trajectories. But if this concept is validated, it could be used widely across the population of small bodies to get a good mass estimate. So that, and of course, mass estimates feeding forward to orbital missions, super useful for designing orbits with a higher fidelity than we're able to do from just assuming a volume and a density. Okay, the next slide.
About 1 minute.
Thanks. Just more broadly, NeoShare is kind of a similar concept with similar small sats, similar simple payloads, but the idea is to sample the diversity of the near-Earth object population with a single launch. We think with a single launch at any given time, there's about 100 near-Earth asteroids that we could get to with typical delta V capabilities for these small sats nowadays. There's also a couple of dozen near-Earth comets that we could visit. And so large selection potential, and you all know about the asteroid soup, the alphabet soup of asteroid classes based on telescopic observations. We could pick and choose from those classes for compositional type. We can pick and choose for size. We can pick and choose for binarity. We can pick and choose for orbit characteristics. We can send six small sats out there. We think we could probably encounter 8 asteroids just as flybys, because some of these could be retargeted to a second object. So the idea is just to start to sample that diversity of this enormous population, 20,000 plus objects, with relatively simple rideshare type or small launch vehicle dedicated type missions in the $50 to $100 million class. So we've got a lot of interest there as well. Next slide. I can skip that. Same kind of concepts as Apophis Pathfinder. Just go to the final slide then. So we are a member organization. Since rolling this out a couple of years ago at IAC and previous PDC conferences, we've had a lot of interest. We had a lot of conversations with over 150 different universities, space agencies, and companies. And we're building these consortia of organizations that are frankly having trouble getting involved with the large space agencies because they don't have the experience. So rather than compete, we've created an environment where members can join, participate directly, and get out of it whatever they need. So that's it. Thank you.
All right. Thank you, Jim. That pretty much leaves us 15 minutes for questions. I noticed that there were some questions that were in the chat, and they have been answered in the chat as well. So actually, there's one that just came in for Dr. Shears right now. What will the imaging resolution be, both optical and thermal, for each body?
Yeah, it's a great question. The visible imaging will be on the order of 1 to 2 meters on the surface for the pixels. And for thermal, it'll be about 10 times that, about 10 meters per pixel on the surface.
Okay, thank you. Actually, I had a question of my own for you, Dr. Shears. You were saying that the mission is on a ride share with Psyche. I assume that then kind of influenced the targets that you were looking at for your mission. Did you have other targets potentially in mind that either had to change once you figured out what launch you were going on, or afterwards?
Well, in the original Simplex call, there were 2 opportunities that were highlighted. One was Lucy, and the other one was Psyche. For both of those, however, we really focused on FG3 and VH, on our target asteroids, and we were able to make it work. I didn't talk about the trajectory, but it uses an Earth gravity assist in order to set up the flybys of these 2 different target binaries. So we were really driven by the science gain that we would get by flying by these particular bodies, and we were able to make it work.
Okay, sounds good. Let's see. A question for Jim as well, kind of on similar lines with your NeoShare discussion there. You were talking about using those CubeSats up to 8 targets in space. Would you just be looking at targets of opportunity once those 6 CubeSats were up there, or would there be some in mind that you would have once you were launching?
No, we would once the consortium is built and we've all chipped in and we can buy a ride and build the spacecraft, then we set the launch date. Gives us the list of targets of that 120 or so at any random time, and then it's there's a science council that's part of the Milo Institute. Every member of the institute has a seat on that council, and the council gets together and says, hey, you know what, here we go, here's the list. Let's get a D type, let's get a couple of S types, let's get an S type binary, let's go for an X type, whatever. Or this object is in a crazy eccentric orbit and happens to pass through the plane when we get there. It would be that kind of an activity, looking at what we know about the diversity of the NEO population and what we want to learn about what we haven't sampled in that diversity. So very much an interactive activity that's science driven.
Okay. We also got another question for you. Another couple questions for you, but I'll take the first one here. Would the Apophis Pathfinder just be doing a flyby, or is there any chance of station keeping around the body to get more detailed information? Imagine the Delta V might be rather extreme.
That's right. Yeah, no, we're just looking at a flyby. It's just an initial reconnaissance. We have to keep this we're trying to keep it in a cost box and a implementation box that is relatively simple, because it has to happen relatively soon. And we do have interest, but we're not there yet. And so we're just looking at a simple flyby, do as much as we can during a simple flyby and feed that information forward to what is assumed to be rendezvous missions that NASA, ESA, JAXA, other space agencies are going to be pursuing, or at least thinking seriously about in the coming years for 29.
Okay. And the second question that came up for you, and now a third, can you expand a little on the size and payload of the CubeSats for NeoShare, maybe a little on the Delta V range capabilities?
Yeah, well, we're partnering with Lockheed on this. And so Dan Shear's presentation was delightfully prescient. Lockheed has experience through Janus and will have flight experience soon. Looking forward to giving you a great ride, Dan, with the Psyche launch. Those spacecraft will have deep space experience soon. And that's an example of a basic small sat model that we're using. So the kinds of capabilities that Dan talked about that the Janus mission has, you can see them in his presentations. Those would be an example of what we could bring to bear. That said, there are some member organizations that are working with us that would like to do entirely their own spacecraft. There are some countries out there that have never sent a mission into deep space, and they want to do that for both the scientific value to their own planetary science and asteroid community, as well as frankly, the national prestige of being able to organize and run a deep space mission on your own. And so, we were certainly totally open to having one or more of those small sats be completely contributed by a member nation or a member university that has their own, and maybe it's a 6U or 12U, could probably go up to about a 12U spacecraft for the architecture that we're considering. And so we're open to that possibility as well. If it seems like I'm being like, this is crazy flexible, it's because we're crazy flexible.
Probably a good thing. Well, let's give you a break for a second. I've got a question for Sarah, if she's on here. I think she is still. You were talking about for your mission that you were looking at a lower bound of sizes of around 140 meters. What would have to change the spacecraft or the mission parameters or anything like that to potentially lower that bound a little bit, maybe get some smaller asteroids?
Well, we certainly have throwaway detections of smaller objects, so we're definitely going to be capable of detecting smaller things. From a planetary defense aspect, 140 meters is of interest because that tends to be the kind of the size range that puts a city at risk. So that's what we've included most in our simulations. It's useful just for speed of the simulations to cut off the model population at 140 meters in our early runs. And we have extended that down to 50 meters for more kind of robust runs. So we will be able to detect smaller objects, though the bias against being able to detect small objects will be more lower than 140 meters.
Okay, great. Sounds good. Thank you.
Sure.
Follow-up question for Dr. Shears. What surface roughness do the radar polarization ratios suggest, if you have them? Given the surprising surface of Bennu, it would be interesting to compare Janus's measurements.
That's an interesting question. We, well, with all of our radar observations, I believe we would have this information. We haven't focused on it, so I can't tell you off the top of my head. As far as I understand it, though, they look typical for their class, VH being an S-type and FG3 being a primitive C-type. So I think our going-in position is we expect them to be similar to, say, Itokawa or Didymos for the S-type, and Bennu and Ryugu for the C-type.
Okay. Back to Jim. There was another question that came up in your stack of questions. Do you think multiple launches, one at each of the 3 to 4 opportunities, are possible, or would you just be looking at one big launch?
certainly possible from a celestial mechanics perspective. But each of those, remember, we're building a consortium of organizations. If we're talking about let's say it's a $50 million mission to use, NASA's Simplex cost as an example, and we want to be able to make this affordable to member organizations that probably don't have big space science budgets like NASA or ESA. So if we're talking about $5 or $10 million, which might be a reasonable amount of money to put into an effort like this, then we need to get 5 to 10 members, right, to do that. And so building the consortium is what we're doing right now. If we happen to find 30 organizations that want to do this and that can fund 3 launches, we'll fund 3 launches. We'll do it. To be honest, I don't think that's going to happen because we're testing a new model. There's risk associated with it. We try to mitigate that risk by involving Lockheed, which has enormous competence on the engineering side. We think we have enormous competence on the IASU side, on the science and mission design and mission operations side. So we bring that to the table. So, but still, as you can imagine, there's a lot of skepticism, and some, especially the smaller new space agencies, have very limited budgets, and so they need to think very seriously about how much risk they want to take and whether the reward is worth it. So that's what we're mostly doing right now. But if the stars align and we get even more interest, and we've got a lot of interest, but if we get even more and can do multiple of these kinds of missions, great, we'll do it.
Okay, sounds good. Thank you. Brent, there were a number of questions for you, but you seemed to answer them all in the chat as we were going through the other presentations. So may have gotten away with it there, but is there anything more I know you fast forwarded through a number of your slides in the interest of time, but it seems like a lot of people who are interested in some of the extra details. Was there anything more that you'd like to say that you may or may not have your slides to back you up on?
Thanks, George. No, I think I hit the main points. I mean, the thing to emphasize is just that if you want to be able to get off the ground quickly enough to react in a scenario like that, you need to have the infrastructure in place in advance, and it's something that needs to be examined so that the capability is available just in case of situations where even enhanced early detection systems miss something. You can't rule it out, and so you have to give some thought to it and work to be prepared. So it's important. As far as the discussion in the chat goes, what we've been talking about is this idea that you need to be able to, and George, you'll appreciate this, because I'm familiar with your dissertation work. You need to be able to hit high C3 values for the Earth departure, but still be able to deliver at least, a couple hundred kilograms or something if you're going to try to do a minimal fast flyby reconnaissance mission. And what we're discussing in the chat is that you can get to those kinds of high energy launch capabilities by adding upper stages onto the rocket, adding solid stages. And so, in fact, the performance data that's included in the appendix of my talk includes a Star 48 solid upper stage on kind of an intermediate class commercial vehicle. So those data were provided by Kennedy Space Center by Bill Benson, who's one of my colleagues. He did that analysis specifically for this 2021 PDC hypothetical scenario. What is still under analysis is, what would the readiness time frame be under current capabilities for that kind of system? So that's something that we don't know yet, something we're assessing. So we're trying to understand, okay, how fast could we theoretically be ready now, and where do we want to go with that, and what would it take to get there? Those are things that we're considering.
Okay, thanks.
Sure.
And to wrap it up, Davide, we have one last question for you. What drives the 2-month rendezvous time at 2000 SG 344? Can this be expanded, or is the limitation of the CubeSat and this particular encounter?
Yes, thank you, George and Paul, for the question. Now, 2 months, let's say it's the baseline nominal stay to reach, let's say, at least the main minimal scientific goals of an mission. For sure, we can so in the proposal we propose this as the minimum stay. For sure, this can be expanded if there are, let's say, logistic economic possibilities. For sure, it will be interesting to stay more. So we try to stay, let's say, as low as possible, also to limit the cost and the complexity of a mission.
All right. So, and with that, I think we've hit time. I'd like to thank all our speakers for their great presentation and all the questions in the chat for the Q&A. Bill, you want to take us home?
Yeah, that'd be great. I just wanted to thank all of the speakers for today. This was a great panel. All of them have been, and the talks, these technical briefings have been just wonderful. So thank you very much. And tomorrow, I just want to make sure you're following the schedule here. Or the program. We've got impact, effects, and disaster management discussions, and that should be a good one because it's quite relevant to us, of course. And then during the panel sessions, we'll have one where we have media people actually talking to us about providing clear, concise, correct information to the public. And as all of you know, anything we do has to go through filters, and the public plays an important part in those filters, and particularly with something like planetary defense. So hearing what they have to say will be interesting. And then secondly, we'll be learning some lessons learned from past disasters and recommendations for how they might apply to a real NEO threat. And then finally, the Planetary Society has an event planned for us, and that should be very interesting as well. So I just invite you to come tomorrow, and we'll continue the process.